In this introduction to 3D printing and additive manufacturing, you will explore core Industry 4.0 principles and the strategic role of digital manufacturing. The course covers key printing technologies, such as material extrusion, powder bed fusion, and vat photopolymerization, alongside essential CAD preparation, slicing techniques, and support generation. You'll also examine real-world applications across aerospace, automotive, and healthcare, while learning practical skills in material selection, quality control, and post-processing workflows. Deepak from GaugeHow created this course.
A warm welcome to all of you in this short course on the role of 3D printing in Industry 4.0. And I am Krishna Kashyap Singh, and I will be your guide throughout this course, and I will take you through each of the modules of the course. But before doing that, or before going to the introduction of the course, I would like to highlight that what is the importance of this course, the significance of this course that it can have in the modern world manufacturing. So, Industry 4.0 is basically related to the way things are manufacturing, the way things are being manufactured in the modern day scenario. And 3D printing is a cutting edge technology when it comes to manufacturing a product. There are multiple advantages of using 3D printing in the manufacturing scenario. So basically, 3D printing is one of the key enablers for Industry 4.0. And when I say Industry 4.0, then it basically means a high tech manufacturing environment, which we often call as smart manufacturing, which is complemented by multiple technologies that we'll be learning in the course. There is a module for that as well. So, yes, I hope you enjoy this course. And after this course, you will have a know how of what is Industry 4.0 and how 3D printing is a key enabler in Industry 4.0. So, let's move ahead and go towards the introduction of the course. So the first module that we will be covering will be Introduction to Industry 4.0. And then we'll be learning about the various types of manufacturing techniques in the module Introduction to 3D printing. Then we will be learning about the various kinds of applications in the strategic and core sectors. So basically the used cases, we will be talking about the used cases in aerospace, defense, automotive, and other such sectors, medical. And we will also go through about the processing which is required for the data that you have to use throughout the 3D printing process. Basically, 3D printing has got a process flow that starts from CAD data and ends up as a physical part on a 3D printer. So, how the data flows, all that we'll be learning in this module. And then we will be talking about a very interesting concept called as digital inventory, which is a game changer for the supply chain industry. And it is a key enabler for manufacturing on demand. And we'll be talking about the multiple concepts surrounding or revolving around digital inventory. Then we will learn the value addition techniques using 3D printing. So when we are manufacturing a component through 3D printing, what are the various or different kind of value additions that can be done? We will talk about them in this module. We will also learn about the various kind of with the various kind of materials uh, which are used in 3D printing, such as polymer, metal, ceramics. Then we will talk about the design methodology used for additive manufacturing, the design techniques, which comes under a broad spectrum of design for AM. So we'll be talking about the most commercially used techniques in design for AM area or design for AM forte. Uh, Definitely, Any manufactured component in the engineering world has to go through a quality assurance cycle. So this quality assurance cycle is not very much different from the conventional manufacturing techniques, but we will be talking about this once again by the end of this course from the perspective of 3D printing or additive manufacturing. So I hope you enjoy all the courses, and there are certain things that I would like to uh, tell you before moving further. Uh, After every module, we will be going through one set of assessment questions which you have to answer. This assessment questions are a sort of self-assessment questions which will help you understanding, which will help you in realizing your grip on each and every module. And by the end of this course, we will be doing a hands-on exercise which you will be able to do sitting at your home from your laptop. I will guide you for that. We will help you in the complete procedure. And we will also have a live Q&A session by the end of this course, where you can ask all your questions, doubts, which you uh, uh, feel that have not been answered in this course. And definitely, even after this course, you can reach out to me, you can reach out to the website, you can definitely seek help. So once you have done all of this, once you have cut, uh, restart. 3, 2, 1. So once you have gone through all these modules, we will talk about, uh, you will be able to uh, realize these particular learning outcomes, which I will be talking about now. Uh, Comprehend the concept of Industry 4.0, identify various 3D printing methods and where they are being used in the modern manufacturing world, explore real world applications. What are the real world applications where you can take the advantage of 3D printing? And then uh, what are the different kind of materials which are used in 3D printing, and what would be the quality control aspects associated with each of these materials? So that was all about the introduction. Now let's start learning, and let's meet in the first module of the course. Let's get started with our first module, which is Introduction to Industry 4.0. In this particular module, we will be covering four topics. The first one is what is Industry 4.0, which will basically cover the definition and explanation of Industry 4.0. What are the various elements, and how they all are integrated into the manufacturing scenario, which is Industry 4.0. Then we will talk about why do we need Industry 4.0? What is the relevance? What is the significance? What are the advantages of Industry 4.0? Then we will take a very brief uh, introduction of the role of 3D printing in Industry 4.0. Where does 3D printing fit into Industry 4.0? Then rest of the modules will be based on the same lines. And we will also be discussing about smart manufacturing. Smart manufacturing is one of the pillars of Industry 4.0. Basically, when Industry 4.0 is integrated into a manufacturing scenario, then that results into smart manufacturing. So let's understand what is Industry 4.0. Industry 4.0 is a commercial or common name used for the fourth industrial revolution. There were multiple stages of industrial revolution, like the first, second, third, and fourth. And the current manufacturing scenario or the current industrial scenario, everyone is trying to transform their industries, their setups into Industry 4.0 setup. Industry 4.0 is nothing but automating and digitizing all the manufacturing and business related processes in the industry. For example, uh, when you have to make a design a component, then the component can be designed in a digital atmosphere. Now this was something that already came during Industry 3.0. But the integration of digitization with automation and things like robotics, artificial intelligence, big data, that resulted in Industry 4.0. Industry 4.0 basically represents a significant change in the way things are being designed, manufactured, and delivered. For example, if you have to design a component, now there are softwares, artificial intelligence driven softwares, which will help you in designing the software, and it will demand much less inputs as compared to the traditional CAD manufacturing softwares. Also, when you have to manufacture the same component, you don't actually need to go and stand in front of the machine to load the job, manufacture the component. It all happens with the help of robots, cobots, and it is all automated. As soon as the designing is completed, the robots will get the instruction that the job has to be set up. They will start doing their work. And as soon as the job is done on a machine through IoT, the system will get updated that the job has been completed, and the robot will take the part and take forward the job for the next process. Not just that, in fact, all the business related processes, all the logistics related processes, all the admin related processes, even they have been automated. You must have heard about CRM, Customer Relationship Management. Now there are AI driven CRM softwares which enable least manual interference. So basically, all the process has been automated. Now, in order to understand the true meaning of Industry 4.0, we will take a dive into the previous industrial revolutions. So the first one happens to be the first industrial revolution happens to be the revolution related to mechanization, where machines came into picture, water power and steam power. Then came the second revolution, where mass production was enabled using assembly lines. Then, with the advent of computers and information technology, the third revolution came into picture. And the fourth revolution, fourth industrial revolution, Industry 4.0, which we are talking about right now, it is basically based on the cyber physical systems. So basically, all the physical systems, the machines, the design software, the robots, everything is talking to each other. So in fact, the ideal Industry 4.0 scenario will be when there is not a single operator involved. The first industrial revolution started in 1760s, and it basically happened in that period from 1760 to 1840. Now, what happened in the first industrial revolution? Why is it called the first industrial revolution? Before the first industrial revolution, things were being made with hands, or things were not, manufacturing was not the game at all. Most of the industries were based on agriculture, or cotton textiles, which were hand woven garments and all those things. But uh, starting from 1760, we saw that there was a introduction of machines, machines which could manufacture part, machines which could simplify the job, machines which could do the job of a person which earlier used to take months. Basically, manufacturing came into picture. Manufacturing started with machines. Earlier, most of the manufacturing was happening through hand. For example, you would have seen For example, you would have seen how swords were being made in most of the movies or most of the web series, where they used to first pour the molten liquid in a mold, then take it out, hammer it, forge it, polish it, and make it ready. But now the same thing could be done with machines. But how was these machines powered? So most of these machines were powered with steam engines. So this is the same period when steam engines came into picture. And with the mechanization part and the invention of steam power, actually what we could see, that factories started coming up. Production started happening in factories. All the production was consolidated at a single places called as factory. So these are few pictures which will help you and understand how the ancient factories came up. These are the first ancient factories which were basically powered by steam power. Then the second industrial revolution, which basically happened between the 1840 and 1870. And in this, we saw that the factories were powered not by steam but electrical power. And it also helped us in putting up conveyor lines, production lines, assembly lines. So basically, rather than one component being manufactured at one place and then manually it was moved to another, there were assembly lines powered by electricity, which started making sure that there is a conveyor belt, and the components or the goods that were being manufactured, they were put on the conveyor belts, and they were moved from one station to another where each specific job used to happen. This was basically through electrical energy, and it enabled mass production. Then the third revolution came. Now, this picture is very clearly indicating that the third revolution was because of computers. So, between 1870 and 1940, when computers became a thing, then at the same time, industries also started adopting computers. And the information technology helped in digitizing the manufacturing process to a large extent, and the result of those were CNC machines. CNC machines came into picture. All you had to do is to enter a code in the machine, that how the part will be made, and then the machine will take care of the rest. And this helped us in putting the large automation lines that we see today, in the way in which cars are being manufactured, the way in which multiple goods in large numbers were being manufactured. So this basically helped in improving the capacity of the factories in terms of the numbers of goods manufactured. The second part of this module, we will try to understand what is the need of Industry 4.0. Or in other words, what are the advantages of transforming into Industry 4.0 for any organization or any company or any factory? So the significance of Industry 4.0 is very clear in terms of the efficiency and productivity. Now, as you see, the automation and the data-driven decision making helps in increasing the efficiency and productivity. Since there is no human interference involved in the decision making is being based done on the data that the manufacturing during the manufacturing process has been derived using the IoT driven sensors. The machine is able to take the decision itself. So it is fast, it is quick, and the factories can optimize the production process. And also, using the same efficiency, the same decision making ability, the factories are able to reduce the downtime of the machines involved in the manufacturing process, and that they help us in utilization of the resources in a much better way. For example, the machine will exactly tell you, okay, if you want to build a job of this dimension, then what is the raw material size or raw material in what quantity is required for the process. So these decision making would have taken time if there would have been a manual interference involved, which is largely happening with most of the factories. Only a fraction of the factories have transformed themselves into Industry 4.0. That is the reason why it is an upcoming technology. But in short, it helps us in improving the efficiency and productivity. Then, if a productivity improves, then definitely the cost goes down. If I am able to make 10 components in a day and I am able to make 100 components in a day, then the cost of 100 components which I am able to manufacture, which will be much lesser as compared to the cost of those 10 components, because I have been able to reduce my labor expenses. I've been able to reduce my waste or scrap. in manufacturing, the waste is largely called as scrap, and also it helps in improving the energy efficiency. So all these things contribute towards a better costing of the product. Then the third point refers to quality improvement. Now, since I told you earlier that there are a lot of sensors involved, now these sensors helps us in analyzing data in real time when the process is going on, manufacturing process is going on. And also in few scenarios, we can do real-time improvements in the manufacturing process. Thus, any component that I'm making through this process will have a better quality and there will be less chances of rejections. I will be able to manufacture high quality components consistently. Then the fourth point is customization and personalization. Now, Industry 4.0 using additive manufacturing as one of the techniques. There are many techniques, many manufacturing processes such as additive manufacturing involved in Industry 4.0. It helps you to give a customized and personalized touch without any added cost. This is important. Please note that customization can be done without any added cost, and thus you can meet the demand of individual organizations, individual people, or individual country. Geography wise also demands varies. Geography wise, the requirement of a product varies. For example, people sitting in India do not have the same body structure as the people sitting in Africa or people sitting in Australia. So if I talk about a hip implant, then that particular hip implant will be of different shape for people sitting in India and people sitting in Africa. Now, at the same place, you can manufacture uh, both the components without any added cost. Supply chain optimization. This is definitely one of the biggest advantages, because if I talk about smart decision making, then the smart decision making helps in forecasting the right demand for any region, any product, or any given set of target audience. So it helps me in optimizing my logistics and it helps me in managing my inventory in such a way that I only have components which is required for a particular area. Then the sixth point of significance is work safety and ergonomics. Now, all the hazardous or risk-taking jobs where we have chances of the operator, a person who works as an operator, getting injured, those can be done by the robots. So the more risky jobs can be done by the robots, and humans can help in designing, programming, and updating the robots to achieve maximum efficiency. So it basically gives any person working in that environment a overall job satisfaction. Then sustainability. Definitely, as we discussed, that Industry 4.0 methods have less waste produced. They are more greener technologies. The resources are much more optimized. So they have a very sustainable impact on the environment. So when we talk from the perspective of environment, definitely Industry 4.0 is a better choice compared to their previous kind of industries. Then all these things, if combined together, they will give any organization a global advantage with their against their competitors. So anyone who has not implemented Industry 4.0 and any organization who has implemented Industry 4.0, the one who has implemented will be able to produce much more number of components in a more greener way as compared to the other one. So efficiency, innovation, job satisfaction, supply chain optimization, you can multiple. These are the few that I have chosen to explain you, but there can be multiple other, and all these contribute to the economic growth of a company, of a state, of a region, of a nation, or global, of a global company as well. So these were about the significances. Now, after understanding the significances, it is very clear that what benefit Industry 4.0 will give us. Thank you and see you in the next part of this module. Now we will start the third part of the first module, which is understanding the role of 3D printing in Industry 4.0. So we'll move further, but I would like to start this module with a video which will give you a comprehensive idea of how 3D printing fits into the Industry 4.0 scenario. So as you can see in this video, there is a cobot which has been integrated into a 3D printing farm. Now, what is a 3D printing farm? Where multiple 3D printers are trying to print components. Now, these 3D printers were earlier handled by uh, human operators. So there was a limitation in terms of the time at which the 3D printers can work or not. But the good part is that all the 3D printers are IoT enabled. And the what I mentioned earlier about cyber physical systems. So one 3D printer, rather than one, all the 3D printers are talking to the cobot. So the cobot exactly knows when to put a base plate and give the command to the 3D printer to start the job. And when the job is completed, the 3D printer will remove the job and prepare the machine for the next job. Also, there is a conveyor belt that you can see in this video. So the cobot will remove the printed job from the machine and put it on the conveyor belt so that it can be taken up for the next post-processing operation. So this video is by Insider Tech and Voodoo Manufacturing, where they have successfully implemented 3D printing in an Industry 4.0 scenario. Now let's talk about one more example of 3D printing in Industry 4.0 scenario, where we are using where we are using Industry 4.0 integrated 3D printer itself. So as you can see, in this case, the robotic arm itself is doing the 3D printing. This is the example of metal 3D printing where the component is being made real fast, and all of this does not require any human interference. So these are the two examples that we covered. Now let's try to understand what advantage of using 3D printing in an Industry 4.0 scenario is very much visible. So we spoke about how Industry 4.0 is focused towards customization and personalization job, and 3D printing is something which is the best suited manufacturing method to manufacture components on demand, and it is capable of manufacturing unique components. For example, if there is a 3D print build volume where I can fit 5 components, all the 5 components can have different designs, and there will be no effect on the cost. If I have to manufacture all the components of the same design, the cost will be same. If I have to manufacture all the components of different design, the cost will be same, given that the volume and time of manufacturing of the components is nearly same. So you can make tailored items using 3D printing. And this is what we discussed in the during the significance of Industry 4.0 as well. Then supply chain optimization. Now, how 3D printing enables supply chain optimization? 3D printing allows you to manufacture components at different locations rather than conventional factories where all the components were manufactured at a single location. Now, what happens that this helps in reducing the supply chain cost. The parts can be produced near to the actual use of the component. So this is called as distributed manufacturing. This gives flexibility to the manufacturer, and it does not involve the cost of transportation from one place to another. because it is all digital data driven. One person sitting on a computer in some other country can give command to a 3D printer in some other country and the job can be done. It it will eventually help us in reducing the lead time of manufacturing that component and also the cost associated to it. Then on-demand manufacturing. So what I just covered is basically on-demand manufacturing. When you need a part, then only you manufacture it. No need to maintain an inventory of components. When you know that your part is has become non-functional due to some defects in the part, then itself at that time you can manufacture the component using 3D printing. So all these principles are in line with Industry 4.0. So that is why I have said earlier, 3D printing and Industry 4.0 go hand in hand. Then lead time is certainly reduced because you are not adding material, you are removing material. In the next module, which is focused on 3D printing itself, we will try to understand how 3D printing helps us in reducing the lead time, but it definitely shortens the product development cycle. How it does that, that we will understand in the next module. Sustainability. There is no doubt that 3D printing is the one of the most green way of manufacturing. It has very less scrap, so it is considered as a very sustainable method of manufacturing. Now, digital twin is a new concept here, which we did not discuss in the Industry 4.0 part. Digital twin basically is like whatever manufacturing you are going to do, you have a digital replica of it in your computer. So before doing the actual manufacturing, you can simulate the whole process, and these digital models can be tested with the real world scenario. So you will exactly know, okay, when I'm going to manufacture this part using 3D printing or any other advanced manufacturing Industry 4.0 method, what is going to be the implications or how the part is going to come out. Once you are satisfied with the end result, then only go with the manufacturing. This will also help you in reducing the waste. Now, IoT and big data is one of the key element of digital manufacturing. So 3D printing is one technology where it is very easy to integrate the sensors. In most of the 3D printers, these kind of sensors will already be there. All you have to do is devise a methodology to acquire that data using those IoT sensors, and then uh, analyze it and come out with a better way of production. And all of this can be done using software tools. So this was about the role of 3D printing in Industry 4.0. Uh, let's move forward and try to understand how does 3D printing work and how will it enable all these points in a manufacturing scenario. But before moving to the next module, we will cover the last part in the next video, which is smart manufacturing. So yeah, that's it about the role of 3D printing in Industry 4.0. So what are the key technologies involved in Industry 4.0? The key technologies that involve Industry 4.0 are big data and analytics, IoT, Internet of Things, AI and machine learning, the cyber physical systems, basically the uh, physical systems talking to each other via IoT and taking smart decisions, being flexible with the help of big data, AI and machine learning, and additive manufacturing. So this whole course is based on how additive manufacturing plays the role in Industry 4.0, and you can see that it is a key element when we talk about Industry 4.0. And then cloud computing, all the data going and being stored on a single space, in a single space on the cloud. And then the last one is AR and VR, which is very popular these days. All of you must be experiencing a surge in the use of AR and VR. So it basically helps us in simulating all the processes before the actual manufacturing process. So now all these key technologies play a very significant role in making our factories smart and in converting our industry into Industry 4.0. So they are the pillars of Industry 4.0, but for this course, we will be focusing on additive manufacturing to be precise. And yeah, so this was about the basic introduction of Industry 4.0. See you in the next part of this module. Welcome to the second module of the course. The second module is about giving you an introduction to 3D printing. What is 3D printing? And in the second module, we will be learning about the very basic definition of 3D printing or additive manufacturing. Now, again, I would like to repeat myself that 3D printing and additive manufacturing are two interchangeably used words. I will also be using both the words 3D printing and additive manufacturing, but they refer to the same thing, same technology. Now, then we will be learning about why do we need 3D printing? What is the advantage of using 3D printing? And then we will talk about the various 3D printing technologies classified by ASTM based on the nature of their process. Then we will be learning about the major additive manufacturing or 3D printing techniques which are being used in the commercial market. How do they work? What is their working principle? And what are the kind of materials that they deal with? So let's get started with the section 1 of module 2. Uh, Additive manufacturing is one of the process where you don't remove the material to give the desired shape. Now, right now, what you can see on your screen, this is a schematic representation of subtractive manufacturing, where you take a block of material, start removing the, start cutting material away from the block based on the program generated by the CAD model, 3D design CAD data that has been given to the machine. And finally, you end up in the desired shape or the object that you wanted to produce. But this has happened by removing material. Now, when we talk about additive manufacturing, the same shape or the same object will be achieved, but not by removing material, instead adding material layer by layer. So additive manufacturing is the process of creating an object by building it one layer at a time. Whereas in subtractive, material is removed from a large block or a big block of material. Uh, After removing the material using a cutting tool or a machining tool, the object will be remaining to its final shape. In this schematic, you can clearly see that a raw material of block is taken. Then the raw material of block is undergoing a machining operation, and the material is removed based on the machining operations input. And what you achieve is the final product, which in this case has been represented by the spherical shape. So the what machining is doing, it is converting a block of solid block of material to a spherical desired shape of material by removing material. And the material that has been removed in order to desire the final to get the final product, that is the waste material. Now the scrap rate is usually very high in subtractive manufacturing, whereas in additive, what we do is that we start with a spool of material, wire of material, or material can be in powdered form. Both inputs are it depends on the process. What is the process? Based on that, the input material is decided. Then we start the printing process using that input raw material. Once the printing process is done, that means that the material is added layer by layer, then we reach the final product, the desired shape that we wanted to create. Now the advantage here is that the waste material that we have created is very less as compared to the final product, because you have used the amount of material precisely as much as it is required to create the object, and little bit of wastage. Whereas in subtractive, you have removed a large amount of material. Whatever was not required, you had to remove that, because you are starting from a fixed shape and you have to reach a desired shape. Now Uh, we will understand additive first, but in order to understand additive, first we need to understand what is subtractive manufacturing. And for that, I'm now going to play a video. In this video, you will see that how subtractive machining process gives shape using cutting operation or material removal operation from a solid block. So as you can see that the solid block has been taken, mounted on the CNC machining center or a milling machine, and a cutting tool which has been designed to remove material at a very high speed and with minimum defects is rotating at a high RPM, which is attached to the spindle head of the CNC machine, and it is removing material as per the input given to the machine. Now, slowly, it will keep removing material in multiple steps or depending on the strategy, how the operator has made the program. But based on the program, it will keep on removing material, and ultimately it will try to attain the shape that has been given as the target shape to be obtained after the machining process. And for this also we need to upload the 3D CAD model, and we also need the 2D drawings in order to decide upon the right tolerances to be produced during machining. So this is subtractive machining, and you can see that using different set of cutting tools and different cutting operations with different cutting parameters, the final desired shape is obtained. Now again we will see a video of a very short video of an additive manufacturing process where we will see how material is being added. Since the subtractive machining process was for a metal, the additive manufacturing process also that I'm going to show you is for metal. Now in this video you can see that the material which is raw material in form of powder, metal powder particles, is coming from a laser head, and from the same laser head laser is also coming out. Now this laser is giving the energy to melt the powder particles and deposit it in a specific manner, and as soon as it solidifies, it is solidifying in the shape of the uh, data that was given for the 3D printing operation. So it is you can very clearly see that the laser head is only depositing material in the area where the data has been given to the machine. Now this data will be given by slicing of the 3D CAD model which you want to produce. But the advantage here is that you only need to deposit material which is uh, required to be there, and slightly some extra that we will understand what are the requirements. Yeah, so now we understood okay, how what is additive, what is subtractive, how both of them are varying from each other in terms of their working principle. Now we need to understand why do we need additive manufacturing. So there is a very interesting example of additive manufacturing case study. This is a BMW chassis, a BMW two-wheeler bike. We all know that BMW bikes are known for their high performance. And in automotive, performance to weight ratio is very important. They either need to increase the performance or they need to reduce the weight. So this performance to weight ratio that we are talking about, uh, a large weight of the vehicle is contributed by the chassis of the vehicle. And in this case, they tried producing a 3D printed chassis because they wanted to reduce the weight of the chassis. And this particular case, if you go and explore further, you'll be able to find that around 40 to 50% of the weight of chassis was decreased using a unique design technique called as topology optimization. That is why this is looking like that. Now, topology optimization is something which has come up with additive manufacturing, and it basically mimics the natural designs in order to create a structural design. So that is why many of us say that additive manufacturing is the natural way of creating things. And like this, we can create more complex designs. And more complex designs will help us in improving the performance of the component or the subsystem that we are designing for. It also leaves us with less waste material, and inherently it is much faster as compared to the other conventional manufacturing techniques such as subtractive or forming, and there is no tool required in order to make uh, components through additive manufacturing. So making a component through additive manufacturing gives us various advantages, whether it be in terms of lead time, or whether it be in terms of higher design complexity. So all of this can be leveraged if we choose additive manufacturing as the final route of manufacturing for any component. Now, this is a very interesting comparison. This comparison basically, when you see the blue curve, that is your conventional production, and when you see the peach curve, that is your 3D printing line. Now, as the design complexity increases, the cost of manufacturing a component increases as per conventional production. Whereas in 3D printing, with the complexity, there will be an increase in cost, but the increase will be very minimal as compared to conventional process. So if you have really high complex design components, then conventional manufacturing might end up being more costlier as compared to 3D printing. So if we are in this zone, we can choose 3D printing as one of the preferable way. Then we have the second graph where you see cost versus number of components. Now, when the number of components increase, conventional manufacturing technique allow us to reduce the cost per component. Whereas in 3D printing, the cost will decrease, but again, the decrease in cost is very minimal if the volume increases. So if you are having low volume of certain type of components, then you might have paying more amount through conventional process for manufacturing and less through 3D printing. So when we are in this region, when it comes to number of components, 3D printing is a more suitable way to suggest for manufacturing. Now, since we have understood about additive and traditional manufacturing process, let's try to just plot down the comparison. Okay, how do they compare when it comes to few of these entities, like production time? So additive manufacturing is usually having less production time as compared to the traditional manufacturing process. Material wastage is definitely less in additive manufacturing, again, as compared to the traditional manufacturing process. You can allow for easy customization in additive manufacturing, because if I'm building 10 components in a single build in additive manufacturing, all those 10 components can have different kind of designs. Whereas in traditional manufacturing, it is difficult to customize, because when we try to customize each and every design program has to be generated separately, and there is some setup time involved in changing from one design to another. It is definitely cheaper to make prototypes because there are no tools involved, and you are using less amount of material and the time taken is less. Whereas traditional manufacturing processes prove out to be expensive when it comes to making prototypes. Then the labor cost is very much reduced when it comes to additive manufacturing, because there is less human labor involved. And as traditional manufacturing suggests, it's the traditional way of manufacturing, so labor costs are more. So this was about additive and subtractive. So I hope you understood what is additive. Now, from the next section of this module, we will try to understand in detail what are the different kind of additive manufacturing processes that we will look into once we start uh, getting deeper into the manufacturing realm. Thank you. Welcome to the second section of module 2. And in this section, we will learn how ASTM has classified the various additive manufacturing processes. So if you see this particular slide, there are 8 kind of processes that ASTM has defined to be of additive manufacturing. The first one is Vat Polymerization process, which basically uses a resin as a raw material. Then there is powder bed fusion, which is used for metal polymer both. where powder particles are used as the raw material. Then there is binder jetting, in which again powder particles are used, but along with binders. Binders are like adhesives for powder particles. And then there is material jetting techniques, where using an extruder, material is jetted along with the binder and to give the desired shape. Then there is sheet lamination. In sheet lamination, various sheets are joined together to give the desired shape. And then we have material extrusion. Material extrusion is one of the most popular techniques, popularly known as FDM. We'll learn about that as well. And DED, directed energy deposition. The video that we have seen in the previous section where I introduced additive manufacturing to you, that video was for DED. And then hybrid, where additive and subtractive, both the process happens together. So let's get started with Vat polymerization. Uh, in the coming few minutes, I will introduce each and every technology to you, but don't worry, we will be learning more in detail about those technologies in the later sections of this module. So vat polymerization is basically a technique used for vat photopolymers. So the photopolymer materials, they are used in resin format. In resin form, they are fed as raw material in this technique. And a UV light comes and cures that resin to form solid polymer. That is the very basic principle of photopolymers, that upon curing by UV rays, they become solid. Now, in this, the energy source can be a UV light or a laser as well. Laser also does the same job of curing the photopolymers. And the commercial, very popular names of this technology which are used in the market are SLA, stereolithography apparatus. This similar process is also commercially very popularly known as stereolithography. And then the other name is DLP, direct light processing, where we use a projector or UV light. Then we have powder bed fusion. Now in this, what happens that uh, powder is spread layer by layer, and an energy source, which is laser in 99% of the cases, it comes and either centers those powder particles together or melts the powder particles selectively to give the desired shape. We will have a detailed understanding of these techniques later using videos as well. Now, in this, the raw material can be a polymer or a metal, but it has to be spherical powder particles. And the energy source can be laser or electron beam. Electron beam gun is also used as an energy source in this regard, in this case. And the very popular commercial names that you will come in the market is SLS, which is used for polymers. SLS is selective laser sintering, and it is used for sintering powder particles of polymers together to form solid polymer parts. And then direct metal laser sintering is sintering of metals. Selective laser melting is melting of metal particles, powder particles, to join particles together. And the same thing which is done in selective laser melting or DMLS, if the same thing is done using an electron beam gun, then it becomes electron beam melting. So this is about powder bed fusion. Then we have binder jetting. Now binder jetting is again very much similar to powder bed fusion, but in this, uh, instead of melting or fusing the powder particles together using an energy source, what we are doing here is that we are uh, selectively dropping binder additives in the powder bed which has been spread. Now this binder will be dropped as per, very precisely as per the 2D layer data, which is again been derived by slicing of the 3D CAD model. So binder jetting may there is, in binder jetting there is no uh, e- energy given by a laser or an electron beam gun. Instead, binder cures the powder particles, sticks them together, and later on they are put in UV chamber and the curing is done in that UV chamber. That is where the part gains all its strength and the binder is removed from the component. Then there is material jetting. Now, material jetting is very much similar to binder jetting, but in binder jetting, the powder particles are being spread in a layer-wise fashion, whereas in material jetting, the material and the additive, the binders, they are coming from the same nozzle. And selectively, the binder as well as the powder particles, the material that is being deposited based on the 2D layer data that has been given to the 3D printer. In sheet lamination, you can, it is very simple to imagine. You imagine that you are cutting a sheet metal design from a large sheet and using laser cutting, and then you are welding multiple layers of laser cut sheet metal together to give form to a 3D object. So in this, the layers are not created using 3D printing. The layers are cut and then they are welded together or they are joined together using adhesive to give the desired 3D component. This is a slightly not so much used technology currently commercially. But yeah, the very common names that are used for this technologies, commercial names are LOM, Laminated Object Manufacturing, SDL, Selective Deposition Lamination, ultrasonic additive manufacturing. Basically, this is used for metal sheet lamination, where the metal sheets are joined together using ultrasonic welding. And the raw materials that this can be used for can be paper, plastic sheets, metal foils, or tapes. And the energy source is either adhesive, glue gum, or ultrasonic welding in case of metal, in case of polymer, adhesive. Now, material extrusion is again a very interesting technology, which was because it has picked up very fast and a very quickest possible way, and it is one of the technologies to start with because it is more affordable as compared to other technologies. It is popularly known as fused deposition modeling, where an extruder will come and it will keep depositing material layer by layer. First of all, in each layer, it will deposit material only in selected area as per the command given to the extruder based on the 2D CAD data. And when one layer is completed, accordingly it will shift the Z axis and start printing the next layer on the top of the previously printed layer. So this is basically used for thermoplastic filaments, thermoplastic polymers. And now few people have started using it for metal as well. That's a slightly different technology than this. And it is used for liquids, slurries, for micro printing. It is used too much. Now the energy source involved here is the extruder. So basically, this point that you see from where the metal filament is coming, it is a heated extruder where the thermoplastics deform, melt and deform, and then it is easier for the extruder, for the deformed or molten thermoplastic, to lay it down in the desired shape. Now, directed energy deposition is again something similar to FDM, where a robotic extruder is depositing wire. But apart from that, the difference is that it also has an energy source which can be in form of an electron beam or a laser or a wire arc gun. So it is used for metal particles. Now, metal wires are fed and they are molten down and spread based on the 2D CAD data. This is something that we will read about in too much detail because it is of a lot of uh, importance when it comes to metal additive manufacturing, which is currently being used in the industry. The common names are laser metal deposition, LMD, lens, uh, laser engineered net shaping, DMD, direct metal deposition, uh, and the materials that we can use here are metal wires, powder particles. In fact, ceramics also can be 3D printed using directed energy deposition. Now, hybrid is when we combine directed energy deposition along with subtractive machining capabilities. I will show you in the videos how it is done. But just to understand right now, hybrid is the combination of subtractive and additive. Now, in the same machine where your wire will be deposited to give a desired shape, you will have capabilities to cut and finish those areas using subtractive manufacturing. And in 90% of the cases of hybrid technology, the energy source is laser beam. Nowadays, people have also started using VAM, wire arc additive manufacturing, to couple with subtractive in order to get hybrid additive manufacturing. So this was about the ASTM classification of additive manufacturing. Uh, Now, in the next part of the module, what we will be doing is we will be learning about each of these technologies in detail, but we will limit ourselves to the only ones which are commercially being used in the industry and which have been able to scale up in terms of production volume and in terms of cost, uh, revenue in the last few years. So thank you and see you in the next. Let's get started with the third section of the second module, where we will be learning about Vat Photopolymerization in a bit detail. So to start with, to give you a fair idea of how the process looks like, I will just start with a video. So this is the metal base plate on which the part will be printed. It is mounted upside down, and this is the resin tank where the resin will be stored. Now, the bottom structure of the resin tank is clear so that the laser can pass through it and cure the resin material. Now, the resin tank is filled with resin, and the base plate comes in contact with the resin, and a very fine layer of photopolymer is cured. And layer by layer, this process is repeated. The result is the part. Once the part is printed, it is taken out, washed, and you can see how photopolymerization 3D printing part, SLA, stereolithography, looks like. So now we saw the actual process, but how it works will be explained by schematic. Now you can see that there is a laser unit which is reflecting on a mirror, and by the movement of the mirror, the laser path on the resin tank is being controlled. Now wherever the laser reacts with the resin, it cures it and makes it a photopolymer. Once this process is repeated, the resin tank moves down or up, and then uh, a fresh set of resin is displaced. And in the fresh set of resin, again, based on the second layer data, the process starts. Now, we saw that there is a laser, there is a platform, and the photoresin is being cured by the laser. And wherever the photoresin reacts with the laser, there the solid object is created, and the same process keeps repeating layer by layer. Now, why did we start with photopolymerization? Is because Vat photopolymerization was actually one of the first 3D printed processes that was discovered. Not discovered, which was invented. Yeah, invented would be the right word. And till now, it has been able to produce the finest features and the best of the surface finish. The precision at which SLA can print is really great. In fact, it has given birth to another area of 3D printing, which is known as micro 3D printing or micro stereolithography. Another advantage of using this technology is that the there are bioresins available, resins which are biocompatible, so they can be used for medical purposes as implants. Now, to be precise, there are three categories of photopolymers. based on the light source or the energy source that they use, and based on how the energy is directed towards the resin layer. Now, the first one is stereolithography. Now, if you look at stereolithography schematic, you will see that the platform is upside down mounted. So, and it is at the bottommost position when the first layer is being printed, and slowly it keeps moving up as the number of layers of parts that have been already cured keeps increasing. Now, in this stereolithography, there is a projector, there is a mirror and lens that comes and cures the part. Then there is digital light processing. In this, there is a white light source which is used instead of a laser or an energy source. So it is this laser light is basically nothing but your projector light that you use in a projector. Then one more technique is continuous digital light processing. Now in this, the platform doesn't move up layer by layer, it keeps moving continuously, because in this process the idea is to be able to print micro features which are of size in the range of microns, like microneedle prototypes, as you can see in this image. Uh, so because of this continuous motion, we are able to adjust the printing parameters in such a way that we are able to achieve very fine features. And definitely there are other modifications in the machine as well. Now, what is the advantage of vat photopolymerization is that it is one of the fastest technology. When it comes to the production rate, it is the fastest. And we can really produce very small features using this particular technology. Uh, Another advantage that it helps us in making watertight parts. Matlab parts which can be used as storage for liquid items or liquid fuels, other things. Because the curing happens in such a way that there is no porosity in the part at all. Then the finish in all the polymer additive manufacturing processes, the finish of photopolymerization, vat photopolymerization is the best. The repeatability is consistent, and the resin can again be used, whatever resin is left in the tank, that can again be used for the next build. Also, one big advantage for the medical industry here is that through this process, they can make biocompatible implants. The disadvantages, the disadvantages are that these resins that we use, they are really expensive, and there are very limited set of materials available. Also, the post-processing time is very long because you have to wash, you have to cure it sometimes, depending on what process of that photopolymerization we are using. And if the parts are over cured, they become brittle as well. Also, when the parts during their application are being exposed to the sun for a long time, they will develop brittle tendency. So this is the disadvantage. Now, the typical applications of vat photopolymerization, the very popular one in India, from where it all started, is was into jewelry sector, where they used to make wax patterns for the final investment casting process. So the final jewelry will be made through investment casting process, but the patterns used in the investment casting process will be 3D printed using vat photopolymerization. And then dental applications, where molds for dental uh, development, dental implant development, and for dental surgery study were being made. In aerospace, vat polymerization is being used for short runs or productions, prototyping. In automotive also, now it is being used as a good alternative for vacuum casting. So in the applications module, we will definitely learn about the precise applications in what industry it is being used in what way. So that was about Vat photopolymerization. Thank you, and see you in the next module. Welcome back to the fourth section of the second module. And in this module, we will learn about powder bed fusion in detail. So as we have set up the strategy of watching a video first, let's go ahead with the quick video to understand how does powder bed fusion work. So this video is of selective laser melting, selective laser sintering, one of the powder bed fusion methods. So you can see that the 2D CAD data for each and every layer has been set in the machine, and the laser, which we cannot see with our bare eyes because the laser is in the invisible range. One layer of powder is spread and the laser selectively fuses uh, the powder particles to form solid bulk polymer parts. And once one layer is done, the build platform moves down, a fresh layer of powder is spread, and once the same process is repeated layer by layer, the whole part is made. The full powder bed is taken out, and in a powder handling machine, powder handling equipment, the build is uh, cleaned and the powder particles are separated from the solid components. So you can see these are the components. Now once we get the components, they are short blasted to remove the powder particles completely. In this component, you will see that the parts are small, so they have been put in a net and they have been cleaned out of powder particles. This is what the part looks like. So I hope it is very clear now what powder bed fusion looks like. Now that was for polymer. That's why we called it selective laser sintering, where laser is the energy source and powder particles are the uh, feedstock, raw material. Now let's have a look at selective laser melting, which is used for metal particles. So same in this, layer by layer, powder will be spread and laser will come and melt the powder particles and quickly solidify them to form bulk metal. So the what in the previous case we were not able to see the interaction of the laser and powder particles, but since it is metal right now, it is ionization is happening there. So that's why we can see these sparks or spatter. Now a fresh layer has been spread, and again based on the next layer CAD data, the melting starts selectively in the areas. Now once layer by layer this process is completed, the whole build platform is moved up along with the powder and part, and using a fine brush we remove the powder particles, and this is the part which will be made on a base plate which we had fit in the machine. Now this will be separated from the base plate using any material removal technique such as wire cutting or a bandsaw machine. So this was about selective laser melting. Now both common to the selective laser melting and selective laser sintering, the basic phenomena is same. Let's try to understand that. Powder is loaded in the supply container and a laser unit is there which is throwing laser on a mirror which is moving at a very high speed. Now the movement of the mirror controls the reflection of the laser and thus the path of the laser on the powder bed. Now once the laser selectively melts powder particles for one layer data, the build platform moves down by one layer thickness, and the roller containing taking extra powder from the dispenser build fills that gap created using fresh powder. Now again the laser will start once the spread has been complete, and layer by layer the same process will be repeated until the process is complete. So selective laser sintering is basically used for thermoplastics like nylon, alumide, and the fundamental is same, that laser is the energy source and raw material powder particles of the thermoplastic material is the feedstock. And selective laser melting is exactly similar, but instead of photopolymers, we are using metal powders. And if I have to generate a part in a particular alloy, the powder of the same alloy will be used. And the laser, instead of sintering here, what they do is the laser energy is adjusted in such a way that it melts the powder particles and quickly solidify it. So what we get, the solid part that we get in 3D printing using selective laser melting is a solid metal part which has been obtained after melting. Now, if I, in selective laser melting, if I change the laser head uh, with an electron beam gun, then it becomes electron beam melting. The same process, melting process will be done layer by layer, it will be done, powder will be dispensed in the same way, but I have changed the laser source, so it is being called now electron beam melting. Now, what are the advantages of using powder bed fusion is that the part tolerances are very good as Vat photopolymerization that we learned in the last module. But however, the strength of the parts produced through powder bed fusion is usually better than photopolymerization, SLA. And the design complexity that we can achieve in powder bed fusion is the highest amongst all the additive manufacturing processes. The metal parts that we print using SLM, the mechanical parts are comparable to conventional components made using machining or casting. And the components that we make through powder bed fusion, whether it be in plastic or metal, they can be used for the fully functional end application. So they're not just prototypes, they can be used as end parts as well. And nowadays, the advantage of PBF is that there are multiple materials that can be printed through PBF in a single build. And the support structures that can be really optimized using the heat dissipation phenomena. So it is a very optimized and very most updated process in 3D printing. And the powder that we are using, it can again be recycled just like that for photopolymerization. So what are the disadvantages of powder bed fusion is that, again, since it's metal, the post processing requires wire cutting and heat treatment, so it becomes a costly affair. And raw material cost is also very high, approximately 10 to 20 times as compared to the conventional billets and blocks. And but since it is a powder based phenomena and the equipments that do this 3D printing, they are very sophisticated and are mostly used only at industry level scenario. Whereas Vat polymerization can also be used in a lab or in a uh, dentist medical facility or in a hospital. Whereas powder, because since metal powders, which are really harmful, it is that's why there are a lot of regulations involved, and they can only be used in industries. And the depending on the geometry of the part, the surface texture may vary because of the, again, powders being involved as raw materials. And there is a lot of issue with the parts when it comes to residual stresses and thermal distortions, since there's a thermal phenomena in metals and in polymers too. So if the thermal stresses are not managed properly, there are chances of distortions. And keeping all these in mind, let's just go through very quick introduction to the applications. So defense and medical are one of the early adopters of laser powder bed fusion technology. And low volumes, low batches of functional components are are manufactured using this technology. Then in the common industrial hardware industry, what laser powder bed fusion is being used for one of kind of machine parts. So designs which are required in very low numbers, which is not feasible to produce through casting or machining, can be made through uh, laser powder bed fusion. And then for regular manufacturing production processes where lakhs and millions and billions of components are required, there we can use 3D printing laser powder bed fusion, not to make the end component, but to manufacture the jigs, grips, and fixtures. And definitely, we can do a low volume production of small components where the batches is in from hundreds to thousands. Then a quick rapid prototyping can be done for very complex designs in metal and polymer both without actually investing in the tool or mold. So this is a very big advantage, and you can actually do functional testing on those prototypes. They cannot be only for ideation and visualization. And now this is one of those technologies which is heavily used for end production of low batch components. It is also used for architecture models, SLS to be precise, not metal, but SLS, polymer laser powder bed fusion is used for architectural model. So that was about laser powder bed fusion. Now we will pick up a next technology in the next module. See you then. Thank you. Now in this section of the second module, we will learn about binder jetting in detail. So as usual, let's get started with a video to understand how binder jetting works. And again, as you can see that powder particles are spread. Uh, in this case, there is a powder bed of nylon material that has been spread, and then there is a print head that comes and spreads binders only in the area where the part has to be cured. And then again, a curing head comes and it cures the particular binding material. Sorry, it cures the particular powder material which has been mixed with the binder already, and both of them under the action of the curing light, they become solid parts. Let's try to understand the same thing using this actual video. An actual video. A 3D CAD model has been loaded in the virtual build environment, and powder is now being fed in the machine. So powder has been loaded in the machine. The powder bed is being leveled, and a printhead comes and drops binders only in the area where the part has to be cured based on the CAD data that has been given to the machine. And then this is the UV curing that has cured the area where the binder was mixed with the powder bed, and rest of the remaining powder bed will remain as powder bed. But this particular area where the binder was mixed and it was cured using that laser light, sorry, using that UV light, that has become solid now. And rest of the powder that will be again extracted, and it can be reused, but the part, this is how the part will look like. So it's again a very simple process, just like powder bed fusion. The spreading of powder happens, but instead of melting it or sintering it using a laser source, a binder comes and binds the powder particles only in the selected area, and then a curing light comes in the form of a UV light, and then it cures that to make solid parts. And most of the polymers which are being used in this technology are nylon and metal also. Binder is being used for metal also. Now, what is the advantage of using binder jetting is uh, that the complexity and the capability to produce very fine resolution components is equivalent to powder bed fusion, but it is much faster and affordable than powder bed fusion. So it is a more affordable technology. And also the mechanical properties are very much better than compared to other techniques of 3D printing. So it's again a technology which can be used for manufacturing fully functional end components, and using binder jetting we can make components with multiple colors, just like you can have as many colors in a normal 2D printer. Similar way you can have as many colors as possible in binder jetting. and the raw material wastage is really less as compared to all the other additive manufacturing process, and it can easily be integrated with any of the foundering techniques which are traditionally or conventionally being used. And since the powder is not being melted, there is no thermal energy given by a laser or an electron gun. So there are no residual stresses when the part is being made, and the residual stresses are next to zero. So there are no challenges when it comes to distortion and delamination. But definitely there are some of the disadvantages as well. So let's try to understand the disadvantages now with related to binder jetting. Uh, Once the process is complete, you only get the green part. After that, there are certain post-processing techniques such as infiltration, sintering that needs to be performed on the part to get the right mechanical strength. And during this, before this post-processing is done, the part is really fragile, and there are chances of the part getting damaged during the post-processing stages. Even once the post-processing is done to ensure that the part attains good mechanical properties, the mechanical properties that we get here are not as good as powder bed fusion, both in metal and polymer. So it is a good technology, but it is the mechanical, for example, for binder jetting of metals, the maximum strength you can get is equivalent to sintering, which is lower than casting or melting. So this was about the disadvantages of binder jetting. Let's meet in the next module and explore one more technology in a similar fashion. Thank you. Welcome to the sixth section of second module. And in this module, we will learn about the FDM technique called as the 3D printing technique called as material extrusion. Material extrusion is popularly known as fused deposition modeling, FDM. So let's have a look at the video of fused deposition modeling, a material extrusion technique, and understand how it works. So raw material in the form of wire will be fed through this hot end extruder, a nozzle. This nozzle is heated at some temperature. It helps in melting the raw material and lay it around in a layer wise fashion. Even in a layer, it is only laid at areas where the 2D data has been given to the 3D printer, and the 2D data is nothing but the slicing data of the CAD model to be printed. Now, layer by layer, as soon as the one layer is complete, either the build platform moves down by one layer thickness or the extruder moves up by one layer thickness and starts printing the next layer. And once the final layer is done, when the part is completely 3D printed, then we can remove the base plate, remove the part, do a very basic set of post processing, and the part can be used. So it is usually used for polymers. When we call FDM, it is largely used for polymers, and a filament, a wire of that particular polymer of 1.2 mm dia, 0.4 mm dia, 0.6 mm dia, depending on the process parameter selected. The wire comes and is fed through a set of rollers to a temperature controlled nozzle, which is called as a hot end extruder, and it deposits material selectively for every layer, and the same things keeps repeating layer by layer. So one of the name is FDM, the other name is fused filament fabrication. Now in the fused filament fabrication, again the coil with filament will keep feeding material to the hot end extruder or the heated nozzle, and it will keep laying down material layer by layer. So it's a very simple process. It's a very fantastic process how by the application of very little amount of heat, parts can be converted from spool to the desired shape. That means the end component. Let's have a look at another video to understand this process. Now in this video, if you see, the software you will have a virtual build volume where you can create the parts in the build volume. Now, once you design the part, the part is converted to STL format, the CAD model. And then that STL can be opened in any build processor. In this case, the build processor or the slicer is Ultimaker, because the machine that they have used is of Ultimaker. And layer by layer, each uh, data is verified before starting printing. Now, this is the build base plate where the build platform will start. You will also see that some additional material is being printed. That additional material is called as support structures. Now, once the support structures and the part are printed layer by layer, they will be removed from the build plate and the supports will be removed from the part. So the support design is has been done in such a way that they are weak and they can be broken with hand tools easily. So you can see the time lapse video of the model, CAD model being printed. Now, once the part is printed, the support structures are being made after removing the part from the build platform. This is the removal of the support structures. So when we say support structures, they are necessary for printing, but they are not required in the part, so we have to remove them. So I hope this video makes it very clear, like how FDM works. Now, what are the advantages of material extrusion? That it is a very basic technology and it is very much affordable, even for hobbyists or school students or college students. Anyone can have this technology. The printer starts from 15-20,000 rupees to and goes up right up to 1 crore, 2 crores, the industrial level FDM printers. So it basically creates an entry point for anyone into the additive manufacturing industry. It's a low temperature process. As I told you, with very less amount of heat, we can actually get the desired shape of the components. It is a good process if you just have to print a single component and try and test it out for validation or something. Then the raw material is not very difficult to maintain. It is very easy to handle the raw material. It just comes in the wire form and it is available right from 500 rupees kg to 2000 rupees kg, 3000 rupees kg on Amazon as well. And the parts that you make do not need much post processing. But yes, not all the components or not all the machines can produce FDM components which can be used for fully functional use. So that is one disadvantage. Let's talk about the disadvantages. uh, Now, since the heating involved is less, that's why very limited options of polymers can be made using FDM. And it is a process which is basically made for less number of components. So there is no scalability when it comes to producing high volumes. The accuracy is not as good as powder bed fusion or binder jetting or vat polymerization. As I told you, this is an entry level process. So definitely you cannot have everything at the same time. And the component strength is not also as good as compared to the other additive manufacturing techniques. There are anisotropy in the parts which needs to be taken care of. Materials can sometimes be toxic, which is usually the case with all the 3D printing materials, and the parts may be subjected to warping and shrinkage. So we need to see in which scenario 3D printing such as material extrusion, FDM, FFF can be used or not. Now in construction nowadays, this material extrusion technique is being used a lot. Construction 3D printers are based on this technology itself, which can 3D print rooms, houses, architectural structures, or in fact a building of 2 to 3 floors can be built using 3D printing. Human tissues can be 3D printed using this particular FDM technology. And small prototypes can be printed very quickly. So imagine you are making a design and you just want to see how your design looks. There, material extrusion, FDM, makes a very good sense, both in terms of the realization time and realization cost. And also for the end process, we agree that there are limitations with respect to the mechanical strength, but at the same time, jigs and job holding devices can be 3D printed using FDM, because if the load bearing requirement is not very high, then this is a very good technology to produce the jigs, fixtures, which can be pre-printed after certain amount of time. So that was about fuse deposition modeling. We will meet in the next module to discover another such process called as DED. Thank you. Welcome to the last section of the second module, where we will be learning in detail about directed energy deposition, popularly known as DED. Now, you can clearly see in the image that there is a built platform on which metal wire is being melted and deposited uh, layer by layer. Now again, just like all the other 3D printing processes, the area where the metal wire has to be deposited, or metal powder particles, both can be used in DED, that particular area is defined by the 2D layer data generated after slicing of the 3D CAD model. So slowly it will, this process will keep repeating layer by layer, and the whole part is made in the Z direction. Now let's try to understand about DED. What are the different kinds of DED technologies available? How do they work? So the first one that we will talk about is laser metal deposition. So in this, basically, the feedstock that is used is powder particles, fine powder particles from 50 micron to 150 micron of size. And there is a laser head. From the laser head itself, the powder particles will be delivered, as well as the laser will be delivered for melting that powder particles and laying it out in a selected area. So wherever the nozzle moves, it drops some powder particles and it melts down those powder particles very quickly and solidifies it very rapidly. It is all done in the presence of a shielding gas which is of inert nature. Now, uh, in the same equipment, if we provide a electron gun instead of a laser head, then it will be called as electron beam additive manufacturing. But usually electron beam additive manufacturing is uh, carried out in vacuum, and it does not use wire, it does not use powder as the feedstock. Instead, it uses wire as the feedstock. So electron beam additive manufacturing is capable of producing really large components by melting wire metal uh, in wire form using the source from an electron gun. Another such technology which is very popular for large parts is called as VAM, wire arc additive manufacturing. So using a wire arc mechanism, which was used earlier in welding, which is still being used in welding, very popular. A wire is melted down using the arc technology, and then it will solidify in the form of solid bulk metal that we want to produce. So again, this is like FDM only, but the amount of heat that is being generated in the extruder or in the nozzle, that is basically equivalent or much more than the melting point of the alloy of metal. So this is all used for metal. When we talk about DED, it is specifically for metal. Let's watch a video for laser metal deposition, where a laser head is mounted on a rotary table, a 5-axis sort of arrangement, and as per the requirement of the program, the build plate will keep rotating and moving. The laser head here is stagnant, and it is continuously emitting powder particles, melting them down and solidifying it quickly in the area where the 2D data has been fed to the machine. So you can see the real time of this video. It is around 3 minutes, 4 minutes. Imagine how fast this process is. This is laser metal deposition. And when a feature at different angle has to be printed, then the build will tilt itself, build platform will tilt itself. So this is how our laser metal deposition works. Now let's have a look at electron beam additive manufacturing. How does this work? Electron beam additive manufacturing is typically used for even larger parts like 1 meter, 800 meters. The largest machines you will find in the industry will be of this technology, electron beam additive manufacturing. But at the same time, the features that we can produce through electron beam additive manufacturing will be much coarser than powder DED, because the wires that we are using, they are usually of big diameter like 1 meter, 1.2 meters. But yeah, for titanium and tantalum materials, this is a very preferred technique. But again, this has to happen in a vacuum environment. Unlike other DD techniques where they were happening in inert gas atmosphere, this happens in vacuum and it requires machining. Machining is mandatory. After producing the part, you need to machine it because the surface texture is very coarse, it's very bad, and you need to finish it off. And that finishing is done through machining. So this is a typical electron beam additive manufacturing where you can see two separate nozzles are being used for feeding wire, and the electron head is fixed separately. It is used a lot for aerospace components and other components. Now, the similar way wire arc additive works, let's have a look at the video how it works. So the basic principle is simple, only the wire arc torch is used instead of an electron gun or a laser head. It also uses wire as raw material and it slowly deposits layer after layer. Again, you will see, since we are using wire here, the feature sizes that are produced are very large, very big. So we need to machine these as well. But again, uh, both VAM and VAM and EBAM, electron beam additive manufacturing, are the technologies which are used to produce large parts, not fine features. When it's about fine features, we will prefer going to powder DD or laser powder bed fusion. So we learned about the processes. Now let's have a look at the advantages of DED. Now, since it's a nozzle-based method, which is very much similar to welding, what it can also be used for welding or repair purposes. So you can actually take an existing component, an old component, and start depositing material on it. Now, since it's more similar to welding, a conventionally established, well-established technique, there are lots of options when it comes to materials. So basically, what can be welded through wire arc can be done through wire arc additive manufacturing. So you have more options for materials. We can definitely make large components by 1 meter, 2 meter, that large components. And the properties that we achieve through this are really good because we are able to achieve fully dense metal components using directed energy deposition. The build time is really fast, the material wastage is minimum, and at the same time, in a single build, if we are able to accommodate multiple components based on the build volume where we are building, we can actually make multiple components at the time. So this technology offers multiple advantages, but definitely, just like other technologies, it has got some disadvantages. Let's try to understand that. The components uh, that can be made are big because the equipments that we use to make these components are big, and they are costly. Since they are big, they are costly. And if we compare to other additive manufacturing processes, only powder bed fusion equipments are relatively in the similar cost range. Otherwise, all the other equipments are available at a much lesser cost. For example, this kind of a machine can be available in the price range of 1 crore to 10 crores, 12 crores, 20 crores. Whereas FDM printers are available in 15,000, 60,000, 1 lakh rupees. Now, in this, support structures are very difficult to make because uh, the large liquid melt pool that we make during deposition of the material, it doesn't allow me for an overhang. So if I can move the build platform to create that overhang, it is okay. Otherwise, it is very difficult to generate that overhang because we cannot make support structures here. Also, the energy required to maintain the melting point of the alloy that we are dealing with, that we are processing, it results very high thermal gradients. So residual stresses are a problem in this technology as well. And after the parts are printed, as I told you, most of the cases like VAM and EBAM, electron beam additive manufacturing, post-process machining will be required, because if there is no post-process machining, the surface texture will be very bad. So you need to machine it out. But nevertheless, this technology is being used in a great way in the aerospace sector, in the oil and gas sector. You can see on your left hand side, there is a titanium mm, gas bottle which is used to store oxygen and other gases which in spacecrafts. Then you can see there is a rocket nozzle being manufactured for a spacecraft where we are able to reduce the thickness, but we can still maintain the strength using these rib-like structures which can easily be produced through DED. Then we have rocket nozzles here, again plain rocket nozzle walls with internal cooling channels which have been used for rocket engines, and they have been realized through DED. So some great examples and very large components are being made through DED. You can realize the scale of this component by comparing them with the people standing next to it. So that was about DED, and thank you so much for listening to the module 2, Introduction to Additive Manufacturing. I hope we are all very fairly clear now what is additive manufacturing and what are the different kinds of additive manufacturing processes. In the next modules, we will understand how to work about these processes and what are the exact applications that we are looking at. Thank you, and see you in the third module. Welcome to the third module of the course. And in this third module, we will focus on the applications of 3D printing in the strategic and core sectors. So the course content is going to look something like this. First, we will be talking about the strategic and core sectors which are actually using 3D printing at multiple levels, whether it be at prototype level or be at batch production level or other purposes. Then we will go into each of these strategic core sectors and talk about specific applications of 3D printing in these particular sectors. We will start with aerospace and defense. Then we will talk about applications in the automotive sector. Then we will jump to medical sector. And towards the end of the module, we will cover energy sector. So we will all try to understand why all these sectors are using 3D printing and what is so unique about all these case studies that we will be discussing. So first, let's start with the defining those particular strategic and core sectors of the manufacturing industry where 3D printing has been adopted at a faster rate when compared to the other strategic and core sectors. So what are these uh, sectors that we are talking about, the so-called strategic and core sectors? The first one is aerospace. Now, in aerospace, there are multiple reasons why additive manufacturing is being used, but the primary one is lightweighting. Basically, aerospace always prefers a lightweight design, keeping the factor of safety of the part maintained. If we can provide them with an option to lightweight the components but having the same stiffness, then that is the best kind of solution for aerospace, and additive manufacturing promises that for aerospace industry. Now, apart from this, aerospace aero engines where the hot section is there and the temperatures can go up to 3000 degrees Celsius, those particular areas also require some components made of specific alloys, and it is easier to manufacture such alloys through additive manufacturing. Then when we talk about polymer, there are a lot of spare parts management that happens in the aerospace sector using both polymer and metal 3D printing. Then the next sector is healthcare. Now, healthcare is uh, the primary reason why healthcare is using additive manufacturing is the turnaround time, because time is a very critical factor in the healthcare industry, and thus the healthcare industry uses additive manufacturing for manufacturing surgical tools, which helps them in the surgeries, and to manufacture actual implants which go inside the human bodies, and then prosthetics, medical equipments. There are multiple components of medical equipments which are better if we produce through additive manufacturing. Depends from one case to another. Now, automotive is primarily using right now additive manufacturing for prototyping, because at the mass production level, the volume of automotive components are so high that it doesn't suit them uh, when it comes to the cost and time both. But at prototyping level, since the quantity required is very low, comparatively very low, in 10 to 100 numbers might be required only. At that time, automotive prefers using additive manufacturing because of the uh, quick turnaround time. Then customization, you can do a lot of customization on your cars. We will discuss a few case studies related to that also. Now, one interesting thing is that automotive also values weight reduction a lot. That's why for weight reduction, additive manufacturing is being used in automotive as well. Then die mold sector. Now, when you have to make number of components like 1 lakh components, 2 lakh components, then you cannot make the end part through 3D printing because the volume is not suitable. Hence, you try to add the benefits of 3D printing by manufacturing the die and molds which will make the end components. Those die and molds are made through 3D printing. Then we have general engineering. Now, general engineering is a very wide arena, but for example, any SPM you required, any machinery you require, that comes under general engineering. And then your normal engineering works basically. And in this regard, whenever you have to create a prototype, additive manufacturing is definitely the best solution. Then function integration, combining multiple parts together and achieving multiple functions from the same part, and how it is done that we will see in the case studies. Then spare parts management. Now, there are certain general engineering areas where the quantity is very less and it is basically depending on the demand. For example, SPMs. So if we are catering to that area, additive manufacturing can help in maintaining a digital library and producing components on demand. Then, uh, last but not the least, energy sector. Now, what energy sector, where energy sector allows us to incorporate additive manufacturing is largely spare parts management, because the spare parts requirement for the energy sector is quite high, and it involves enormous amounts of budgets. So having localized solutions through which you can produce the spare parts on demand whenever required helps the energy sector a lot. And one more reason, that downtime is very critical for energy sector. They cannot afford downtime. We will discuss these things about downtime and all. Yeah. So that was about the strategic and core sectors using additive manufacturing and why. Now we will deep dive into each one of them and their applications and try to understand from one case to another the benefits of additive manufacturing in the upcoming sections of this module. Thank you. Welcome back, and let's start with the applications of additive manufacturing in the aerospace industry. So you can see the image on your screen, right? Now, this particular image is of Boeing 737 MAX, which is a very popular aircraft. with most of the domestic airlines. Now, one more flight, which is yet another common flight like aircraft like Boeing 737 MAX, Airbus 320 Neo. Now, Airbus 320 Neo is a very common flight for people who are traveling in Indigo. It's like hundreds of Airbus 320s are there in India, similar to Boeing 737 MAX. Now, these flights are using a LEAP engine. Both Airbus 320 Neo and Boeing 737 MAX are using a LEAP engine that is from GE, basically a joint venture of GE called as LEAP engine, which is one of the most fastest uh, jet engines made by GE. Basically, this engine is made by an organization called as CFM, and these are popular as CFM LEAP engines or GE LEAP engines. CFM is a collaboration between Safran and GE. Now, this particular fuel nozzle that you see here, around 20 of them goes into the aircraft in one engine. So if there are two engines in the aircraft, usually there are two engines in Boeing 737 MAX and Airbus 320 Neo. Uh, per engine, 20 components, per aircraft, 40 components. And this is a fuel nozzle basically. Now, this component is made through metal additive manufacturing, metal 3D printing. And recently, GE has rolled out its 1 lakh number component, uh, and like it is a huge success in the area of series production for aerospace through additive manufacturing. Now, I will just quickly, uh, in order to explain the importance of this component, I will take you through this quick GIF image where you can see that wherever the blue area is there, till that time, the cold air is coming, compressed air is coming. And after the combustion, the color of the air is changing. So what is happening here is that the component that I was showing you, that particular component is injecting fuel at that particular area and combustion is starting. That's why the color is changing. Now, when we talk about this LEAP engine, there are 20 such fuel injectors, fuel nozzles. Now, this particular component, conventionally, it was made of 20 different components, and using additive manufacturing, GE was able to make it as a single component. So there is a tremendous benefit both in terms of inventory and technical advantage because the part is not an assembly anymore, so it is more consolidated. It is more reliable. Then this CAD model that you see, this is for the nozzle of a rocket engine for a launch vehicle, space launch vehicle. Now, this particular nozzle, if you see at the cross section, there are thin channels in between of these thin walls. There are thin channels for the fuel to flow because these nozzles where they operate in the engine, the temperature goes up to 3000 degrees Celsius. And if we want to make sure that the materials don't degrade over there, we need to make sure that there is active cooling of these thin wall structures. And that cooling is achieved by passing the propellant itself, the fuel itself, because the fuel is at a much lower temperature. It carries away some heat from the walls of the nozzle, and then it allows these nozzles to operate without any deformation or without any functional degradation at such high temperatures. This is the actual 3D printed part, what you are seeing on your screen. Now, this was made in SS316L material. This was made in Inconel 718 material. And Inconel 718 material has a very good property that it does not lose its mechanical properties till 0.85 times of its melting temperature. So that's why it is heavily used in the aerospace industry. Then there are structural brackets where through additive manufacturing we can achieve very lightweight brackets, and they have got, as I told you, that weight reduction has got a very special treatment in the aerospace industry where they want to reduce weight as much as possible. So 3D printing coupled with technologies like topology optimization, this particular part was designed using topology optimization and printed by 3D systems through laser powder bed fusion 3D printing in titanium material. This is basically a component for mounting of a satellite component on the satellite. And since it is going to space, and in space every gram counts, and but at the same time there is a very high cost of the projects involved in space industry, so you don't want to have any failures there. So that is the reason why stiffness or strength is also important. So topology optimization and 3D printing allows the aerospace industry to couple both these attributes, strength as well as with lightweighting. So again, this was a titanium component. So all these case studies in aerospace industry, you saw that basically most of them are being used for lightweighting, then for thermal management, heat management. So, but the overall idea is to create complex designs so that you can extract more performance and reduce weight. So the funda is very simple. You have to increase the power generation and you have to reduce the weight. And that is where additive manufacturing plays a crucial role. That was clear to these three case studies. So thank you, and see you in the next series of applications for the next strategic and core sector. So now let's start learning about some of the interesting applications of 3D printing in the healthcare sector. And 3D printing is used in the healthcare sector for multiple reasons, but the primary reason is to make the surgeries more effective. So most of the methods that we will see, we will find out that all of them directly or indirectly aid in making a surgery more effective. So what you see on your screen is a polyjet model. Now polyjet is something similar to a uh, resin and laser based 3D printing method. And this particular model has been created from the actual CT scan data of the patient who has to be treated. Now, what is the advantage of doing this is that the surgeons are able to plan for the procedure, the surgery that they are going to do, the procedures. They can plan much in advance, and thus they end up saving a lot of time that is otherwise gone in decision making during the surgery. So this is a very big advantage. This is a hard, what is this? Yeah, this is a general, this is basically your veins and arteries has been shown in different colors, and this particular model, it will help the surgeons in uh, planning the surgery. Then what you see on the right hand side of the screen is the 3D printed model of a heart. Now it also has the disease or the defect which has occurred due to the disease, that also is incorporated in this heart, because this heart is again been designed using the CT scan data and then been 3D printed. Then 3D printing is being used in medical for making surgical guides. Now, if you look at this maxofacial area, so maxofacial is anything related to your lower jaw and upper jaw. So when there is a surgery and you have to repair damaged areas of in your maxofacial areas, so these surgical guides helps in locating the screw accurately. So you don't have to, the surgeons don't have to go through conventional technique to locate the area where the screw has to be uh, done. And these surgical guides make the job really easy and very quick. And that is easy for the doctor and the patient going under surgery both. Then similar surgical guides are here, but this is for dental screws. So when you have to put dental implants using screws or other things, then the surgical guides help in locating them exactly where it should be. And again, all these surgical guides are made per patient. So these are patient specific surgical guides. Yeah, so the surgical guides aiding in safe and efficient implant placement. Then we have the actual implants. So now whatever we discuss the surgical guides, anatomy model, that is not actually going inside the patient. The but the implants are going to be inside the patient, and the implants are therefore made of biocompatible materials. For example, the metal implants are made of titanium and SS316L because these two materials are biocompatible materials. Now, what advantage 3D printing gives here is that these implants can be customized as per the CT scan data of each and every patient, and the repair to the maxillofacial areas. All you see right now are the maxillofacial areas where the implants are being used to join the damaged areas, the broken areas of the maxillofacial uh, features. So these are called as maxillofacial implants. Then in implants category, we have something called a cranial implant. So wherever you have a defect in the skull bone where it's gone damaged, so that area is replaced by a titanium cranial implant, which will have nearly same density, same kind of thickness as compared to the skull. It's a these designs are highly engineered designs for each and every specific patient. And again, because of this specific patient factor, 3D printing plays a very important role in manufacturing of these implants. So another example of cranial implant, how cranial implants look like, where they go. Then uh, another used case of implants is these are spinal cages. So these are very small components. To give you the idea of the size of these components, you can have a look at the image. It has been compared with the fingertips, so it fits on your fingertip. It is that small. Now, where this component goes? So this is a human vertebrae, and in the vertebrae, in between two vertebral bone, there are these spacers, natural spaces which are inside human body. But when these spaces worn out due to some ailment, then these are replaced by these titanium spacers. Now again, why 3D printing? Because it can be customized for each and every patient, and in the same build, in the same at no added cost, you can manufacture multiple number of this in multiple variants and multiple designs. So that is the advantage of using 3D printing for these implants customization, patient specific customization. These are called as spinal cages, spacers basically for the vertebral bones. So thank you. That was about the applications in the medical sector. Now in the next section of this module, we will learn about another strategic and core sector applications. Yeah, so let's start learning about the applications of 3D printing in the automotive industry. Now, automotive industry is also a kind of early adopter for 3D printing, but mostly for prototyping applications. So now there are some cases of series productions in the automotive industry, but they are associated with high-end automotive, not with the general mass automotive industry that is the major source of revenue for the automotive. So prototyping may basically what happens is that what you see on your screen is the 3D printed model of a V8 engine. Now this is a scaled down model of a V8 engine produced through fused deposition modeling, because it is a very cost-effective method of 3D printing, fused deposition modeling. And the idea in this case is just to evaluate how the design looks like. So the designer can have a physical feedback. Okay, my design looks like this. This is where I should change it, or these are the modifications I must do in order to make the component more serviceable or any other factor. So once 3D printing helps you at the prototyping stage, in the ideation stage, where you can make low cost prototypes for ideation and visualization, just to visualize your idea. But after that, you can in fact use metal 3D printing. What you see on your right hand side of the screen is a metal 3D printed model of a V8 engine. Now, this metal 3D printed part has got properties equivalent to the actual component which will be made at the production stage through die casting or any other method. So this part can be used for a fully functional testing of the component. So both are being used at a prototype level, one at the early stage, but the second one at the end stage of the prototyping level, where you want to fully functionally test your design. So you will use this component, mount it on the test rig, and keep running it as per the regulatory or desired number of hours. But in automotive also, as I told you, now the 3D printing technology is not only limited to prototyping area, it has also moved to series production. This is one of the examples for that. This particular component is again a topology optimized component, but a very popular car you might have heard about, uh, or definitely automotive lovers would have heard about that car. This is a metal 3D printed bracket that is used in a BMW i8 Roadster. Now, where is it used in BMW i8 Roadster? When you have your back hood of the car. So this is the bracket on which the hinge of the or the pneumatics of the hood is mounted, which allows the movement of the hood. So this component has been redesigned using topology optimization for 40% lightweighting and 10 times more stiffer, because earlier with much more weight the same component was being made in ABS material, but with 3D printing redesigning we are able to use the good benefits of aluminium and produce this component in aluminium 3D print. So this is a very interesting case study because it is a car that we all know. So it is going on a BMW i Roadster. So actually 3D printing applications, people talk about them, they talk 3D printing is a thing of future, but this is happening, this is in the present. Then another example of series production is this Eco Series engine, Eco Boost engine from Ford. Now, this goes on to another very popular car that you must have heard about. But before telling you that, I would like to talk about this component. Now, this component has been redesigned for additive manufacturing. You can see these lattice structures in these components in between the walls. These lattice structures can only be manufactured through 3D printing. In this case, metal 3D printing to be precise. This is an aluminium component made through laser powder bed fusion, which is a metal 3D printing technique that we have learned in the earlier modules. Now, through this design, the designer was able to enhance the performance of the engine, and this engine goes into the Ford Shelby GT500, which is a very popular car. So all these case studies that we are talking about, these are not from any other universe. They are all from the known around world, which is around us. And if we explore more, deep dive more into the applications of 3D printing on the net, we will be able to find many more such case studies. So due to shortage of the time, I can only talk about few. So I have picked up one or two good case studies from each area. So now let's talk about a case study for customization. So you can see this is the panel for your front dashboard. which has been 3D printed as per the customized design given by the customer. So these are the advantages. You can have your names on the components of your car. You can have the backlight of your car, the cover of the tail light, uh, redesigned, reprinted. 3D printing is now available in uh, acrylic materials as well, so you can get that done anytime. You can have customized steering wheels, customized brake pedals. A lot of customization can go onto the 3D printing, but the customizations which affect the performance of the car, that should be done taking help or under the guidance of a professional designer, automotive designer. So great scope for customized car interiors using 3D printing. Then we have jigs and fixtures, which are used in the automotive industry. So automotive industry manufactures jigs and fixtures using 3D printing because it is easier to manufacture, and jigs and fixtures can be made lighter, and uh, since if they will be lighter, it will be easier to use them, because jigs and fixtures are something that either a robot, a cobot, or a human being is uh, going to handle it. So this what you see on your screen are the jigs and fixtures manufactured by Ford. So jigs and fixtures all not only help in assembly, but they also help in uh, inspection of the manufactured component. So the image that you see on your right hand side is someone is holding a vacuum injection molded component in his hand. But below that, what you see is a 3D printing fixture in stereolithography, SLA technology. Now, this part is pushed inside the check fixture. The 3D printed part is called check fixture because it will be used to check the dimensions of the injection molded component. So it makes things really quick. Now, this component, people, if they manufacture in through other techniques, it's very heavy and it takes a lot of time in development of the fixture itself. So 3D printed check fixtures are a perfect way to go for doing inspection quickly and with very less development time of fixtures. So we covered all the most of the automotive varieties of 3D printing applications, and I hope there is a lot of more understanding now that where all in automotive 3D printing can be used. And in the coming sections or modules, we will learn more in detail about these applications via different strategies such as design for additive manufacturing. So thank you and see you in the last section of this module. Welcome to the last section of the third module, which is about applications. And in this last section, we will talk about the applications in the energy sector. By now, we have covered almost all the strategic and core sectors, most of the strategic and core sectors. So now let's get started with the energy sector. So what are the potential use cases or where it is being used actually in the energy sector? And first, we will talk about oil and gas. So oil and gas has a very specific way of using 3D printing for the spare parts management. Because if we talk about oil and gas, where there are oil rigs and there are oil pipelines, there the downtime is very important for them, because if the pipeline or the oil rigs are down for certain number of hours, they can suffer the loss in millions. So that's why what they want is they want quick replacement of the spare parts, and 3D printing helps them in doing that. This impeller that you see, this is a 3D printed impeller, and the time taken to realize these impellers is very less, because if we have to make these impellers through conventional route, these impellers are made through casting, the 3D impellers for oil and gas industry, and casting tool development itself takes around 10 to 12 weeks. And if we talk about the impeller on the right hand side, then we will see that this particular impeller is again a similar SS316 impeller, which has been developed through 3D printing, but only in 2 weeks. So this is the advantage of making spare parts through 3D printing, that you get it when it is required and you get it as soon as it is required. So now let's talk about the application of 3D printing in the nuclear energy field. Now, there are multiple applications being explored in the nuclear energy sector, such as making the fuel cell rods, making the nuclear cores for nuclear fusion fission reaction. Uh, However, I could only pull one of the examples which was put up by Oak Ridge National University, USA, because most of these studies that are going on, they are confidential and open data is not available. But this one has been published as a research paper, and so this is the component what you see where the Oak Ridge National Laboratory is written. This is the actual component. This is a nuclear core reactor. But this what you see, this is just a representation that has been only printed to some height from the base to make you realize like how complex the internal structure is. So now these kind of internal structures can only be manufactured through conventional by combining multiple manufacturing techniques and by manufacturing multiple components first individually, then joining them together by brazing or welding. Whereas in 3D printing, design complexity comes at no extra cost, as we have seen in the earlier modules. And this is the perfect example for that, how a highly efficient design can be uh, manufactured with the lowest possible challenges using additive manufacturing. Now, what you see on the right hand side is the uh, 3D printing process being thermally imaged uh, to detect the defects. So, since it is nuclear science and it is very critical when it comes to engineering, so that is why the utmost amount of care is given for in situ quality inspection. So what you are seeing on your right hand side is a X-ray imaging happening in situ when the process is going on, and this part is being made through laser DED process, directed energy deposition, where the laser head is providing powder particles and melting it at the same time and laying it as per the CAD model. That also we have learned earlier. Now, another method of energy generation is gas turbine. So gas turbine is another sector where 3D printing is very popular, and the reasons are partly similar to aerospace. So whatever reasons are suitable for the aero engine industry to use 3D printing, similar reasons are suitable here, because these blades can be manufactured with very good cooling channels using 3D printing, which is not possible otherwise using other conventional process, not even through casting. We can really make very fine, intricate features inside these blade structures, which work as a cooling channel when the blade is operating. Now, these blades are operating uh, over 1600 kilometer per hour at an RPM of 1600 kilometer per hour, speed of 1600 kilometer per hour, and are able to withstand 1250 1250 degree 1250 degrees Celsius of heat. Not only that, the parts are going rapid cooling at 400 degrees Celsius because of the atmospheric conditions, and thus they need to be really strong when it comes to the mechanical properties. And with 3D printing we can achieve that. We can alter the mechanical properties for your end application, your end requirement. So this is about the manufacturing of gas turbine blades using 3D printing. One more example of blades only of gas turbines is the repair application. So what you see here is that a good condition blade is taken and CAD model is prepared after 3D scanning of that. Then a worn out blade is taken, and using the details of the good blade, the worn out area is deposited via robotic arm 3D printer. So basically material is being deposited using 3D printing process, and after that one small cut of machining you can give and the blade will be ready to use. So this application is making DED, directed energy deposition, the 3D printing technique that we learned earlier, very popular to manufacture turbine blades out of steel, out of Inconel material, out of titanium material. So now you need not throw these worn out blades. You can use the worn out blades also after repair. So this is the advantage that additive manufacturing brings on to the table for gas turbine industry. So we have covered a wide variety of applications in this module, and in the next module we will start learning new things about additive manufacturing. And I request all of you to kindly go and explore further in your surrounding, in your area, in your company, in your college, in your school, how 3D printing is being used and in what manner it is adding value to the process of manufacturing or to the performance of the component. Thank you. See you again. Welcome back to the course Role of 3D Printing in Industry 4.0. And now we are at module 4, and we will be studying about the pre-processing of CAD data which is required in order to 3D print an object. Now, since 3D printing is a digital manufacturing technique, hence digital data, which is the CAD data, 3D design data, that becomes a very critical aspect. Hence, this module is also very important. So in this module, we will be talking about the basic process flow of 3D printing, because in order to understand how, how data is being processed at the various stages, first we need to understand that what are the various stages. Then we'll be talking about, in the next section of the module, the various type of input file formats which is used for 3D printing. What is the CAD data format which is used for 3D printing? And then, of course, the most important part of the data processing is orientation and support generation, because without the right orientation and support generation, it might lead to build crashes. Then we will talk about slicing and job preparation. Why do we need to slice, and how do we slice the files? And then what do we mean by job preparation? Also, we will talk about the commercial platforms where you can actually perform all this processing. So let's get started with the first section, which is the 3D printing workflow. Now, in a 3D printing workflow, you can call it a workflow or a process flow. Uh, we basically start with a 3D CAD model. Now, this 3D CAD model is something that you design in a 3D CAD modeling software platforms such as SolidWorks, Rhino, Creo. Then you convert that data to an STL file. So in the next few slides, I will tell you what is an STL file. But in general, STL file is the most popular file format used as an input file for all the 3D printing softwares. Then that STL file is sliced, and sliced data is produced. Now this sliced data is an input for the job file that you have to make. Now up till slicing, up till CAD model STL file slicing, the process flow remains same for all the 3D printing methods, whether it be laser powder bed fusion, or whether it be selective laser sintering, whether it be FDM, fused deposition modeling, or any other process that we have learned in the previous sections or previous modules of this course. But once I have the sliced data, that sliced data will be used to prepare a job file. Now, this job file is usually unique to each kind of additive manufacturing technique. For example, if you are making a job file for fused deposition modeling, then the job file will consist of G codes which will tell the printer that print nozzle head of the FDM printer, which is depositing the material, to move at what speed and what would be the feed rate. and other things like what will be the build platform temperature. Whereas if we talk about laser powder bed fusion, then in laser powder bed fusion, the job file will consist of information such as what should be the laser path in form of vectors, then what should be the laser power, how far one laser vector should be from each other, that is called the hatch distance. So in a similar fashion, the job file contains specific data required for that kind of 3D printing, basically required by that particular machine of 3D printing. So this job file becomes the input for any 3D printing machine. Then what the 3D printing machine produces is the finished 3D printed objects. Now, sometimes, or not sometimes, in most of the cases actually, this final object will be required to go through some post processing. That also we will try to understand why do we need post processing and how post processing varies based on different methods of 3D printing. So yeah, as I told you, uh, in the upper section from CAD to STL to slice data, it is same process flow for all the 3D printing methods. After that, it is changing, the process flow changes uh, based on the type of 3D printing process you are using. Then let's try to understand each and every step of this process flow so that we can understand what is happening in each and every step here. So modeling is nothing new. Even before 3D printing was introduced, 3D modeling is being used at a very large scale for any engineering operation right now, machining, quality. So basically, 3D modeling is referring to your generation of a 3D CAD model because that is the input required for any kind of 3D printing software. Now, once you have this, sorry, yeah. So cut. Yeah. So this software may you can start modeling from scratch. If you have to make a new product, then you can start modeling from scratch and you can make a new design. You can develop very intricate features since you are doing it, since you are manufacturing it via 3D printing. Or you can, if you want to replicate a physical object, then you have to do 3D scanning of that particular object and generate the CAD model by reverse engineering, and then you have to use that for printing, an input for printing. Or you can use the CAD data which is available somewhere else. There are some cloud uh, websites, where cloud libraries, some websites where this CAD models are available for 3D printing, such as Thingiverse or grabcad.com. Now, the model that you have obtained, whether it be by any of the discussed methods, now this model is required as an input, uh, and it is required in a particular format which is accepted by the 3D printer, and that is where this all processing comes into picture. Now this model will undergo a series of operations, series of processing, and it will be converted to an STL file first. Now once we create an STL file, what is an STL file basically is, it is a the surface geometry data. So whether you make a solid modeling file in SolidWorks or any other platform, or you make a surface data file, once you create an STL file, only the surface data will be remaining, everything will be gone. So once this surface data is remaining, because this is a surface data which is required to, which is required by the 3D printing software to start slicing, and this STL file only will be used to further to generate the G codes or the job file basically. Now, when we convert this STL file, there are multiple factors such as what is the feature size, or how big is the file, how heavy is the file. Now, all these things are decided by a feature called as tessellation. Now, tessellation is nothing but dividing the surfaces of any geometry into small geometrical elements. In this case, in the case of an STL file, this geometrical element is a triangle. So you can see on your right hand side, rightmost side, that the more number of triangles means high resolution file. less number of triangles, further less resolution, and in the left hand side is the least triangle, which is very poor resolution, or you can say coarse tessellation. Now, once you have the tessellated file, you orient it in a software, generate supports, and then the time is for slicing. Now, slicing is the process of transforming an STL file into G code. G code in terms of FDM process, or any other job file which is required by that particular process machine. Now, G code contains all the commands that it needs to give to the printer. And now that command will be based on the geometry of the file. Now, slicing performs the job of providing that information related to the geometry of the file to the G code, because it has been generated by slicing of the STL file. So now the printer will follow exact the same path based on the sliced data, and it is one of the major informations that the G code or any job file carries. Now, many 3D printer manufacturers, they tell you to use their specific slicing softwares, and there are many manufacturers who have made these softwares open source. For FDM, most of the softwares you will find online, which are open source, whereas for others there are less number of open source softwares, and most of the softwares are OEM controlled softwares. So once all this job file is done, then it is given to the 3D printer. The 3D printer starts processing once the command is given to it, and the result is the final part. Now, the only thing that you need to take care is during 3D printing is like setting the printer right and feeding good enough amount of raw material. In this case, what you see on your screen is an FDM printer where the parts have been finished, and in this case, the raw material is a filament, as we have discussed in the previous module. So yeah, that was about 3D printing. And once the parts are printed, they need to be post-processed. Now, this post-processing is a very broad term. In post-processing, you can also do post-processing. That means some activities to improve the finish of the part, or to improve the mechanical strength, or to improve the accuracy of certain features which you want to use for assembly or for other purposes. So basically, the operations that you are doing after printing of the part to make it more suitable for the end application, that is called as post-processing. So that was about all the complete process flow of 3D printing. In the next section of the module, we will start learning about the different data formats involved in this process flow. Thank you. Welcome to the second section of the fourth module. In this section, we will learn about the various input file formats which you need to use for 3D printing. So basically, when you have designed your CAD model, every CAD modeling software will have its parent format and plus some generic formats. Now, out of those generic formats, we will learn about those particular generic formats which are accepted by the 3D printing softwares. So the first format is the most popular one, which is an STL file, which I have discussed about in the basic process flow as well. Now, this STL file in 99% of the cases will work. Only it will not work in the cases where you want to do color 3D printing, that I will explain you okay, what format to use in at that stage. But STL is basically stands for stereolithography. It was the format used for stereolithography, and a .stl file consists of basically tessellated data. Now, I had shown one image of tessellated data. We will understand in this module as well, okay, what do we mean by tessellated data. And in 99% of the cases, this is the standard file format, which is works as an interface between the CAD modeling softwares and 3D printers, because all the CAD modeling softwares will have an export option for .stl, and all the 3D printers will accept the .stl file. Now, one limitation with .stl is that it is only surface geometry and it only carries the surface data. in form of the triangular elements to represent the 3D geometry, but it does not contain the data of color. It is a single color file. So if you want to print an object, 3D print an object with 2, 3 different colors, which can be done in multi-jet fusion or DLP technology. In fact, in FDM, there are dual extruder available. Then you need to use a format which also contains the data of color, not just the surface geometry data or the 3D dimensional point cloud data. Now, in STL, tessellation is very important. Few people also believe that STL stands for Standard Tessellated Language. Now, tessellation is nothing but dividing any surface into smaller number of elements. Into smaller elements, more number of elements. For example, if you look at this wall, it can be a single structure of wall, but when you use tiles on the wall, it you can call it as tessellation of the wall. So tessellation of the wall is happening using tiles in this particular case. Whereas when we talk about our STL file, then the tessellation always has to happen in triangular shape. So the tessellation element has to be triangle always. So now, for example, what you see here, where you can see one tessellation where this element is having 4 nodes. One second. Yeah. So this element is having 4 nodes. Now, this is not a right element because any triangular element will have 3 nodes, and that is the right way of tessellation. So these things are taken care by the software while generating the STL file. We are just discussing it for our deeper understanding what the software is doing behind the scenes. Then another format is the .obj format. Now .obj format is the second most common file format used after STL files in 3D printing. In a .obj format, just similar to STL file, only surface data is there. Now it is widely supported by a large number of 3D printers, including Formlabs, who do resin-based 3D printing. And there are almost all the software, again, just like STL, which have the capability to export .obj file. Now, as I told you, in this case also, it will only represent the surface data, not the color. But let's try to understand that both in OBJ and in STL, how the surface data is basically uh, uh, annotated, or how the codes are written to represent that surface data. Now, I told you that the tessellation element is always triangle. Now, in this triangle, it will have node 1, node 2, node 3. Now, each one of the nodes will have their own x, y, z coordinates. And in order to define the normal of this particular STL triangle, this triangle, if we have to define the normal, we have to use the right hand thumb rule. So if you want your normal to be facing outside, you have to name you have to give the nomenclature of the triangle in such a way that the vertices, the coordinate points of the uh, vertex 1 comes first, then second, and then third. So you are curling your hand from 1 to third to 3 because your thumb should be in up direction. This is called as the right hand thumb rule. So this is how you define a triangle, and a collection of such triangles covering all the surfaces of a CAD file results into an STL file or an .obj file. Now another format is .vrml. Now VRML is a virtual reality modeling language, and it is very newer type as compared to STL and OBJ. The advantage with .vrml, which is also known as VRML, the file extension is also used as .wrl in many softwares. And the advantage here is that it can hold single UV color map. So that if you are printing any component with more than one colors in it, then you can use this particular format. Now, this format is not as widely accepted as STL, but definitely in future it is going to be very popular as colored 3D printing picks up on the way. So Cura is a software which is an open source software used for FDM 3D printing and other few methods. And Cura accepts VMRL. It supports VMRL format, but not all the program supports VRML format. Now, one more format is .3mf. .3mf is a file format created by Microsoft itself because Microsoft wanted to develop certain features in Windows 10 operating system where you can do 3D printing without using any other software in between. You can directly connect your Microsoft 10 system to a 3D printer and you can start 3D printing, which is still a work in progress. And there are some printers compatible with Microsoft directly as well. Now in .3mf, uh, not just color or surface data is contained. Apart from the color and the surface data, the material information, the textures, if there are meshes, they will also be replicated. So a wide variety of information can be contained in a .3mf file. So it is a very, very good file for 3D printing, especially when it comes to industrial sectors. And it is an open source software. It is there available with any Windows 10 operating system after any operating system later than Windows 10. And you can use it to connect to the basic 3D printers. .amf is another file format, which is an XML based open standard printing format. So this does not contain as many informations as .3mf, but it contains the color information. The file format supports for color. And the advantage of this file is that it can be compressed to very minimum size, file size. STL, the problem with STL file is that the data, surface data is, when it is huge, the file size also is huge. So with huge file size, .amf gives an advantage that it can be compressed to a smaller size. And it contains data about object, material, texture, consolidation, the metadata information. Again, just like .3mf, .amf is not that widely used, but as compared to .amf, .3mf is slightly more used in the industry. But very soon .amf is going to be popular because it has got material data, texture data, and multiple kinds of data, which is also being supported by the new age 3D printers. So thank you and see you in the next section of the module. So welcome to the third section of the fourth module. And in this section, we will learn about the orientation. What is the significance of orientation and support generation in metal 3D printing, and how they differ from one technology to another. So in this module, uh, let's start with the very basics of orientation and support generation. That why do we need to talk about orientation? Why is orientation so important? Uh, so basically, a part can have multiple effects. Sorry, an orientation can have multiple effects on the part that is being produced through any particular technology, whether it be FDM, whether it be metal 3D printing technology. The first one is printing time. So depending on the orientation, the printing time can vary for the same part. You have to manufacture a component. Now, if you change the orientation, the volume of the part is not going to change, but still, depending on the orientation, the printing time might change. And then your geometrical and dimensional accuracies also depend on the orientation. What feature has been aligned in what particular orientation, on that the particular features, dimensional and geometrical accuracy will be dependent. Then also the mechanical strength, because in most of the 3D printing processes, the mechanical strength is anisotropic in nature. That means in the layer wise, since the printing is happening in layer wise fashion, so across the z axis the strength will be less, whereas across the xy the strength will be more. Now, on your orientation, your design of support structures will depend, because your part orientation will decide that which features are under an overhang and they need to be supported. Also, the surface roughness depends on orientation. So any vertically aligned feature or any vertically aligned wall in the direction of printing will have the best surface finish. And when we change the angle of that vertical wall or any other feature which is at a different angle, then you end up having a different kind of surface finish. So surface finish is also dependent. Now all this that I just told you can be seen in these two parts, what you see here. One of the part has been printed vertically and one of the parts has been printed in a horizontal fashion. You can see since the printing is done in a layer wise fashion, there are evidences of this layer wise manufacturing on the surface of the component produced. So in the case of the vertical printed component, that effect is aligned in the Z direction, whereas in the other component it is in a perpendicular direction because the printing has been done in perpendicular direction. So all these things we need to understand, and we will now see that how the mechanical strength varies in the based on the orientation. So when you do FDM 3D printing, this particular slide is specifically for FDM 3D printing. In other technologies, the difference in X, Y, and Z is not that much, but in FDM, the difference is very high. So what you see is that when you apply this, you can see that the part has been printed in the vertical direction based on the marks of printing layer based on the evidence of the layer wise manufacturing method. You can see that the printing direction has been this particular direction. Now if you apply load in the normal direction to the printing direction, then the part will be weaker. Whereas if you apply load in the perpendicular direction to the printing direction, then the part is stronger. So in this manner, the strength depends on the orientation in which you have printed the part. Also, now let's take an example where building the part in that same Z direction. Most of the cases building will happen in the Z direction, either plus Z or minus Z. Then what we need to understand is that based on keeping in mind the printing direction, what has been shown here, all these features needs to be checked whether support has to be added or not. Now, if you're looking at holes, then any hole which is having dia more than 6 mm or 5 mm, it needs to be supported. Otherwise, what will happen that this surface finish will not come good and sometimes it might bulge down also. So it needs to be supported. Any hole larger than 5-6 mm needs to be supported via a support structure which will be removed after 3D printing. Now in some cases like in metal 3D printing, it is not very easy to remove the supports. So in those cases we can go to make a teardrop shape if the hole is circularity of the hole is not functionally important. So you either need to support that overhang with a support, or you need to change the shape below that overhang so that it's not an overhang anymore. Now, similar to walls, when we have angular walls, if the angle of the wall is in FDM, the straightforward rule is 45 degrees. If it is less than 45 degrees, then it has to be supported. If it is more than 45 degrees, there is no need of support. So here you can see the angle is less than 45 degree or equivalent to 45 degree. So support has been given. Now this angle varies from one technology to another and one material to another. For example, if we talk about metal 3D printing, then in stainless steel and aluminium, I can print this at 35 to 40 degrees. Whereas in materials like Inconel, it is as high as 45 degree more. So basically, depending on the material, this angle also keeps changing. And whatever, if I reduce this angle, the surface roughness also increases. So maybe at 45 you can print without supports, but the surface roughness will be high. By giving support structures, you can improve the surface roughness. So this was about the where do we need to give supports. in terms of inclined walls and holes. Now, if we have a flat overhang like this, what you see on your screen, this overhang has to be supported. This is a pocket. You can consider this a pocket which is of certain width. Now, if this is the printing direction, then we need to make sure that the this particular feature is supported. Now, this support can be in this form where you are filling up that cavity with certain material and later on removing that material, or it can be an angular support, what you see here. That you have put a support which is coming out of the part, not falling on the part. So in this case, it is falling on the part, whereas here it is falling out of the part. So there are different ways to give supports also. So support design is a very deep area of study in itself. Now there are other ways to avoid supports. You change the orientation of the part itself. So this slide is actually showing us that, okay, if you need to give supports, what are the different ways in which you can give supports? Or if you want to eliminate supports, what are the different ways in which you can eliminate support? So one is changing the orientation. Second is changing the design of the pocket such that minimum amount of supports are required. Here you can see, since we have changed the shape of the pocket of the overhang, there are only supports required at the tip of those overhangs. Or you can completely change that in a way so that uh, the design change is not requiring any kind of support structure at all. So these are the different methods by which you can avoid supports. But what happens if you print without support structures? Part failure. And what kind of part failure? This kind of part failure. So here the user has tried to print L structures, L-shaped structures with quite good amount of overhang. If the overhang is less than 1 mm or 0.6 mm, 0.7 mm in that range, then you can try printing without supports. Whereas if the overhang is more than 0.5, 0.6, depending on the process, then these kind of issues will come. These are uh, quality issues or which which have uh, caused the features not to be realized at all because there were no support given. So supports are very important, and I will quickly take you through different kind of support structures for different technologies, because every technology has different kind of thermal physical phenomena going on. That's why the requirement of support structures are different in every technology. For example, this is how the support design of a laser powder bed fusion process will look like. So what you see here, this is the support, and this will be removed after printing. This is sacrificial. And then this is the part what you see with solid density. This is the part. In a similar fashion, in polymer 3D printing, SLA, selective stereolithography, in that these kind of light supports are required. You can see these are the this is the part that is being printed, and these are the support structures. So this is the SLA support structures. Then when we talk about FDM, this is FDM support structure. This is fused deposition modeling. And when we talk about fused deposition modeling, there are two extruders in the FDM printers which allow for printing support structures, where in this you can have different material of support and different material of the part, which you cannot have in other methods such as laser powder bed fusion or SLA. There you have to provide supports of the same material which is there in the part. But in FDM, you can have different materials. Again, just like other methods, in FDM also the parts can be removed. One important thing now, there are certain methods such as SLS, selective laser sintering, or binder jetting, MJF, multi-jet fusion, binder jetting. These methods don't require supports at all, because again, the process physics allows in those methods for realization of the part without the requirement of support structures. So yeah, this was about support structures. Thank you, and see you in the last and next section of the module. Thank you. Welcome to the last section of this module, where we will learn about the slicing of the STL files. What is slicing? Why do we need slicing? And then we will talk about the commercial platforms available for slicing and the end-to-end process flow. So slicing is basically taking a 3D CAD model and converting it into a job file, which is G code file when it comes to FDM printers. And in a similar fashion, whatever G codes is just a format of 3D printing in for FDM printers, but other technologies have different kind of job files. But basically, it is used to give command to the 3D printer. Now, basically, as soon as the STL file is given as an input to the slicer software, then it starts dividing the slicer software into thinner layer of data. That layer of data is dependent on the layer thickness on which the part has to be printed, and also that is defined based on the productivity that is required and the mechanical strength that is required out of the part which will be printed. So this particular slicing software, uh, first of all, it slices the geometrical data. Then after that, there are different kind of settings of the 3D printer, the environment in which the printing has to be done. Those settings, those conditions are also defined in the slicer software where the slicing is happening. So, what are the type of settings that we can define in a slicer software? The first one is the printer settings. Now, printer settings is like what will be the layer height, how will be the shell, that means hollowing, how much infill percentage you have to do wherever there is a solid area defined in your CAD model. So, how with what density you are going to fill that solid area. We have one more slide in this module related to infill where I will explain you more, and also the speed. Now, if the infill is more, the speed will be less. So all these things are basically the printer settings which are stored in the slice file. So this job is done by the slicer. Then we have the filament settings. Now the filament settings means that what kind of raw material we are going to use, that we have to tell the printer, and with what speed and at what temperature the material has to be dispensed from the nozzle and laid down for 3D printing. All this information we have to tell the printer. So this information also is given input as an input in the slicer software, and the slicer generates the G code file and then sends it to the printer with all this information. Then printer settings like what model it is, what is the bed shape, what is the basically they are trying to create uh, a virtual printing environment in the software. So it will give you a build volume, virtual build volume, where you will have the length, breadth, and height of the build volume, or if it's cylindrical, the dia and the height of the build volume, similar to the actual printer build volume. So all these three informations: the print settings, the settings on which the print is going to happen, the filament settings, the setting at which the filament is being used and the material is being dispensed for the 3D printing, and the printer settings. That means the size of the printer, the Cartesian coordinates, or it's like other kind of coordinate. All these things has to be input. Now, once the slicing has been done, you can send the job file to the printer, and it will do its work. Now, let's try to understand about the uh, front end and back end of the slicing softwares that we are talking about. So what input you need to give in the front end and what the software will do at the back end, that we will try to understand in this slide. So basically the front end is something that you interact with, where you load the STL file, you visualize the STL model. If there are any errors in the file, or if there is any uh, issue with the file, with the model, and then you can also see the G code visualization in the front end. That means that you can actually see how the printer nozzle will be moving in case of an FDM printer, and in case of a laser powder bed fusion printer, you can visualize how the laser vectors or the laser paths will be defined for each and every layer. Now, in order to do all these things in the front end, what must be happening at the back end? So as soon as you load an STL file into the GUI, the STL reading, the software does the reading of the STL file at the background, and then it generates an algorithm which defines the slices. In that algorithm, as an input, you need to provide the layer thickness or other settings, as we told. Now, based on that algorithm, the layer data will be generated, and this one algorithm will define all the printing conditions, the input parameters required that we discussed in the previous slide. Now, once all of this is done, then the G code will be prepared at the back end. And when this G code is prepared, you can visualize the G code, verify the G code, and then send it to your file. Now, this G code can be any job file. As I told you, that job file depends on the kind of 3D printing you are doing. Now, let's talk about where to do all these things, where we can perform all these actions. Oh, sorry, before going there, let's talk about the infill pattern, which is a very important setting in FDM 3D printing. So you can see that we can define in the printer that how much this. Now here you have a circular circumference, which is the outer body of the part, which has been given as an input in the form of STL file and then sliced. But in the printer, you can define that how much area inside to fill with what density. Now, in this first case, suppose you decide to fill with zero density. Then this is how it comes here. Then you increase the density slightly, slightly, slightly. So all these are examples of varying infill density, right from 0% to 80-90%. You can see this would be somewhere around 100%, 95% or 100% in the center. So this is your infill. If it is more, your speed will be less. But at the same time, if your infill is less, speed will be more, but the part strength will reduce. So infill has to be thought of very carefully while giving instructions to the FDM print. Now, what are the commercial platforms which are available? The commercial slicing platforms are Cura, which is an open source software you can download and it can print with any FDM printer. Then Simplify 3D is another open source software which you can download and input your printer settings and you can start printing. Now in this software, you can load the STL files directly, generate supports for FDM and then start printing. Repetier is again an open source software. Octoprint is an open source but cloud-based software. So these are different kind of slicer softwares that you can use for slicing the file or preparing a G code file, a job file for FDM 3D printing. Now for other kinds of 3D printing, there are some commercial platforms which support end-to-end process flow, like generating the CAD file, yes, converting it to STL, yes, orientation, yes, support generation, yes, slicing, yes, job file, yes. And this can be done with a wide variety of softwares, but these are not open source softwares. These softwares have to be bought on subscription based or perpetual license. These are Fusion 360, which is by Autodesk. Altair inspired by Altair, Materialize Magics by Materialize. Materialize Magics is the most widely used 3D printing software for all the processes such as binder jetting, laser powder bed fusion, directed energy deposition, and others. ANSYS Additive. Now, ANSYS also has a full end-to-end additive manufacturing suite where you can design parts, simulate, design for additive manufacturing also can be done, and then you can finally be ready to produce a job file right from ANSYS. So this was about the commercial softwares which you can use to generate a job file for 3D printing. And this marks the end of our fourth module where we have learned about the pre-processing of the CAD data which is required for 3D printing. So thank you so much for attending this module. See you soon again. Welcome to the fourth module of the course, and in this module we will be talking about the various materials which are used for 3D printing for various technologies. So what we have done, we have divided this module into three sections. In the first section, we will be talking about plastics which are used for 3D printing. In the second section, we will be talking about the resins which are used for 3D printing. And in the last, we will be talking about the metal alloys which are used for 3D printing. And we will be sticking to the most commonly used materials in the additive manufacturing or 3D printing industry. So let's get started with plastics for 3D printing. So as you can see on your screen, there is a table. Not finding to place this. Okay, yeah. So there is a table on the in the front, and it has various materials mentioned in terms of their strength. So PLA is a very basic material, polylactic acid, which is a very basic material, and this particular material is used for very basic applications. It can be printed using FDM process. Then we have ABS, which is slightly better in strength as compared to PLA, and it can be used for fully functional components for functional applications, and it can be developed through FDM, and it also can be developed through stereolithography. For FDM, when we use ABS, then it is given in it is the raw materials in the form of wire or pellets, whereas for stereolithography it is in the form of a resin and some other combination, some other chemicals which are incorporated into the resin. Then we have PETG, which is a good thermal stability component material, and again it is printed through FDM. Then we have nylon, and nylon is basically a widely used component, even when we talk about conventional. And nylon is also used for manufacturing of components via machining. But in this case, 3D printing in 3D printing, we can use selective laser sintering and multi-jet fusion to make nylon parts. Then we have polycarbonate. Now using polycarbonate, you can actually make transparent components. And it is widely used in the aerospace industry, and it can be developed through fused deposition modeling technique. Then we have TPU. Now TPU is my favorite because it's a thermoplastic polymer, but it is flexible, and that's why if you see in the clothes industry, in the shoes industry, TPO is being used in a large way, and it can be made through FDM, it can be made through SLS, it can be made through multi-jet fusion. So you have multiple technologies which offer you the possibility of 3D printing TPU. So now we will stick to few of the materials which are used in the industry at a very wide scale. The first one is PLA, polylactic acid. So polylactic acid is available in spool and pellet form. I will show you how pellets look like in the next slide. Now this is used for some industrial solutions to some extent, but it is largely for hobbyists. It is largely to make architecture model. It is largely to make your components which do not bear any kind of load. And also the advantage of using PLA is that it's a green material. When you say green material, that means it is made from natural and renewable resources such as cornstarch, tapioca roots, or sugarcane. So it's a very nature friendly material, and it is the cheapest material you will get in some 700-800 rupees, 1500 rupees on Amazon per kg, this material. Then as you can see that it is good for making show pieces and components like flower pot, pen holders, basically any component which are suitable, which are low stress applications like custom brackets, housings, fixtures. You can 3D print small hooks to put on your wall for hanging clothes, things like that. Now this is this is the pellets that I was talking about. So instead of wire, there are now the FDM 3D printers which are coming. There is a class of a family of pellet based 3D printer. Now these pellets are even sold at half the cost of the wire or the spool. Now, these pellets can easily be used for FDM 3D printing, given that the printer supports pellet input. Then we have ABS. ABS is acrylonitrile butadiene styrene. Now, ABS is a tough material. As I told you earlier, ABS can be used for functional components, and it is also got, and as you can see, it is available in multiple colors. And it is a thermoplastic polymer, which basically comprises of three monomers, as the name suggests: acrylonitrile, butadiene, and styrene. Now, why do people use ABS is because of its flexibility, moldability, and I told strength already. Now, moldability is a very important factor because you can mold it into any shape. So printing is slightly easier with FDM. Also, it resists high temperature. And so ABS is something which gives options to you to print a wide variety of application. And it is largely used in making interiors for automotive, or it is used in making some functional components for automotives like hinges and others where there is not much load acting, but yeah, it can be used for load bearing activities. Then we have PETG. Now PETG is a bio-friendly material. It's a polyethylene terephthalate glycol. Now, PETG again is available in spool format, and PETG is a tough copolyester thermoplastic material. Now, the advantage of using PETG is that it has got a natural resistance to impact, humidity, and heat more than ABS. We will look at one slide where we will compare the properties of PETG, ABS, and your PLA. It is considered non-toxic because of its composition, and it is largely used in the food industry and FMCG industry. Now, another added advantage of PETG is that it does not deform under UV radiations, and it has a strong resistance to deformation. It's cost effective, less prone to warping compared to materials such as ABS. So it is a good choice for making components which face severe conditions, severe service conditions, and which are also supposed to bear loads. Now let's look at a comparison between PLA, ABS, and PETG. Now, when we see ABS, you can clearly see that the impact strength is highest with ABS. So when it comes to applications dealing with impact, ABS should be our first choice. And when we talk about UV resistance, both PLA and ABS are very much average when it comes to UV resistance, but PETG is much better than average when it comes to UV resistance. Density is highest for PETG and lowest for ABS. Thermal conductivity of all the three are in the similar range. Elongation at break is highest for PETG, 130%. That means uh, PETG is more ductile, and when the fracture happens, it will be of ductile nature as compared to ABS and PLA. Then when we talk about yield strength, the yield strength is highest in PLA, and flexural strength is highest in ABS. So when we talk about flexibility, ABS can give me highest amount of flexibility. So now you can clearly see when you have to go for impact, you go for ABS. When you have to go for severe conditions, you go for PETG. When you have to go for design for high yield strength, you go for PLA. So these are the various properties based on which you have to decide which polymer to go for. So these are your these come under the scope of selection of materials. Now let's talk about nylon. So what you see here is nylon 11. Now nylon 11 is available in powdered form. It's like have you you can it is identical to your talcum powder. So the raw material is available in that form, and it is made in SLS and MJF, both powder based methods. Now nylon 11 is the best material for printing curved surfaces, thin walls, and interior joints for machine devices, because the bending strength is very good when it comes to nylon 11. Also, nylon 11 is a high performance material, whereas nylon 12 is the nylon which is used for general applications. That also we will see in the next slide. Now, nylon 11 is engineered for end use parts that may experience impacts. For example, if you are trying to make the legs of a drone which is subjected to impact on every landing, or if there is a flight failure, then nylon 11 is a very good material. You can see in the image most of the components that you see, they are like functional components which are made for end use. There is a lever also. Now, when we talk about nylon 12, it it has a better surface finish than nylon 11, but less impact strength than nylon 11. Now, it can be used for permanent fixtures, fixtures which do not move from one place to another. It can be used for casings, enclosures. So basically, the idea is to use nylon 12 where there is less load acting, and it gives a good balance between surface quality and performance. Nylon 11 has a better performance, but the surface roughness is quite higher as compared to nylon 12. Now, nylon 12 has a high flexural modulus. That means the flexibility is more as compared to nylon 11, and the tensile modulus and heat deflection temperature are also higher as compared to nylon 11. Now, so nylon 12 is good for small batch manufacturing and general parts, but when it comes to high-end engineering, then you should prefer nylon 11. So thank you. That was about the plastic materials. Let's meet in the next module and cover the resin materials which are used in 3D print. Welcome to the second section of the modules materials. And in this section, we will be talking about the resins which are used for 3D printing. And resins, if I'm talking about resins, that means they are being used for SLA 3D printing, stereolithography that we have covered earlier. And the resins, we will start with a number of resins, but we will cover number of resins, but first we will look at the standard resin, which is the very basic resin with the minimum strength and minimum mechanical properties. And this particular resin, standard resin, now what is the advantage of using resin is that you get a very good surface finish, and the features that you can make are really fine. Basically, the resolution of the process is very high, and this particular material that we are talking about, SLA resin, they are acrylate monomers. So they take an acrylate monomer and combine it with multiple polymers such as epoxy, urethane, or vinyl ester resins, and hence the resin gets its properties. Now, this standard resin yields 3D printed parts with good resolution. That is what I meant when I told it is being the feature size can be really small, which you can produce. You can produce feature sizes as small as 0.2 mm, 0.1 mm, 0.3 mm, like that. And it is very good for prototyping and production purposes both. But you need to look where to use standard and where to use other resins. That is one thing that depends on the properties. So it's very important that we talk about the properties of the standard resin. So when we talk about the properties of the standard resin, we can see that this particular standard resin is having a tensile strength of 10 to 50 MPa. It has got a good hardness. Now, hardness you did not see in the FDM material because basically they don't have good hardness and they are not being used for industry production purposes. That's why hardness becomes very important in these resins, because they are very hard and tougher as compared to FDM parts. And then the deflection temperature is also good, 45 to 70 degrees Celsius compared to FDM materials. But when we talk about other resins, standard resin has got the lowest heat deflection temperature. Then there is another resin which is a tough resin. Now this tough resin is basically is used for making components which have got high stress conditions. It is more durable as compared to your standard resin. It is like the impact strength is more as compared to standard resin, and the resistance to fractures is more. So a standard resin part might fracture in a given loading conditions. There you need to use a tough resin component. Now it basically contains rubber additives and polymers. Now these additives and polymers are designed to provide high rigidity to the components that are being made using tough resin. It is more durable than standard resin, and that is the reason why it is more suited for functional prototypes. So if you want to make a prototype and put it under testing, then you should go for tough resin. Now, what are the polymers involved in comprising of the tough resin is urethane, epoxy, acrylate, and some rubber particles are also there. Now, these rubber particles are incorporated to increase the fracture toughness. Then the properties of tough resin. Let's have a look at properties of tough resin. So we can clearly see that the tensile strength is higher as compared to the standard resin. The elongation at break is also much better as compared to the standard resin. The impact strength. Now, impact strength is one characteristics that you did not see in the standard resin because it is having very low impact strength. Whereas my tough resin, as I told you, because of this high rubber being added in this, the impact strength is quite high. The isode impact strength is between 50 to 50 joule per meter. And then the hardness is definitely more than the standard resin. Then we have one more kind of resin, which is a flexible resin. So we discussed about TPU, which is a flexible plastic used in FDM. Flexible resin is basically, you can see in this picture, it can clearly indicate flexible, what does flexible resin means. And flexible resin is used a lot in the shoe industry, again in the clothes industry, fashion industry, also for prosthetics and functional components. As I told you, it has since it's flexible, it has got good amount of compressibility. Now, what it is made of? It is made of urethane, silicon. Silicon is what is giving the flexibility to the flexible resin, and other thermoset elastomers. Now, these thermoset elastomers, silicon and urethane together, they enable stretchability in the 3D printed components using flexible resin, and they also have got good bending and flexural strength. Now, since it is flexible, it is a good alternative to rubber molding process. You can see like how the parts looks like. Then when we talk about flexible resins, the typical properties that you see, that the tensile strength has decreased as compared to your standard resin as well as tough resin. The tensile strength of flexible resin is less, whereas the elongation at break is tremendously high. You can see that elongation at break can go up as high as 500%. That means it will deform to that extent before breaking. Hardness, shore A hardness is 30. The tear strength is 10 to 30 kilonewton per meter. And why tear strength and shore hardness is coming into picture? Because these are the typical properties of rubber or flexible materials. Then we have a specific resin which is used in the dental industry. So they are used to make dental models and dental molds, and these are biocompatible resins, so it can easily be placed in your mouth for dental and other orthodontics treatments. But yeah, you cannot leave it inside. It can only be used for an operational procedure or a kind of implant procedure, but it has to be taken out. It is just used as a tool. Now, the good part about dental model resin is that it meets ISO and FDA standards for temporary insertion. So ISO standards for medical, and FDA is anyways used for medical only. So FDA and ISO standards have proven it to be able to put inside your mouth. And it produces highly accurate crowns, bridge frameworks, orthodontic thermoforming models, surgical cutting guides. All these items that I told you, they assist in the surgery. They are not the final implant going in your dental area. Now let's look at the properties of the dental resins. Now in dental resin, we will not try to look at the mechanical strength properties, because the mechanical strength properties are not very good, but they are as compared to tough resin, but they are biocompatible. So it means ISO 10993 and USP class 6 standard for limited time exposure. So you can put it in the mouth, but for limited time. High resolution. Now, when we are making miniature dental geometries, we can actually realize those geometries with very high resolution using dental model resins. So that is the advantage of using dental model resins via SLA process. Then there is one more advantage of using it is that it is non-toxic. It is because it is made of medical grade monomers. So it is supposed to be inert when it is exposed to human tissues and fluids. It does not react with them. And you can see the density is very typical as compared to the general photo curing resins, the standard resins of SLA. So that was about the resins. We learned about standard resin, we learned about tough resin, we learned about flexible resin, and then we learned about dental model resin. There are some other high temperature resins and other kind of resins which we have not covered here. If you want, you can just Google them and for your understanding. Now these four are the most widely used resin in 3D printing SLA. So this marks the end of the second section, and we will meet in the next section, third section of the fifth module, materials for 3D printing, where we will cover the metal alloys. So stay tuned. Thank you. Welcome back. Let's start learning about the metal alloys which we can use for 3D printing. Now this is my favorite because I feel that metal 3D printing is the greatest advancement in the field of 3D printing, and the properties that we get from metal alloys, they are comparable to the conventional alloys. So this is just an overview of the alloys that are being used in 3D printing. For example, aluminium alloys, tool steel, steels, stainless steels, Inconels. Titanium is also one category that we will cover in this module. Now, aluminium, as we know, it is lightweight, it has got good alloying properties, it has got good electrical conductivities, but the best part is that it has got good processability with laser powder bed fusion. It is one of the materials which can be most easily processed with laser powder bed fusion, and that is the reason it is the most widely used metal alloy in 3D printing for any kind of application, whether it be automotive, whether it be aerospace, whether it be general industrial applications. So heat sinks is one section that we will cover when we are talking about aluminium in detail. Now LSI 10 mg is one of the materials which is the most widely used, but there are few newer materials also when we talk about aluminium alloys. Then we have tool steels. Tool steels are basically your H13 material, H11 material, maraging steel. So what you see here, 18 nickel 300, this is an alternative of most of the tool steels. This covers the properties of most of the tool steels. Now these properties include good machinability, very high hardness and toughness. Now the hardness can be as high as 60 to 60 HRC when we talk about tool steels, and that is the reason why they are used in all the tooling procedures such as plastic injection molding, pressure die casting molding, and very widely used in maritime applications where good strength is required and good durability is required. Then we have another family of steel, which is the stainless steels. All of you must be aware about stainless steel. It is the most commonly used steels in the industry, and this is made for good corrosion resistance basically. So wherever you require corrosion resistance, you go for stainless steel. It has got good ductility and it has got good strength under elevated temperature. Elevated temperature, that means 150, 200, 250 degrees Celsius, 300 degrees Celsius. And it can be used in automotive, aerospace, maritime. Also, if we talk about Inconel, Inconel is a nickel superalloy. Now it has got a good mechanical strength at high temperatures as well, and the temperatures that we are talking about in the range of 700 degrees Celsius, 1000 degrees Celsius. Inconels have got outstanding weldability, and also Inconel can be welded with tool steel, stainless steel, any kind of ferrous alloy. Inconel can be welded, And Inconel is largely used, since I told you it is for high temperature in aerospace, gas turbine, rocket motors, 62578. Many other materials are there of Inconel that we will cover. So now let's get started with our first alloy, that is a aluminium alloy. So if you see here, the aluminium alloy is used basically wherever you need weight reduction. That is case one. Case two is wherever you need good electrical conductivity and thermal conductivity. So it is used for applications such as heat sinks. What you see here by Conflux technology, this is a heat sink made by Conflux technology, and it is made in 3D printed in aluminium. Now the problem with aluminium is that the hardness is not very good. So when it comes to applications where you encounter high fatigue, in those applications aluminium fails, basically under high stresses and loads, because its mechanical strength, maximum mechanical strength that you can achieve is around 550 MPa. So if the stresses are more than that, definitely you need to go for any other material. So what are the alloys that are currently available in the industry for aluminium 3D printing? LSI 12, LSI 7 mg, and LSI 10 mg. Nowadays, aluminium 6 grade and aluminium 7 grade aerospace grades are also being 3D printed, but that is very limited. So that's why let's not discuss that here. Now, as I told you, this is a 3D printed heat sink by Conflux technology. Now, copper alloys, yeah, copper alloys can also be 3D printed. This is a very recent advancement. And if you would have asked me 3 years back, I would have said absolutely no, because copper has got very high reflectivity when it comes to making the part through 3D printing. Now, currently, copper is being 3D printed using laser powder bed fusion, and these are the various components which you will see here. And largely, these components are components which have to deal with electrical conductivity or thermal conductivity, because copper has got good ability to conduct heat. It can resist corrosion. Also, in some cases, it can even kill bacteria and viruses. And that is the reason why most of us use a copper jug to drink water at home, because it can kill bacteria and viruses. So copper is a very good development in the field of 3D printing. Then we have the materials of copper which can be 3D printed. The alloys are copper nickel alloys, CuCrZr, and pure copper. Now let's try to see where these are being used. Copper alloys are being used. So what you see here on your right hand side is uh, a electrical heat sink on a motherboard. So these copper 3D printed copper heat sinks are very good when it comes to minimizing the area and increasing the heat conductivity. So copper is a good choice there, definitely. But copper is also a good choice when it comes to making components for radio wave applications, because copper's reflectivity allows it to reflect the radio waves at the highest efficiency as compared to materials like aluminium. Aluminium is another material which is used for radio wave applications. So what you see here is a radio frequency called dropole. So basically it breaks any radio wave into 4 different frequencies, and it is a part of an accelerator complex. So imagine these kind of radio wave components can be made using 3D printing. So you can actually minimize, yes, you can minimize the losses in the radio wave transmission. Now this is my favorite slide, application to be precise, because copper, CuCrZr, the alloy that I mentioned for copper, is being used to make rocket engines. And this is from California based company called as Launcher. launcher has successfully tested its first 3D printed copper rocket engine. Now in India, ISRO and other private players such as Agnikul, Skyroot, they are also printing rocket engines, rocket components in CuCr ZR. Now we will talk about a very interesting alloy, one of my favorite but the most expensive alloy, Ti6Al4V. So all the materials that I told you, they range in the price range is somewhere between 4,000 rupees per kilo in powder form to 8,000, 10,000 in powder form. But titanium is ranging from 25,000 per kg to 40,000, 45,000 per kg. Also in conventional, titanium is a very expensive material, and it becomes 10 times more expensive when it comes to 3D printing. So it has got excellent properties such as lightweighting, high strength, low density. So it becomes a very obvious choice for the use in aerospace industry. Now let's try to understand about the application of titanium, because in all the other cases the uh, very single industry or 2-3 industries are using aluminium and copper, but titanium is being used for multiple reasons in multiple industry to a limited amount because of the high cost. But let's see why aerospace uses it. Aerospace uses it to make airframe and wing structures, and to make small components of turbine blades, compressor blades, where the temperature is not going too high. Wherever the temperature is going too high, we will use nickel superalloys. That is covered in the next slide. Then it is being used in medical because of its biocompatibility. Also, it is being used in automotive and motorsports because of its high strength to weight ratio and high temperature resistance. So all of us know that titanium melting point is very high. So that gives it a good resistance to high temperatures. And you can make, people are making brake calipers, people are making wheel rims, people are making uprights in automotive using titanium. But the major takeaway point is that titanium is being used anywhere for its high strength to weight ratio. You can get the maximum strength with the minimum weight. The material has got such properties. And when it's combined with additive manufacturing, definitely it gives you a very uh, holistic advantage of having lightweight. Now, let's talk about nickel superalloys. So these are few components which are from rocket engines, and these components are used in rocket engines because nickel superalloys can provide very high thermal stability. They do not tend to lose their mechanical properties even at 0.8 times of their melting point. So they can be used up to as high as 1000 degrees Celsius, 1200 degrees Celsius, depending on what nickel superalloy we are choosing. They can be manufactured through laser powder bed fusion. They can also be manufactured through directed energy deposition. So these are the two 3D printing methods. Yeah, the recent studies have proven that nickel superalloys can also be manufactured through FDM. They're a special material which comprise of a nickel alloy matrix, and your materials that we use are Inconel 718, Inconel 625, CM247 LC, HEST alloy, and IN 939. Now, why is it able to retain such good mechanical properties even at high temperature is because of the alloying elements. So alloying elements allow nickel to not oxidize even at high temperatures. Yeah, so that was about nickel superalloys, and I hope you are very clear now when to use titanium, when to use aluminium, when to use steel, when to use nickel superalloys. Steel, just like all the conventional applications, if you have a good design, if you have a good part for design for 3D printing, then you can go for 3D printing application. Whereas in all the other materials that I told you, 3D printing is always preferable as compared to conventional materials, because conventional manufacturing processes, because of the challenges in dealing with these materials in conventional manufacturing. So that was about the materials. This marks the end of the fifth module, that is materials for 3D printing. And I hope you are now very clear with what materials to use for what application, whether it be polymer, resin, or metal. And if you want any further information on this, you can please search in detail. There are material data sheets available on the internet which will give you a detailed overview of the mechanical properties of all these materials. Thank you and see you in the next module.
Welcome to the sixth module, Value Addition using AM, or Value Addition using 3D printing. So by now we have understood the various applications and the kind of 3D printing techniques which are being used in the industry. But now in this module we will learn that these technologies and the application together, what kind of arrangement are they finding with each other? And that is nothing but the value that the application derives from the particular additive manufacturing process. So in this module, we will learn about why and how to add value. Then we will talk about the examples of some of the complex geometries which can only and only be produced through manufacturing techniques such as additive manufacturing. And then we will talk about customization. Customization is one of the uh, most popular value addition that has become popular with additive manufacturing. Of course, rapid prototyping. Rapid prototyping is the uh, quick way of prototyping your designs in a product development stage. So how rapid prototyping is a value that is being added through 3D printing, that we will try to understand as well. Then we will talk about lightweighting. Now, lightweighting is a very important, I would say, trait of certain industries such as automotive, aerospace. So we need to understand how additive manufacturing can help us in making lightweight designs. And then part consolidation. Part consolidation is basically joining one or two parts together so that they can be produced as a single unit using 3D printing. So let's get started with understanding what is value. Now, earlier when 3D printing started, it was a technique where people could just make physical models back in the 90s, I'm talking about. But now it is much more than that. Using 3D printing, you can actually make uh, fully functional components which can be used for 5 years, 10 years of mission life, or whatever product life you want to design the product for. And this has been possible because of the benefits that AM offers. And broadly, when we talk from the product perspective, these benefits uh, lie under two categories. One is the production benefits. So the production benefits are the benefits which are incurred during the manufacturing of the component. Then the other one is lifetime benefits. Now, lifetime benefits are the benefits which are incurred when the component is being used. So it is throughout the lifetime of the component. For the time being, the component is in the service. Now, under production benefits, the various benefits are definitely reduced material consumption, shorter lead time. You can make components in a much quicker or in a much less time as compared to conventional manufacturing technique because there is no tooling required. And since there is no tooling required, there is no cost associated with tooling. Hence, your cost of manufacturing the components is more effective when we talk about certain number of volume or certain number of certain lead time or certain number of processes. Then the additive manufacturing happens to be more effective during the production. But of course, it varies from one case to another, as we have discussed earlier, and we need to identify the right case for that, and that is the idea why we want to understand all these benefits. Then definitely lower assembly cost. So one of the value additions that I mentioned few seconds back, part consolidation. Part consolidation means joining one or two or more parts together. So when we are producing two, three components as a single unit, definitely we are eliminating assembly. And thus the assembly time and cost is being reduced. Now, when we talk about the lifetime benefits, uh, what you can do is you can actually make a very lightweight component using 3D printing. And that we have seen in few of the examples earlier. So you reduce the weight. And when you reduce the weight, it is easier uh, if it is a static component or if it is a fixturing component, it is easier for it to be for the operator or the person handling the component to move from one place to another. Second, if the weight is reduced, it has a, a direct implication on the performance of the component in the aerospace and automotive industry. Then, as I told, uh, by reducing weight, you can improve performance, but not only by reducing weight. In some cases, you can improve performance by improving the heat transfer. In some cases, you can improve performance by improving the volumetric flow of the fluid flowing inside it. So there are multiple ways of improving the performance. So basically, you can make a very complex design which will help you to achieve a higher performance out of the same component. So you are basically extending the boundaries of your designing. Then uh, improved reliability. Now, since we are making components with lightweight, we are making components more stiffer, we are designing for 3D printing, and this all is resulting into improved reliability of the component when the component is being used. So value, all you can see from this particular slide, that value is not only being added when the component is being manufactured. If we switch to additive manufacturing, there are certain values which can be added, and the advantage of those values will be derived whenever the component is being used. So value is not limited to production, it is also limited to the use of the component. Now the question is how to add value. We have very well understood that what is value, but let's try to understand how to add value. So there are four stages of AM deployment. This particular uh, theory has been defined by Dr. Mark Saunders, the Vice President of Renishaw PLC. And the first stage starts with rapid prototyping and tooling, where we can make low volume parts directly from CAD. So if you have one or two components requirement, four components of requirement, whereas in your mass production stage, you will be 1 lakh, you will be having a very high volume requirement, 1 lakh, 2 lakhs. So mass production will be some other technique, but for rapid prototyping and tooling stage, you can adopt additive manufacturing. Then we have direct part replacement. Now this is for reproduction parts. Now if there are components uh, which are being used, but you need to supply it as a spare part. If some component gets worn out or gets damaged, then that component can easily be reproduced. But here we need to see that the geometry is not very complex, because uh, we cannot make any design changes, because the actual design has been made for a certain mass manufacturing technique. So we can only uh, make changes through which the end application is not affected. So that is why a fair non-complex geometry can easily be directly replaced and printed through 3D printing. Then we talk about part consolidation. Now part consolidation is about simplifying geometries, simplifying assemblies, and enhancing reliabilities. Now, for example, if I'm making a component through welding, and in 3D printing, I don't need to use welding. I can make the component without welding. So that is called as part consolidation. We will learn about that in the further sections of the module. And then in the end comes DFAM optimized. So in this case, you are redesigning the component for DFAM. So I hope you understand now how it works. First, you start with very basic components, you are only printing components for tooling or rapid prototyping, not the final component. Then you are making the final component but without any design changes. Then at part consolidation stage, you are making the design changes but only very minute design changes, such as joining the components together. And then in DFAM optimized, you also want to tap into the values that can be added at the lifetime use of the part. So that's why at DFAM optimized stage, you redesign the component for it. It's a completely new product design strategy. So this was about value. Now in the next section of the modules, we will try to understand the various examples of these values that are being added. Thank you and see you in the next section. Yeah, welcome back to the module value addition using AIM. And this is the second section where we are going to understand some of the examples of value additions that we understood according to the strategy of Dr. Mark Saunders, Renishaw. So let's start with the first level of AIM deployment, which is rapid prototyping and tooling. So prototyping, we are by now we all should be very much clear what is prototyping. It's bringing your idea to life for the first time. Now, prototyping uh, can take a certain amount of time, maybe a day, or two, a month, a year, also in some cases. So, what 3D printing does is it allows us to produce these prototypes without specific tooling required for the object. And when the tooling is not required, the time taken to manufacture these components are reduced drastically. Now, the catch here is that in prototyping, you can do prototyping for multiple purposes, such as for just ideation or visualization. You can also do prototyping for functional testing. So you need not have the same material, which is your actual material, which you will be producing the part in during mass production. For example, here you can see there is uh, earth digging equipment. I'm sorry, I'm missing out on the name of this particular equipment, but it is basically made of some metal alloys. But for prototyping stage, we can develop it in hard engineering polymers through 3D printing. This very drastically reduces the time taken to realize the first prototype. So your design iteration time is reduced. You can make conclusions based on your prototype, and then you can go to the next design iteration, create the next design iteration, and produce prototyping for the same as well for a feedback. So that is the idea of prototyping. Now I told you about direct part replacement. So here if you see, there are certain impellers. Now these impellers are conventionally manufactured through casting, but using additive manufacturing, these impellers can be printed in very less time. These impellers require uh, a particular mold which is very complex when they are made through their conventional way, which is casting. So in this, what happens that the mold manufacturing itself takes 1 to 2 months. Now imagine these impellers being part of any particular industry where the supply chain is very critical, and the parts have to be replaced, the worn out parts or the damaged parts have to be replaced in no time. Then they cannot wait 1 or 2 months. Whereas for 3D printing, since there is no tooling required, these impellers can be produced in hardly 6 to 7 days and can be delivered to the actual use of operation. So that is the advantage of direct part replacement. And in this, you don't need to change the design. So both in rapid prototyping in tooling and direct part replacement, you actually don't need to change the design. Minute changes you might have to do for adapting to 3D printing, because every process has got certain limitations. Then we talk about part consolidation. Now, part consolidation is basically redesigning and reimagining the assembly of the component.
So what is your objective here? The objective is to reduce the total number of components in an assembly by seeing if you can eliminate some joints such as bolting or welding or any other threading joints, any kind of joints. If you can eliminate, uh, then you can consolidate multiple points and print it as a single structure in 3D printing. What you see on your screen, on the left hand side, you can see that these are all sheet metal parts which are being made through sheet metal manufacturing, such as punching, bending, and stamping, and then they are welded together. Whereas on the right hand side, what you see is one single component produced through 3D printing in one shot. So this is what we mean by part consolidation, and this is very useful in reducing the assembly count. We will understand about part consolidation, what are the ideas, in the last module of this, in the last section of this module as well. Then we talk about DFAM optimized. So what is DFAM optimized? Basically, you redesign the component for additive manufacturing. So there are two kinds of redesigning methods available. One is simulation driven design, one is manual driven design. Simulation driven design is basically using a software algorithm to create the design, which where you have to give the input that 3D printing or what 3D printing technology is going to be the end manufacturing technique, so that the design that is being created by the software has already taken the manufacturing technique into account. And manual driven design is where you make the changes yourself. The designer makes the changes himself or herself, and then reaches to a conclusion that this is a good 3D printing design. But yeah, it can be really time taking, and multiple discussions amongst various teams might be required to reach that. Whereas the simulation driven design techniques such as topology optimization and generative design, they can really help you redesign components in no time for additive manufacturing. Now, this image that you are seeing, this is from a software platform called as Topology, which is one of the most advanced engineering design tool for additive manufacturing. So, thank you. That was about what kind of values and at what stage the values can be added, basically a roadmap of AM deployment. Now we will take a dive into the specific techniques of value addition in the next section. Thank you. Welcome back to the third section of the sixth module, and in this section we will learn about the different kind of complex geometries that we can produce through 3D printing. So before going further, the first thing that I would like to talk to you about lattice structures. Now, lattice structures, I hope you are aware about lattice structures because it is used in the conventional industry as well. But before 3D printing, manufacturing lattice structures used to be a very clumsy task or a very hectic task. Whereas with 3D printing, we can easily manufacture lattice structures with high degree of complexity, as you can see on your image. So basically the image that you see here, this is a 3D printed rocket engine manufactured in a single shot as a single component. And the weight of the rocket engine was reduced drastically by using lattice structure inside the structural walls. And the advantage of using lattice structure here is that it does not affect the mechanical strength of the walls. The stiffness or rigidity of the walls is equal to the solid walls. So basically, you can use lattice structures without affecting the functionality but reducing the weight at the same time. So lattice structures are a very, very, very big boon in a, I would say, in a designer's life when designing lightweight components. So a bit more about lattice structures. So what you see on your screen is a gyroid lattice structure. It is a particular type of lattice structure. So this particular image I have put to explain you what is a lattice structure. So uh, any particular given design space
can be converted into an area where a certain amount of material is being removed. For example, uh, if you give the software command to generate a lattice structure with 30% weight removal, it will do that. If you give the command to generate lattice structure with 70% weight removal option, it will also perform that. And you have to take care of certain parameters, such as what is the minimum thickness of the lattice struts that I need to maintain. And with these particular kind of components, you can see on your screen, if we just convert one particular cylinder, a disc, to lattice structure, then we can also increase the surface area by 4x. And so lattice structure is not only used or useful in the areas where we have to reduce weight, but also in the areas where we have to improve heat transfer of or heat efficiency. And what you see on your screen is a gyroid lattice structure, which is known for its heat transfer properties. So lattice structures, as I told, are also a big advantage in the heat heat transfer areas. So this is one example of a cold plate. So basically, this is the cold plate for a electric race car. There is a Formula student team called as Dynamis PRC, and this is the uh, cold plate for cooling their battery management system. For cooling their battery management system, and it is called as a cold plate, and inside you will see that it has been filled with lattice structure. Now the advantage of using the lattice structure in this case was that the dynamic PRC team was able to reduce the weight of the component by 30% and improve heat transfer efficiency by 300%. So this is what I was talking about. Now, another very interesting application or the value that lattice structures add when you are making a medical implant, that it helps you produce a very rough texture kind of surface, uh, which is porous, which is not completely solid. If you see these images, these components have been designed so that when they are 3D printed, they are printed and they are porous after printing. Now, why we want these components to be porous? Because if they are porous, they will encourage tissue and bone growth, and that is something called as osseointegration. So naturally, while we are making implants, considering a block implant at certain areas is a much less preferred option uh, compared to lattice structures. So lattice structures, three benefits till now we have seen: lightweighting, improved heat dissipation, and the third one, this is osseointegration, which is used in medical. Now, another example, all you see, there are multiple examples here. One is on the left hand side of your screen. You have your shoe soles, which are being 3D printed nowadays. And the advantage of these shoe soles being 3D printed is that they absorb energy better than the conventional soles, and their life is also much longer as compared to the conventional soles. And then you have these impact resistance, shock resistance helmets, where lattice structures has been used in the inside layers for the same purpose of shock absorption. So lattice structures have multiple advantages, as you can see in the left bottom side, right bottom side here. This is again a lattice structure, a particular lattice structures which has been designed for 3D printing to be used uh, in a heat transfer application. These areas, so some of these uh, areas will be used for one particular cold fluid flow, and this will be used for hot fluid flow, and through these thin walls manufactured through 3D printing, the heat transfer would be taking place. And the area that has been increased in this particular instance because of additive manufacturing and this redesigning of component for AM is tremendously high. Then we have something called as internal cooling channels when it comes to high design complexity. So here you can see there are a number of these fuel injectors. These fuel injectors have been multiple fuel injectors have been combined on a single plate. Earlier, all these fuel injectors were being manufactured individually and then welded together on a plate. But now they have been produced in a single shot, and each of them are having very minute cooling channels. Not cooling channels, these channels are for the spray of fuel into the Ariane engine. Ariane 6 is the launcher by NASA. Then if you see here on the right hand side, this is a new model for an engine. This is called an Aerospace engine. And in this, if you can see, there are multiple cooling channels. So this is called as regenerative cooling. When the engine is working, it generates very high temperature for combustion, and the material should not oxidize. So at that time, the fuel itself is passing through the structural steels using these internal cooling channels and then cooling down the engine. This is called as regenerative cooling. So before 3D printing, these cooling channels had to be made in the form of tubes which were welded to the particular engine structure. But now these are integrated in the structural walls of the engine. That is why they are called as generative cooling. So this was about the examples of complex geometries. So what advantage complex geometries gives us if we make them through 3D printing. And in the next modules, we will talk about, in the next section of the same module, we will talk about further value addition techniques. Hello, welcome back to the sixth module, and this is the fourth section where we will talk about customization using additive manufacturing. So customization is the all-time favorite of everyone. I mean, the most favorite value addition technique that has become the most popular with 3D printing. So let's try to understand what kind of customization is happening using 3D printing. So we will only understand these through multiple case studies. So the first one is of uh, these specs frames. So for specs, the lenses and frames are being designed and positioned in such a way that it is fitting the individual need of a person. Now, as we know, like uh, as the geographies change, as the countries change, as locations change, different kind of people are having different features when it comes to the face of uh, different people. So definitely, if you want to fit one product to different kind of people, then there would be some people who will be feeling left out. But this problem can be addressed by making customized products for specific people. So now there are companies who are manufacturing specs in such a way that they capture the facial feature of the customer, and based on their facial features, the specs frames are designed in such a way that it suits them in the most appropriate manner. Interesting, right? Huh. So another customization example you'll see here is of from Sonova. So Sonova is not an Indian company; it's an outside company, and it is making uh, hearing aids specific to each and every person's ear. So again, rather than making uh, hearing aids through a labor-intensive process, they are just taking a digital scan of the ear, and then using that data, they are generating the design and manufacturing it through 3D printing. One more example of customization. So the sole of the shoe, or what you call it as 3D printed orthotics. 3D printed orthotics, also known as corrective insoles, which you slip for flat foot people or different kind of people who are suffering from different kind of foot problems. And this particular insoles can be generated based on the design of your foot. So your foot will be scanned, and based on the scanned data of the foot, the most appropriate design of the corrective sole will be manufactured. So all these are kind of medical or personal healthcare examples where customization plays a huge role, huge role. Now let's talk about some music, something about music industry. So you can relate to this picture, right? This is nothing but an earbud of a earphone. So now these earbuds and earphones, now every person is having a different or slightly different or maybe differing by a huge amount, but the design is of every person's ear differs. So what normal, the company who is manufacturing these earphones, they did is they started making customized 3D printed earphones. So all they needed was a photo of your ear, and based on the photo of your ear, they will develop a CAD model, and using that CAD model, they will be able to make, design and manufacture a earbud which exactly perfectly fits into your ear. So this is the advantage. And yeah, the most important part is this custom fit pair of earphones are being manufactured within 48 hours by normal. So both customization and speed are the value additions that we can see using additive manufacturing that normal has taken advantage of. Then let's talk about rapid prototyping. Rapid prototyping, we have seen earlier also, we have spoken a lot about rapid prototyping. So here I want to focus on particular things of rapid prototyping, such as uh, rapid prototyping is most favorable through 3D printing, because in other rapid prototyping techniques such as vacuum casting or investment casting, you require a mold. Now, depending on your end application or what material you want to develop the component in, you have to choose the material of the mold, whether it be polymer, metal, or what kind of material. Whereas in 3D printing, there is absolutely no need of a mold. So if you compare 3D printing to other rapid prototyping techniques, 3D printing is the most cost effective and the most fast one, is the fastest technique. Also, the biggest example, one example now I would like to give about this cost effective and fast, that Centaur. Centaur is a award-winning manufacturer of industrial door systems, and definitely, since they are making their products, they are going through a product development stage, and at their during their product development stage, at the prototyping stage, they were able to reduce the cost of one prototype from $800 to $10 using 3D printing. Not only that, in fact, the time of manufacturing these components prototypes went down from 1 week to 12 hours. So that is the power of 3D printing when it comes to rapid prototyping. Then here is one example by Markforged. So basically, what this example illustrates that you need not have the same material while prototyping. For example, if there is a component where for prototyping purpose, you want to understand how the fitment is happening. An enclosure like this, what you see on the screen, where different components have to be mounted on this enclosure. Uh, Now, in this, the actual enclosure, which will be mass produced using conventional manufacturing technique, will be of aluminium. But here, through 3D printing, we can actually make components which are stronger or equivalent in strength as compared to aluminium, and these components can be used at the prototyping stage for evaluating the fitment or doing the functional testing as well in some cases. So the basic purpose is to evaluate your design
which using the material which is most readily available and which is slightly equivalent uh, in terms of strength as compared to your actual material. Then here you will see there are some prototypes of engine, of a 8-cylinder engine. And this 8-cylinder engine, for example, if you are making for a prototype vehicle only to go in a race or to put in auto expo or to present to your management for customer for budgetary approval so that they can approve the design, then 3D printing is the absolute way to go with, because this will help you in realizing these components with a very limited period of time and with less complexities or less complex manufacturing techniques involved. And prototyping is the, like, 3D printing and prototyping go very well when we talk about the automotive industry, because their product development cycles are really really fast and their schedules of testing are very tight. If they want a component to be tested on a particular day, it has to be done on the same day. And that is the why uh, they are using 3D printing in a very aggressive manner. So that was about the value addition techniques such as customization and rapid prototyping. Now, in the next module, sorry, in the next section of the same module, we will learn about uh, lightweighting. We will learn about lightweighting, and we will learn about your other value addition techniques. Thank you. Yeah, so now by now we have discussed multiple value addition techniques. Now let's talk about a very critical one, which is lightweighting. As I told you earlier, lightweighting is the favorite for aerospace and automotive industries, because for automotive industries, the simple funda is that they want to improve or increase a particular ratio, which is denoted by power upon weight. So they always want to improve the power and they always want to reduce the weight. And the same funda is true for aerospace. Why in automotive? Because kitna deti hai? That is the basic funda that Indian automotive market is being driven by. So basically, if you are able to improve the power, if you are able to reduce the weight, you are improving the efficiency of the vehicle, and you can run more number of kilometers with a good vehicle design. And in aerospace, every particular gram cost in thousands of dollars. So that is why aerospace, it is highly recommendable to use as lightweight components as possible. So the way of creating lightweight components, there are multiple ways of creating them, and one of them is topology optimization. So topology optimization is basically the optimized layout of material within the structure, within the geometrical design area. So you have to design basically that this is my design space, this is my non-design space, and the software or algorithm which has been set by certain rules, it will automatically put material in the area where the loads are passing through or where stresses are high. And wherever there are negligible stresses, it will remove material from there. So basically, you are putting material wherever you need and you are removing material from the areas wherever you don't need them. Now, the goal while doing topology optimization is that we have to maximize the part performance. Now, this part performance is being affected by multiple factors such as the loading conditions, the boundary conditions, the constraints, the material properties, and all these factors together are fed inside the software algorithm, and then it comes out with a particular design which you work on a bit, like smoothing and other things, and then the design is ready to be printed. So what you see on your screen is a typical workflow for topology optimization, where you start with a solid block of component that has to be optimized. You design the design space, non-design space. Now, for example, wherever the bolts are going, you will define that area as non-design space. You cannot have material in those areas. Now, the software will run an FEA, finite element analysis and generate the stress map for the particular component under the loading and boundary conditions. Now, once the FEA has been done, the software will get the result that which areas are of high stress and which are of low stress, and it will only keep areas where high stress is occurring. And that also you can define what you want the factor of safety based on the factor of safety and the percentage weight you want to reduce. It will add material and remove material. So this is what topology optimization means. Now let's look at some examples. Here you can see the previous example that depending on what objective you give to the algorithm, 30%, 40%, 70% weight reduction, it will generate different kinds of designs. Then we have a very interesting chassis for a bike, uh, which was designed by AP Works. Now, these chassis are a single structure chassis. The interesting part is that they have been designed in a way that the material is optimally laid at the areas where the stresses are occurring. And rest of the area, there is absolutely no use of putting the material. So imagine in a conventional chassis, if you're putting material everywhere, uh, around 30 to 40% of the material is not required. And that is the advantage that you can have through 3D printing, because making such complex designs is only possible through 3D printing. So topology optimization is an absolute way to go for if you want to have minimum weight of your component without affecting the functionality of the component. Then another concept is generative design. Now in topology optimization, you give some certain conditions, constraints, and your objectives, and it creates a design. You work on the design, and if you don't like the design, you can change the parameters that you had input, and accordingly, it will generate a new design. Whereas in generative design, what happens that number of design options are generated by the software. So here you can see this is a bracket for General Motors, which was optimized using generative design in Autodesk software. And the software basically gave 150 design options. This is a component which is mounted on the seat for your seat belt. So now now the designer has a wide variety of options. If they want to try 4 5 different design iterations in the first prototyping or first product development stage, then they are welcome to do so. They can choose the best depending on their preference. So this is the difference between generative design and topology optimization, that generative design is considering multiple scenarios and generating the design, whereas topology optimization is exactly asking you for each and every scenario, the particulars of the scenario, and then they are generating the design. Now, let's talk about part consolidation. What you see on your screen on the top of the image is your conventional component. So it is made up of number of components. One component here you can see, one component here you can see, then this component has been welded to this component, and there are so many nuts, bolts, washers, and three components I can clearly see. Now the same component can be used can be produced as a single part in 3D printing. This is called as part consolidation. And not only that, you can even reduce the wall thickness, because 3D printing allows you to provide such ribs on the parts. So this particular scenario, 42 piece assembly has been optimized into a single part. And the advantage of it is that you don't need an inventory for so many nuts, bolts, and different parts. You don't need welding. You don't need time to do the fastening of the nut and bolts to join number of components together. And the complete part is being manufactured at just one single place. So this is the advantage of part consolidation. And that is the reason why I have brought here one more example, which is to do with the your heat transfer industry.
So these are basically heat transfer devices, and these devices, earlier you must have seen a radiator in your car which you are using. So they are made up of multi hundreds and two hundreds of aluminum sheet metal parts welded together, whereas using 3D printing, Conflux technology is producing custom made heat exchangers for each and every application for their customers. And these heat exchangers are uh, are having hundred times fewer parts than conventionally manufactured components. And because of having less number of components, the production time of such components are also reduced. And Conflux Technologies is making this particular heat exchangers in only 16 days, and this is being made for the rocket company called as Relativity Space. So aerospace is the most favorite or most favorable customer of additive manufacturing, I would say. So now, one more example, I would want to show you two more examples to be precise. This is by Desktop Metals, where they have produced this particular fuel fluid connector assembly, which is used in a chemical processing industry as a single unit. Now, this particular component was being made earlier through by manufacturing 8 separate components and then joining them together through welding and press fitting. So all that assembly and different manufacturing stages gone, just one single manufacturing method, 3D printing, and after that some machining on the component, and then the component is ready to be used. Here, what you see on your screen is it's a Now, traditionally, this part is made by cutting the threads on a lathe machine, and then they are both these gears are manufactured separately, and then they are assembled with set screws and adhesives. But using 3D printing, this is produced as a single part. So this is the advantage part consolidation is offering us. Now let's try to understand whatever we have understood for related to part consolidation in this module. Let's try to summarize it. So definitely, if we go for part consolidation, we end up using less material. We eliminate all the joints, and thus the failure risk associated with all these joints are also gone. You are eliminating processes of assembly, which helps you achieve a low labor cost and low labor consumption and low energy consumption. Also, your requirement of skilled labor, such as welding or other techniques, that is completely eliminated. Now there are less number of components, and those components can be easily produced through 3D printing, so they can be produced on demand. So this is another advantage of part consolidation. And definitely, since we are reducing the number of components, we are reducing the number of assembly stages, we are reducing the manpower involved in assembly, we are reducing the inventory. So all these things end up in reducing the risks associated with supply chain, and all can be done under one roof, and that particular skill set of that particular facility or service bureau can be monitored very easily. So these were the broad points of part consolidation, and I hope you now understood what are the different value addition techniques and where are they being used and how to achieve these value additions. So we will learn about a few of these specific techniques in the future modules. Thank you. Have a great day. Welcome back to the course Role of 3D Printing in Industry 4.0. And this is the seventh module. This is about design for additive manufacturing or 3D printing. So what are the design considerations that we need to give? In the previous module, we learned about the value additions, which were largely based on the different advantages that you can take from 3D printing.
But now we will learn that how to keep in mind the advantages as well as the very basic limitations of the process, and how to incorporate that in your design so that you can have a successful 3D print process and you do avoid build failures. So in this module, we will be talking about the design limitations, the design guidelines, the design modifications which you can do to a part to make it more suitable for additive manufacturing. And then we will talk about a concept called as simulation driven design, which I have also discussed in the value addition module. But in this module, we will see how to achieve simulation driven design and what is the workflow of simulation driven design. Then we will talk about the three-layer design approach for simulation-driven design, where we will understand that what are the different things that we need to do in each specific layer of designing so that the process is as as smooth as possible. The 3D printing process is as smooth as possible and the part is realized without any challenges or without any difficulty using 3D printing. So let's get started with design limitations and design modifications for additive manufacturing or 3D printing. So uh, you can see that on the screen we have a topology optimized component, something that we discussed in the our value addition module. So this design, when we talk about value addition, it has been perfectly designed. It has been designed uh, for minimum material consumption. It has been designed for low weight. But still, when we go to the build processor and start processing this CAD file for 3D printing, this is not the ideal design because it is generating a lot of supports. And when there are a lot of support structures, we have studied earlier that for supports we need to remove them after 3D printing, and then that becomes another process which is added to your workflow. And also wherever supports are there, those areas will have slightly poor surface finish as compared to the areas where supports are not there. So it's desirable to avoid supports. So what is the fundamental of avoiding supports is that any feature which is at 45 degree with respect to the base plate where you are printing the part is requires support. Any feature less than 45 degree. So basically low hanging features, this is 45 degree, and if it's a low hanging feature it will require support to be connected to the base plate on which it is being printed. Whereas if the angle is more than 445 degrees, it will not require support. So this is something, this is a recap of what we studied in the module uh, where we discussed different stages of 3D printing. Now, in order to understand what are the other areas where we require support, so any island, by island, when I talk about island, just focus on this encircled feature. So basically 3D printing is a layer by layer phenomenon. So by the time you reach the layer where your this tip will be printed, then as per the printing process, it is a completely unsupported area feature which is not related to the part because it is attached to the part from the layers above which has not been printed yet. So it is very important to understand in order to successfully realize this feature, we need to add a support structure. Also all the holes diameters wherever the it is more than 6 mm 5 mm, there we need to provide support, otherwise the holes will become oval. But this philosophy is only true for FDM, fused deposition modeling, that we understood, and then laser powder bed fusion of metals. In the laser powder bed fusion of polymer materials, we do not need support structures. So whatever we will discuss in this module, that is true for FDM, LPBF, and SLA technique, SLA DLP, which is resin based technique. So let's move further, and since we have covered support structures in the previous module as well and the previous module as well, so uh, that was a recap of support structures. Now based on the requirement of support structures, you need to modify your design. So how do you modify your design? uh, Basically in order to, if we want to modify our design, first let's understand the basic constraint of that particular feature. So when the hole is less than 0.4 mm, it will not be printed at all in your part. When the hole is 6 mm, it will be printed and support will not be required. But if it is more than 6 mm, for example 10 mm, then supports will be required. If you print without supports, this is what will happen to the hole, as you can see in this image. Or if you don't want to give support structures, then this kind of modifications need to be done. So this is called a teardrop shape. A hole can be converted into a teardrop shape. If it's a functional use, later on it can be machined. Then this is a diamond shape. Hole can also be converted into diamond shape. Or if the hole is very critical and your positional tolerance is also required, then you better close that hole and then later on realize that hole through machining. So this is the design modification with respect to the holes that we need to do. Now, when we talk about overhangs, then you can see here that if my part is having an overhang means that if this is a feature, then this area will be called as overhang, which is uh, in air, which is not being supported to any structural member. So if I have 1 mm overhang, then 1 mm overhang can be printed without any support structure. But for overhangs like 5 mm, 10 mm, 20 mm, you can see we require support structures. So what we can do is we can convert that overhang into a chamfer, as you can see in all these cases. Now a chamfer, what it does is that it helps me realize that feature in a better way without the requirement of any support structures. Then the other way is orientation. So this example you can see there are multiple orientations given here. Only in this orientation if we have to print, then we require support structures. So the first thing is you should try to optimize the orientation. If you're not able to optimize the orientation, then what you can do is you can modify the design in such a way that it eliminates support structures. Like a T-shape feature has been converted into a slanted feature, eliminating the requirement of support structure. So these things are very necessary to keep in mind while designing a component. So now I will give you a very wholesome overview, like what are the design tips basically when you are doing. First of all, that remodel all the holes which are 10 mm to cell supporting diamond shape or teardrop shape. Second is what we just discussed, use chamfer or radii to avoid tall supports. There is no requirement of giving very tall supports because they can also cause build failure. And also, it's an unnecessary headache, wastage of material, too much time removing those support structures. It will spoil the surface areas. Then you remove all the overhanging areas which are at an angle less than 45-degree to the base plate. Then rotate the downskin away from the wiper direction. Downskin is basically the areas which are facing downwards. So if your feature is like this is called downskin. Now if recoater movement is like this, then build might crash. So you have to make sure that you change the feature and your recoater movement is, so basically if this is the feature, your recoater should move like this. It should grow with the part. The part feature growth should be in the direction of the recoater. Last but not the least, uh, the small features that you cannot realize through 3D printing, that you will have to machine. So give the allowance for machining during the 3D printing time itself. Everything, all of this has to be decided well in advance while designing the component. If you incorporate all these things, then the design will look something like this. Here you can see a part printed in uh, laser powder bed fusion in aluminium alloy. And here all the considerations have been given. Not only the part has been optimized for topology using topology optimization for minimum weight, but also it has been modified for laser powder bed fusion process. So this is what we mean when we talk about design for additive manufacturing. Now, how to do this? So what you can do, that any 3D printing process or any 3D printing machine will be having a software, build processing software with it, which will highlight the areas where supports have to be generated. So you can identify these areas and you can check for multiple orientations, that which is the orientation where I am getting the minimum support structures. then you can freeze that orientation and redesign all the features for that particular orientation. So that is what we have done with this particular component. This is the redesigned component in the software. Now, once you have redesigned the component and removed support structures, the build will have highest chance of success. And also your part will be realized with the best quality. But remember, all this has to be done at the designing stage itself. So this was a very uh, basic introduction to design for additive manufacturing. I used a component, and please explore more about this. There are multiple documents available online for design guidelines, and this will only help you make your design better. So with this, we will end this section of the module, and in the next section, we will learn about simulation driven design and the three-layer approach for simulation driven design. See you in the next section of the module. Thank you. Welcome to the second section of the module 7, Design for AM, and in this section we will talk about simulation driven design. So first let's try to understand what is simulation driven design. Now simulation driven design is basically the design which has been optimized based on the simulation or finite element analysis of the component. So the usual way of doing finite element analysis of the component is that the designer makes the design in SolidWorks, Creo, or any designing platform. Then it is sent to a simulation platform, a FEA platform. It can be integrated in the same design software, or you can take it to popular FEA platforms such as ANSYS, and then you do one round of simulation there, and if you don't get the right result, then you come back to your design software and make the changes, and then again you go back to the simulation software and simulate your redesigned component. So this is an iterative process. This is the conventional designing process. But with 3D printing, simulation driven design has taken a lot of what do we say uh, a lot of popularity. It has gained a lot of popularity. And if you see at this your images at the screen, you will realize that these are the various components that you need to input or you need to consider while doing simulation driven design. So simulation driven design is basically of two types: topology optimization and generative design. We will understand in the later module what that means, in the later part of this section what that means. So you have to define the design space and non-design space first. So defining a design space and non-design space means the area where you want to optimize the component and the areas where you don't want to optimize the component, that is called non-design space. So what you see here in yellow color is the area which can be optimized, and the area in gray is something which cannot be optimized because that area is being used for mating. Some bolt is going there, some screws are coming there, or another part is mating. So those areas you cannot use as a design space. That mandatory have to be there in the design. Now once you are clear with the design non-design space, you provide the loads, what kind of loads are acting on the component. You provide the supports, whether it's fixed support, hinge support, what kind of support is there in the component, which area, what location, and then you define the constraints. In this, the best part is that you can define the constraint with respect to the manufacturing process. Always you can select that laser powder bed fusion or FDM is my manufacturing process, so please consider the constraints for laser powder bed fusion. So these were the constraints that we discussed in the previous section of the module. Now once you are done with that, you define an objective. What is your objective? You want to achieve maximum stiffness or you want to achieve minimum mass. These are the two major objectives that are defined in the software. Now once you define all these things, your design will be converted to a very basic topology optimized part with number of advantages such as lightweighting. Now This simulation driven design, largely that most of the people are using in the industry, is topology optimization and generative design, as I told you earlier. So let's first understand what is happening in topology optimization. Then I will tell you like how topology optimization differs from generative design. So in topology optimization, basically it's a shape optimization method which is using algorithmic models to optimize the material layout within a user defined space. So this user defined space is the design space. And then all the boundary conditions that you have provided, based on that, it is the algorithm is generating the optimized design from the actual design. You can see in the image below that we start with an normal design which has been done in SolidWorks Creo. Then it has been sent to Altair Inspire, where an FE analysis happens on the part, and based on that it removes material where there are no stresses, and it tries to improves the performance and efficiency of the design by removing all the redundant material from the low stress areas, and where the part is not carrying much of significant loads. Now this cannot be only done for reducing the weight. In fact, it can be done for design challenges such as reducing resonance or reducing thermal stresses. So there are multiple objectives which you can define for topology optimization. Now, this is a 20-year-old technique, but why it has become popular so suddenly? Because these designs cannot be manufactured very easily by the conventional manufacturing methods because of the high amount of constraints that they impose on the manufacturing. Whereas 3D printing allows these topology optimized designs to be printed successfully with very minor modifications. Now, what is the workflow of topology optimization? So we start with an original design, then we do a FEA analysis of the part, the finite element analysis, simulation basically. Then based on that simulation, the algorithm generates the topology optimized shape, and then the topology optimized shape is finally uh, modified by the user to make it more smooth or make it more aesthetically good. And then you do one more round of FE analysis for the validation of the design that has been produced by the algorithm. Now, what you can see here is that in this case, it's a bracket for aircraft. Basically, it's a partition wall. When you fly in any commercial liner, you will see that where the door is and the first this thing is there, sitting arrangement is there. In between the door and sitting arrangement, there is a partition wall. So this particular partition wall was taken up by Airbus, and they optimized this for topology optimization. So this is how the topology optimized material looks. Now you can modify it to look more aesthetically appealing. So that is how the topology optimization process works. Now, what is generative design? Now, the same thing that you are doing in topology optimization, you have to input a CAD model first, basic CAD model that you have made in your other CAD modeling softwares. But when we talk about generative design, you only have to define the boundary conditions which we discussed earlier, and then the software uses AI to autonomously create the optimal designs, and it will create multiple designs, and you can choose from those designs that what do you want. These are few examples of generative design where there has been minimum or no amount of designer interference. As I told you, the algorithm will also take into consideration the limitations of 3D printing that we discussed in the first section. Now, what are the commercial platforms which are available? So, topology optimization and generative design can be done in a software called as Topology, which is very popular. It can also be done in SolidWorks. SolidWorks is the a very most popular CAD platform, but it is also giving plugins for generative design and topology optimization. Then we have Autodesk Fusion 360. You can download it from the web, Autodesk Fusion 360 comes with a very comes with a 1 year free license for all the academic users. Then we have Creo. Creo is again a conventional design software, but now it is giving provision for topology optimization and generative design. Then we have Altair Inspire. So all the screenshots that I'm showing you, they are from Altair Inspire because I personally use Altair Inspire. It's my favorite software for topology optimization. Generative design feature is not available in Altair Inspire. Then we have Tosca. Tosca is again a very good platform for topology optimization. So kindly go on the net down. If you use whatever you are convenient with amongst these softwares, you can download them. If not free education license, then they will give you some trial license. You can use that for a month or 14 days or 2 months, 3 months, depending on what platform you're going with. And please start practicing. Once you practice optimization of certain component, and then you will realize okay, how useful a tool it is for 3D printing. So thank you and see you in the next module where we will try to learn about the systematic approach considering topology optimization, design limitations, and simulation driven design, that FEA analysis, finite element analysis. So see you in the next module. Welcome back to the last section. Welcome back to the last section of design for a module. And in this section, we will be talking about a very systematic 3-layer approach. So this approach is something which has been combined from various studies to give you a systematic workflow, how to modify your design. And you will see in this module that whatever we have learned till now, uh, what you will see in this particular section of the module 7, that whatever we have learned in module 7, how that has been implemented using a case study of brake pedal. So this is the 3-layer module that I have created for uh, all of you to understand the various stages of design for additive manufacturing. So the first layer consists of design for LPBF. When I say design for LPBF, that means your chamfers and other things, and there are multiple other considerations that we need to take that I have explained in this particular layer, that what are the considerations. Then the second layer is of topology optimization, that how you are optimizing the design. Now the third layer is simulation driven design, where you are doing simulation for the topology optimization as well as you are doing simulation for your design modifications that you have done for LPBF based on the particular 3D printing process that you are going for. In this case, since LPBF, laser powder bed fusion, is the most widely adopted 3D printing process, and it is the most physically dynamic process because there is a melt pool involved and there are high temperatures involved. So simulation is very important. That's why I have made this model for LPBF, but the same model can be adopted for FDM and SLA process as well. Now let's talk about the third layer. We will go in a reverse order because the third layer encompasses everything: topology optimization or generative design, as well as the design for additive manufacturing guidelines as well. So what you need to do is, first you need to define your design specifications, that what is the performance that you are expecting out of your design. Then you need to create the CAD model. Then you need to establish the functional requirements, that what is the functional requirement, that means what is the tensile strength required, what is the material required. And at the same time you need to also define the constraints for the manufacturing process that you are going for, which is in this case LPBF, laser powder bed fusion. So there will be manufacturing constraints related to the process. There will be assembly constraints related to the final assembly of the component, where it is going to mate with what element it is going to interact. And then there will be constraints from the material side, because from design side you want some material, but every material will have its own set of challenges in 3D printing. So those challenges have to be incorporated. For example, it is easier to print aluminium than titanium. Your supports can be very weak in aluminium, but in titanium, your supports have to be really strong because titanium is a high stress material. Then you enter the design process. Once you have all these specifications ready, the constraints ready, you enter the design process. You do topology optimization. Once you receive the design of topology optimization, you try to validate it using FE analysis. And once it is done, then you go to the next stage, which is the uh, first layer, which is designed for LPBF, and do the similar kind of validation there. In case if you are not able to get the right design, then you should go back to your topology optimization and again change the parameters and try to create one more design of topology optimization or number of iterations till you are satisfied. Once you are satisfied with this process in design for LPBF, similar thing you have to do. If your simulation is not giving a good result based on LPBF, for example, I'm going to print this part in laser powder bed fusion of metal, then I do simulation for that process only by inputting all the process parameters. If I don't get the right input, then again I need to go back and modify my design based on the inputs that have been given by the simulation of the 3D printing process. Again, for 3D printing process simulation, there are particular softwares which are available, such as Simufact Additive, ANSYS Additive. In all that, you can do simulation for 3D printing. Now, once I have done these particular optimization simulation, satisfied with the result, then LPBF simulation, satisfied with the result, then I am ready with my redesigned structures and that can be 3D printed. Now let's take a deep dive. So what you see in green color is layer 3. What you see in peach color is layer 2, topology optimization. What you see in red color is layer 3, designed for LPB. Layer 1, that is designed for LPBF. Now, why design for LPBF is layer 1? Suppose you don't want to go to layer 2 and layer 3. Still, you can just do layer 1 and get some improvement in your 3D printing process. If you do layer 2, there will be more improvement. If you are doing complete layer 1, layer 2, layer 3, then your part will be highly optimized for 3D printing process. So let's try to understand what is there in the layer 2, which is topology optimization. We have already studied it in the previous section of the module in the workflow of topology optimization. But what does this layer model says about it? Let's try to understand that in form of a workflow. So you study the existing design boundary, then you go to the software module and input all the data. First thing is that you do FE analysis of the existing brake pedal. In order to do FEA of the existing brake pedal design, you need to consider all the material and its properties as well, and also the loads and constraints. So all of this you can input in the software. Then you specify the design and non-design space. Now this depends, for this you need the inputs from your assembly as well. What are the features for assembly? Then you maximize the design space without conflicting functional requirements. This is called as defeaturing. So basically, you try to give your software the maximum design space, maximum area to play around with. If you give maximum design space, your design will be optimized design will be uh, very efficient. If you limit the design space itself, then the software will not have much area to play around with. Then the software runs the topology optimization algorithm, and once you have that topology optimized data with you, you smoothen it using polynerves in Altair Inspire. And then the same software platform will give you an FE analysis of the topology optimization. Now till layer 2, we have optimized the part, but we have not yet given the major considerations of 3D printing that we have discussed in the previous section of the module. So we go to layer 3 now, layer 1 now, sorry, layer 1, layer 3 is the complete layer. In layer 1, what we are doing, we are taking the CAD input first. In that CAD input, we are incorporating everything like what is the minimum feature size we are studying. We are seeing what are the fillets and chamfers where we can give to avoid overhangs. And also quality of STL file is important. Now, all these considerations will help you in making a good quality part. Now, when you have the right CAD data ready, then you go to the process parameters stage where you define process parameters such as layer thickness, because your layer thickness will decide that what is the minimum features that you can produce as well as what is the surface roughness. Higher layer thickness, higher surface rough, lower surface, higher layer thickness, higher surface roughness, lower layer thickness, lower surface roughness. This is something that we studied in our workflow module. Then you also have to consider some recoating forces. As I explained to you in the first module, that recoating is spreading of powder particles using a knife-like material, knife edge material. So this recoater exerts force on the part that has already been printed, the layers beneath. So it is very important that you take the recoating forces into account. Now, when you have achieved the right CAD model, you have done process parameter simulation, then you do the right part orientation, then you do all of this can be simulated in a platform. If there are deviations, then you can do one more round of simulation. If there are no deviations, you can go ahead and say, yes, I have achieved my particular design solution. Also, this voxel based simulation, why I've said it's a FE simulation only, finite element analysis, but the element used here is a voxel. So we can clarify this later on, that what does a voxel means. You can write to me, I can explain in detail, but it is for your understanding, it is just an element that is being used to do finite element simulation. Now, very quickly, we will try to see that the brake pedal for which I have designed this 3-layer approach, this particular case study, what was it? So it is the brake pedal for a Formula student car. What you see here, they are students from Ramaiah University. And then once you have now why I'm showing this car, because you need to study this car in order to understand the assembly constraints. Then you select the material. These are the basic properties like mechanical strength and chemical composition that you need to study about the material. Then you also need to study where the part is being assembled. So this is the existing brake pedal that we are going to topology optimize. So now this existing brake pedal uh, is being assembled with multiple components. So all wherever assembly is happening, we have assembly constraint. That area has to be designated as non-design space. Also in this study, you will find out the maximum load that is being applied, where it is being applied, and what is the nature of the load and magnitude of the load. And you will enter these parameters in the software. So when we want to study everything, your whole assembly helps you a lot. So this is the chassis of the Formula student car. This is called a space frame chassis. And this is the CAD model of the assembly. So the CAD, not just the CAD model of the part is required for topology optimization or simulation driven design. Also, your assembly constraints are required. So you take the whole assembly CAD model with you. Now, what you see here, this is the de-featured. I told you about de-featured. So the part here looks like something else, but we have de-featured it and developed into a solid work model so that we give maximum area or maximum volume for the optimization software to play around with. And this is the very basic workflow that we did for this brake pedal. Then you do voxel based FEA, where the element used for finite element analysis is voxel, and for in this case there was option of using two orientations. So it was decided based on the process simulation that which will be the most optimum orientation to print the part. Then this was the result that they achieved from this to this. You can see that there has been reduction of more than 50% in the part, around 50% in the part, from 810 to 422 grams. The maximum displacement that was coming earlier for this part was 3 mm, and now it has reduced to 0.5 mm. So it is more stiffer. Even after reducing the weight, it is more stiffer. That is the advantage of topology optimization and simulation driven design. And the factor of safety has increased from 1.1 to 1.8. So it is a better design and a more efficient design as compared to this previous counterpart. So I hope you understood very clearly using this brake pedal, that how does topology, how does the three layer approach for simulation driven design works. In layer 1 we do basic design modifications, layer 2 we do topology optimization or generative design, in layer 3 we consider all the process simulation, topology optimization, simulation, and then we conclude on the final design. I hope this ideology helps in you in designing very good parts for 3D printing. Thank you, and we will see you in the next module of this course. Hi everyone, welcome back to the course Role of 3D Printing in Industry 4.0. And in this module, we will learn about digital inventory and digital warehouse. So these two are slightly different phenomena or slightly different, I would say, concepts. And we will try to understand what is the difference between two of them and where they exist in the manufacturing space and how they are related to Industry 4.0 and 3D printing. So in this module, we will be looking at topics such as what is digital inventory, and then advantages of digital inventory. Why do we need to have digital inventory? Why it is such a popular concept? And then we will try to understand that what is digital warehousing and how is additive manufacturing an important, I would say, concept in the field of digital warehousing. Then we will talk about examples of digital warehouse. We will see some case studies and we will see the software platforms which are enabling this concept of digital warehouse. So let's start learning about what is digital inventory. Digital inventory is uh, nothing but digitizing your whole inventory concepts. So what is an inventory? You have certain list in your stores, or you have certain items stored in your store which you will ship to any other department in your organization or to a customer as of when required. So you don't want to uh, take some time in manufacturing these components. You want to manufacture this, you want to make sure that the components when required by the customer, or any item which is required by the customer, it reaches at the right time. So that is why an inventory is maintained. Now what is a digital inventory is that you are using digital technologies to track and manage these inventory levels, like which item is how much. All these things is being stored in the digital data, and anyone can have access through a laptop or through their phones, or basically through uh, digital systems. Now in order to create digital inventory, it is necessary to have a software which will keep a track of all these items in the inventory. Again, when I say inventory, it is a list of items stored within a company which will be supplied to the customer whenever there will be a requirement, or it can be pre-planned. Now, when you have to supply these components and you want it to do in a digitized way, then it is necessary that the software talks to the hardware which automates this complete process of inventory management. For example, when the items in the inventory are moving in or moving out, it has to be automated. The hardware needs to be there, which will automate all this process. And that hardware will talk to the software, and the software will tell the hardware, okay, this is the time now. Today on this date at this time, this inventory has to move. So basically, in a real time, we are trying to maintain the stock levels and deliver them as per requirement. Now, it is also important that the software and hardware together collaborate, and they help in producing these components wherever the uh, inventory level is low for a particular item. So you need to produce them on demand. Now 3D printing helps in doing that in a very big way, but that's a completely different concept. That is what we call digital warehousing. So please don't confuse digital inventory with digital warehousing. Digital warehousing we will be covering in the next few slides. Now a digital inventory, it helps a supply chain manager to take more informed decisions. So if a supply chain manager is knowing in a better way
and at all the time he's having the data, not just data of today, data of present, past and future, that how much inventory I will have. So he can take more informed decisions related to the supply chain. Supply chain is nothing but the movement of goods. Now, this is the basic flow chart of the digital inventory system, where you will see there are three systems. There is an ERP here. There is an ERP here. And what does ERP does is that ERP is the software, enterprise software, which will take orders online, and then based on the orders which are being confirmed online, it will provide the pricing and the lead time to the 3D printing vendor. Okay, okay, this is the order that I am having, you please start producing these items, and this item should be delivered in certain amount of time, because this is the time period that I have committed to my customer or to my department. Now another now, since this ERP is doing the job of communication, it's a systematic software which will help you in transferring data from one place to another in terms of order creation, timeline and pricing. Now when these parts have to be made, then definitely there is digital data required. So that digital data part which is required for manufacturing any component, that is taken care by the CAD or PDM software. We also call it as PLM software. So now this software will be having the desired data, and it will generate the data into a format which is suitable for 3D printing, that we have discussed in the previous sections. Now once everything is done, the digital inventory system will send a confirmed print order to the manufacturing system, MES, manufacturing enterprise system. Now this manufacturing engineering system will actually produce the order, and while producing the order, it will communicate real-time data back to the digital inventory system. So in order to have a successful digital inventory system, ERP, MES and CAD PDM software, they work hand in hand. Now, why do we need to have digital inventory? So the basic gist is that the supply chain manager should be more informed about the inventory levels, and he should be able to optimize the supply chain. But let's look at the advantages one by one. So the first benefit that we will talk about is accurate inventory tracking. So one exactly knows that how much inventory level he is maintaining, and uh, based on that he can take the accurate decision that when the parts have to be manufactured or when the parts have to be shipped. Based on that, each and every process will be decided. Then we have efficient order fulfillment. So for example, if a customer is placing an order and the committed delivery time is 2 days or 3 days, then digital inventory enables one to actually produce the component in such a time frame that it will be delivered to the person in 2 days. So the manager or the person who is responsible for manufacturing these products, he will have a clear list of items and a date allotted against it, that when this part has to be manufactured. So that is the advantage in terms of order fulfillment. Your customer satisfaction becomes very high if you are doing an efficient order fulfillment. Then it helps us in an improved forecasting, not just in terms of week, days or years. In terms of 4 or 5 years also, we can plan the manufacturing, and we can actually do this based on the demand patterns. So based on the previous data, you can set up a demand pattern, analyze that data, set up a demand pattern, and give instructions to your manufacturing execution system that, okay, in this month I need this much, in the next month I need this much, or in the next year I need this much. So you can actually adjust your production levels based on the data patterns that you have analyzed, and created a forecast based on that. So you will be able to help your customers better. And then we have supply chain optimization. So you exactly know at which stage of the supply chain you need how many parts, how many components, and this will help you in reducing the lead time, improving the delivery time, reduce the cost also. You will not be manufacturing surplus. So that was about digital inventory. And in the next module, in the next section of this module, we will learn about the digital warehousing concepts, which is a very interesting concept, and it relies largely on 3D printing.
So see you in the next module. So in the previous section, we learned about digital inventory, which is basically digitizing the physical inventory. But now we are going to learn about digital warehouse. And what is the difference between a digital warehouse and digital inventory is that in a digital warehouse, you are not having the physical inventory at all. So whatever items you want to have in your inventory, you are actually having those items only in the form of digital data. And then you produce those items through digital manufacturing techniques. In this case, we are using the most popular technique to understand digital warehouse, which is additive manufacturing. And the concept of digital warehouse has only emerged after the additive manufacturing techniques getting so much popularity amongst the manufacturing industry. So let's try to understand how the concept of digital warehousing works. So the first part is uh, selection of the appropriate part for 3D printing. So not all the components which you want to have in your inventory will be suitable for 3D printing. So first you need to screen a plethora of components, and then you need to reach the certain set of components. A decision making has to be made based on certain decisions that we have learned in the previous modules, the factors which makes a part more favorable for 3D printing, and then those parts are converted into a digital environment. So basically, if I have a 2D drawing of the part, it will be converted into a CAD model. If I'm already having a CAD model, it will be stored in the digital space on the cloud basically. And if I'm having a physical part, then we need to do 3D scanning or reverse engineering and develop the CAD model of the part, and then store all the information such as the tolerances at which the part needs to be produced, the quality aspects, and the material information. All this needs to be stored in the digital environment. And when this all of this portion is done, then what we need to do is we need to validate those components by actually producing them through the most appropriate 3D printing process. Now we learned in the previous modules that there are multiple 3D printing processes available in the industry. So which will be the most suitable 3D printing process which will adhere to the quality requirements based on the end application of the component. So this validation is also a very important process. And once this validation is done, then you get the right part, and the part is ready to be delivered. So let's look at the definition of the digital warehousing. That a digital warehouse with respect to three additive manufacturing solutions refers to a centralized repository or database that stores only digital files such as the 3D model and related specifications such as materials, so that whenever it is required or whenever it is demanded by the customer, the parts can be manufactured using in no time. And also basically this digital warehousing is nothing but a catalog of digital models where you can go select which one you want, what to print, when to print, and most of this is happening in an automated manner. That is another aspect of digital warehousing. So now, for example, when you look at this 2D drawing on your screen, there are softwares available in the industry which can create, just by scanning this 2D drawing, you give the 2D drawing as an input and it will create 3D model as a output, and then that 3D model can be stored in the cloud so that whenever required in any part of the world, it can be printed using additive manufacturing. So not only that, yeah, not only that. In fact, when the CAD model is created of the part,
You can input 100 of CAD models in the software, such as 3Your Mind offers such a software. You can go on the net and search more about 3Your Mind, and 3Your Mind can tell you that which component is suitable for 3D printing and it should be in your digital inventory, and which component is not suitable for being in your digital inventory. And like this, you can actually create inventory of components which are very much suitable for 3D printing and produce them on demand using 3D printing techniques. So all of you can see this image and you can relate to it. It is nothing but the nozzle which comes as the opening of the vacuum cleaner. So the vacuum cleaner company is from US, Miley, and what Miley is doing is that uh, Miley offers printing of spare parts and accessories which customers can print if they have a 3D printing in-house, or they can go to the nearest 3D printing bureau with this CAD model, and which is available on the cloud, digitally available, and digitally stored, and you can actually use any service bureau near to your house to print this part. So you don't actually need to order this part from Miley. Now, conventionally, when customers used to order this part from Miley, they will get the part in 7 days, 8 days, 10 days, depending on what location they are, how far they are from the warehouse, actual warehouse of the physical warehouse of the company. But in no time, they can produce these parts using the nearest 3D printer available to them. So this is the concept of digital warehousing, where uh, it is applicable to an used case. We will have a look at one more case study. So Daimler is a very popular automotive OEM, and they are known for trucks and buses. So Daimler has basically set up these distributed manufacturing centers. So rather than having a centralized warehouse from where all the parts will be supplied, which is usually at the factory, this distributed manufacturing sector can be set up at multiple locations, and they can 3D print spare parts. They can 3D print spare parts using the digitally stored CAD data from the cloud. So if a customer needs anything, they goes to these uh, decentralized manufacturing units. They need not order it from the centralized manufacturing unit or centralized factory, and these spare parts demand can be met in no time by Daimler. So huge automotive giant like Daimler is also using digital warehousing concept to promote distributed manufacturing, so that the time taken for the end part to reach the customer reduces. Now, we have seen the case study, so the benefits are very clear. Your cost is reduced. You don't need to have a regular setup of physical inventory. So when you need, then only you produce. Like this, you are saving lot of components which are otherwise stored in the inventory physically. But what if the customer doesn't order them? If the customer doesn't order them, then they will go waste, because they will have a shelf life. And after their shelf life is over, you have to throw them out. So you only produce on demand, and like that, you are able to reduce a lot of cost. Then you can build faster supply chains. So if the central factory is 500 kilometers away from the actual place where the demand has been created, then it will take certain time for the part to travel that 500 kilometers. Whereas if the distributed manufacturing center is only within 50 kilometers or 100 kilometers radius of that particular actual place of demand, then the part can reach in a much lesser time. So your supply chain is more resilient and faster. You can enable low volume production. So using these distributed manufacturing, you can actually you need not set up, you need not run your factories only when 1,000 pieces are required. So when conventional warehouses or physical warehouses, what we do is we produce the number of components which makes economic justice to the manufacturing process. So if I decide to make 3,000 parts, then 3,000 parts will be stored in the inventory. Whereas here, I am producing on demand. If I have to make 10 parts, I'll make only 10 parts. That is the advantage of 3D printing. And
That is the advantage of having a distributed manufacturing functionality. So these benefits you have also studied in the previous modules where we were talking about the advantages of industry 4.0 and advantages of 3D printing. So all of this inline together creates the customer to enable low volume production. Then we have lower inventories. As I told you that if your parts shelf life are over, then that is waste of inventory. So we are eliminating this standing inventory. Standing inventory is basically the inventory items which are ordered in less number. Not all the spare parts for a certain particular product or particular car or particular truck or bus will be required in equal demand. Certain spare parts will have more consumption, and certain spare parts will have a more standing inventory. They will be ordered less. So you can eliminate the need of standing inventory here. And obviously decentralized manufacturing, you can produce the parts near to the actual center, what we studied in the our case study of Daimler. So that was about digital warehousing. And please start looking around and try to find the OEMs which are offering you the benefit of digital manufacturing. In the next module, we will look at some of the practical use cases, some of the softwares which are enabling the digital warehousing concepts. Thank you. So I hope you have understood the concept of digital warehouse and the concept of a digital inventory. Like just for a recap, a digital inventory is making the physical inventory digitized using digital technologies to manage and run physical inventories, whereas a digital warehouses, uh, there is absolutely no need of having physical inventory. All your inventory will be only in the form of digital data on the cloud. For example, you will not have physical parts, you will have only CAD models of those parts uploaded on the cloud, and then they will be manufactured using the 3D printing methods, because that is the fastest method to produce components, as we have learned earlier. So let's look at some examples which are globally renowned examples. But before moving there, we need to understand, like on your screen you can see there are multiple components. So out of these components, you need to look at each and every component, that which is the right part, and that has to be uploaded to the digital warehouse. And as explained earlier, there are certain softwares which are enabling you with that feature. So in this module, we will learn about those particular softwares which are enabling you to select the right part and then execute the whole concept of digital warehousing. So the first one is 3Your Mind. 3Your Mind is basically digital invent. They also call themselves digital inventory, but it is not. Please do not confuse yourself. They actually take the whole physical inventory in account. They do the evaluation of the physical inventory, then create the most suitable set of components which are favorable for additive manufacturing, and then they make the CAD data for that we will understand. And this is being used by US military and heavy industries in the US uh, to enable agile manufacturing. So basically they make software suites which enable agile manufacturing, and they give the freedom to the supply chain manager or supply chain engineer executive to maintain the spare parts for ships, submarines, and production lines in a much efficient manner. So this particular, what 3Your Mind is doing is that they are converting your physical inventory into a digital inventory. For that, a lot of software is involved. For that, a lot of conversion of physical data to digital data is involved. For all that, 3Your Mind is providing softwares. So let's try to understand how the software suite of 3Your Mind works, because this is how ideally a digital warehousing software should work. Now someone can develop this digital warehousing software in-house, or someone can go to 3Your Mind and ask them to make a customized software for them. So they provide all these services. So the first part of the digital warehousing software suite is Agile Product Lifecycle Management, which is nothing but a PLM software. Now, PLM is, you can say, basically a design software with many more features in that. So what are those features which they should have? Uh, they should be able, there should be an option of creating digital inventory. What digital inventory in this regard means, that creating the digitization of all the physical inventory that is available, including each and every information, the part data, the digital CAD model, the material data, the quality aspects, the qualification criteria, everything. Then it should have the facility, or it should have the provision to screen the components more suitable for 3D printing. It might not always be 3D printing. You can choose the manufacturing method. For example, if your components are more suitable for laser cutting, which is again a digital manufacturing technique, then the software should have provision to screen the components for uh, laser cutting. Then, based on your 3D printing technique or the process that you have chosen, it should be able to optimize the orientation of the part and then send the file directly through the manufacturing execution system for processing. So basically, all the work should happen in this PLM software. That is why it is called product life cycle. All the aspects related to the product life cycle are evaluated in this. Then the second part of this software is Agile Enterprise Resource Planning, ERP. Now, in enterprise resource planning, what it does is it it automates your order creation. So there are ERP softwares which most of the people are using in the industry 3.0 concept. In industry 4.0, the ERP becomes agile by automating order creation process, by creating an automatic material comparison, how much material is there, which material is required, which is the most suitable material, which is the alternative material, what properties will it give. All these things are being done in the software. How much material is required for manufacturing that component, how much is there in stock, everything is automated and happening in the agile ERP software. Then the pricing. Now, if a component has to be made, definitely a quotation or a costing has to be sent to the customer for that. Even that part will be taken care by the ERP software. Then we have, in the end, the Agile Manufacturing Execution System, which is an MES. Initially, in the first module, I misread MES as mispronounced MES as Manufacturing Engineering Services. It is Manufacturing Execution System. Basically, your manufacturing is happening in a digital environment, an environment enabled by robotics and IoT. Now, what my MES does is it will have live part tracking. Okay, which part is being manufactured at which machine, what is the stage of the machine, how many days it will take, and right now how much part has been completed, 30, 40, 50, 60%. All the data will be communicated to the supply chain manager or to the admin in real time. Then we have quality assurance technique. So using a lot of sensors integrated with IoT, the sensor data is communicated to the admin or the supply chain manager or the quality manager in this regard, that okay, the part is being manufactured with this quality aspects. You wanted to monitor the temperature in which the part is being manufactured. This is what, for example, in laser powder bed fusion, we learned that inert gas atmosphere is an important parameter. So inert gas atmosphere will be continuously monitored for laser powder bed fusion, and it will be communicated to the admin directly. Data standardization. So all the data which is being gathered during the manufacturing, it is being noted, but it has to be analyzed and it has to be uh, like sorted out for the good quality parts and bad quality parts. And then you have to create a standard form of data which will always be used in order to manufacture a good quality part. So this is what an agile manufacturing execution system does. So an ideal software, just like TheoRmind, should have all these units. Now we'll talk about one more example, AMFG additive MES. Now AMFG additive MES, what it does is, apart from, so it is definitely having all these three components which we just discussed in the previous slide for TheoRmind. But apart from that, this UK based startup, it also provides a software which you can customize based on your additive manufacturing needs or customer needs. So every
even though if two organizations are using same additive manufacturing process, their process flow before the additive manufacturing process and after the additive manufacturing process, which we call as post processing, might differ. So based on that, this software uh, allows the users to customize that process flow and make it more effective. So these are the value additions that AMFG additive MES is doing in comparison to 3-Or Mind. But it is also performing all the functions which 3-Or Mind has been performing, what we discussed in the previous slide. So let's have a look at the last and one more, Ivaldi. Ivaldi. Ivaldi, what it does is that it comes with a specific tool which is a material technology location comparison tool. For example, if a customer wants to print a part in Los Angeles, and uh, the tool will tell that, okay, this is the model that you want to print, these are the manufacturers which are nearest to you, and these are the material options which is suitable for your component and is available with them. So you can actually, it gives you multiple options in terms of the nearest location or location distance wise, and in terms of the material, that which material you would want to print it. So the user can go and select, okay, this is the nearest center to me, these are the material options they are having, and I want to print in so and so material. So it is really making the manufacturing so efficient based on your priority, whether you want it fast or you want it in the most suitable material or what material you can actually choose. So it is not just about making it faster, it is also making it more compatible to the end application. So again, a disclaimer that Ivaldi is also performing all those three functions which a particular digital warehousing software suite should have. So I hope you are very clear now what digital warehousing means with these three examples. I request you to kindly go back and explore these three platforms, Ivaldi, AMFG Additive MES, and 3-Or Mind. So once you explore them online, you will be able to understand better. And if there are any doubts, we are always there. Thank you and have a great day.
Welcome to the module Quality Considerations in 3D Printing. And in this module, we will learn about the basic quality aspects that we need to consider during our 3D printing project or while 3D printing a component. So the common topics that we'll be discovering in this module is the defects that we face in various 3D printing processes, such as polymer, different kind of polymer processes, and then in metal 3D printing, what is the basic defect that we usually encounter. Then we will be talking about the basic quality controls. So what are the aspects that needs control in when quality is under considerations during 3D printing? And then we will talk about destructive and non-destructive testing. So basically these are the two methods which are evaluated to make sure that your 3D printing part is coming right or the strength of the part is good enough for your end application. Then we will talk about inspection of 3D printed parts. So when we say inspection, this has to do with the dimensional accuracy of the parts that you have printed. So let's get started. The first topic, defects in 3D printing. So what are the various kind of defects that we face in FDM? So by now we have covered multiple types of techniques of 3D printing, which is FDM, SLA, SLS, polyjet, metal 3D printing, laser powder bed fusion, and others. So let's have a look at the defects that they produce. So what you see on your screen is a part 3D printed through FDM technique. And if you will notice at the bottom portion, this particular portion, you will see that the corner has curled up. So that is how the name of this basic defect is defined. It is called as warping. So basically there is warpage of components at certain areas. It usually happens at the corners. Now, all the 3D printing processes that we have learned, let's have a recap on the very basic method of transforming material to some form. It is done by using some form of energy. Now that energy can be heat or that energy can be laser. Now in all the cases, any kind of energy which is given, basically it is resulting into heat. So basically any material from the raw material shape is heated to form the desired shape. Now when it cools down, it shows some shrinkage, and when it is shrinking, it also has some stresses. Usually these stresses are very high at the corner points. That is why the parts, they tend to uh, curl up. Now what is the basic cause of warping is that whenever you have poor adhesion to your base plate, when we are printing FDM components, we are printing on a base plate. Whenever the part is not uh, stick properly to the base plate, the adhesion is not proper, then because of these stresses, the thermal stresses, it may end up in curling up or warping. So warpage is a very basic technique, a very basic defect that we see due to thermal contraction. Now the very common FDM materials are ABS and nylon. Now while they shrink, they show thermal contraction. So in almost all the FDM materials, uh, this phenomena is there, but in ABS and nylon, it is slightly more. So when you're printing ABS and nylons, you need to make sure that your parts are adhered in a very proper manner to the base plate so that they don't show any warpage. Then another defect that you see on your screen is cracking. Now, cracking is again a form of warpage or delamination, you can say, but it happens in between the parts. So when two layers, they don't stick to each other, what happened that because of stresses, they show some, I would say, non-adherence. They do not come in contact with each other, they tend to warp, and that's why we see such kind of cracking. Now cracking is again due to poor adhesion between layers and also thermal shrinkages. So most of the defects will be because of thermal shrinkages or thermal contraction. Another defect in FDM is uh, stringing. Now stringing is basically when instead of uh, your nozzle moves from one feature to another to print that feature, it is not cooled down properly. And when it moves to the other feature, it leaves a string of the material which is attached to the part as well as to the nozzle. Now, there can be multiple reasons. One of the very basic reason for stringing is when the print temperature is too high. That means you are not giving proper cooling time to your nozzle when it is, and before cooling, it is moving from one place to another, causing the stringing effect. So that is why you need to make sure that your print temperature is not very high, and you are giving enough cooling time for the nozzle to move from one place to another. Then again, one more defect. This is curling. Now, curling is slightly related to warpage, but curling will happen not because of thermal stresses, but because of overheating of the material. So when your print temperature is too high and your cooling is not happening, then your part will remain for a longer time in the molten stage. And wherever it has remained for a longer time in the molten stage, what will happen that when you print on top of that, your printing is not proper. So it will result in curling. Now let's talk about SLS and MJF. Again, this defect that you see is from SLS technology, and it is known as delamination. Now, delamination is again because of thermal stresses. Now, all what happens that when two layers are not sintered or adhered to each other, then because of the thermal stresses, when the stress is higher than the yield strength of the material, they tend to detach from each other. These two layers do not attach to each other, instead they detach from each other, and thus resulting in delamination. Now remember, SLS, MJF, in MJF what we do, we use a curing head to provide heat to the sintered part, whereas in SLS we use a laser to sinter the component. So in both the cases, you will face such delamination effects. Then we have warping in SLS and MJF as well. And you can see here also the corners are lifted up. So when the corners lift up, that means they have not been attached properly to the previous layer, or the temperature is too high, and because of the straight portion that should be there in the part, we are experiencing a curved portion. So what we will see is that the part dimensions have deviated what you have given in the model. So again, your part will be rejected. Now, when we talk about LPF metal, again, the reason for defects here is again the same: improper cooling or excessive heating or high thermal stresses, but the end effect might be completely different. So what happens in laser powder bed fusion of metal, or we can say direct metal laser sintering that we studied, that it is the laser is melting the powder particles. So when it melts, there can be high energy which you are giving to melt, or there can be low energy. You exactly need to give the appropriate amount of energy which will result into dense metal. But sometimes we don't get dense metal, we get porosity. You can see different kind of porosity, regular and irregular. So regular porosity, spherical porosity, is when you have high energy input. So what happens that some of the alloying elements, they evaporate in gaseous form. And when they evaporate in gaseous form, these gas particles, when they evaporate, they leave spherical force behind. And when your energy is low, you are giving low energy input to melt the metal powder particles in LPBF, then you will get irregular shape, because that area represents unmelted powder. And when this, what you see on a screen, is a microscopic study of a specimen made in LPBF. So when you observe under microscope, you will see regular, irregular. Irregular corresponds to insufficient melting, and regular corresponds to very high energy given during melting. Then again, we can see delamination in metals also. Now, what you see on your screen here, we have support structures, and then we have the part. Now, when the thermal stresses are too high and the bonding with the base plate or the support structure is not good enough, the metal part that you have built, that tends to delaminate from the support structures. So again, this is because of high stresses. So remember, most of the defects that we get in any of the 3D printing process is because of high stresses generated due to thermal contraction, because we are using thermal energy to transform the part into your desired shape. So thank you, and we will meet in the next module, and we will learn about the quality considerations. Welcome back to the module Quality Considerations in 3D Printing. And now we will learn about the various quality control measures that we can take in 3D printing. So moving forward, the first measure that we need to take as a quality control measure is design validation. So what you need to do is you need to validate your design. Now, this design validation means also validating your design data. There are multiple aspects of it, such as you validating your features, you validating your tolerances, you validating your STL file, and you validating your minimum dimensions, critical dimensions. For example, in a 3D printing process, you can print only 0.3 mm and you have a feature of 0.1 mm in your design. So definitely that design cannot be printed. So this design validation is a very important process that needs to be done during your designing process itself, so that you can design the right part for the right 3D printing process. Then we talk about in situ process monitoring or in process monitoring. So basically what you want to do is, I told you that temperature can be one of the reasons for generating most of the defects. So when you are doing a 3D printing process, you need to monitor all the important parameters. And you also need to make some coupons and specimens to validate your printing process. So basically, when you are making a part and you don't want to destroy the part, but still you want to do the tensile testing of the part or stress rupture testing, that we will study in detail what kind of testing can be done, destructive testing. So in order to do any kind of destructive testing, you need the coupons or the test specimens belonging or corresponding to that particular destructive testing to be built with the build. This is one way of doing in situ monitoring, and the other way is to monitor all the specific process parameters. And sometimes this in situ process monitoring or in process monitoring can also be done by using image analysis or a video analysis during the printing of component itself. Then the third part of it is when the printing is done, which is post process inspection. Now, this is basically just like any other engineering process where you want to analyze or inspect the component that you have manufactured through that engineering process. In this case, it happens to be a 3D printing process. That can be measurement of critical features, dimension measurements, or that can be 3D scanning. You actually want to 3D scan the whole part. We will discuss in this module what is 3D scanning. And through 3D scanning, basically you are not only trying to measure the critical dimensions, but you generate the replica of a component in the CAD environment and then overlap with the CAD model and check how much deviations you have got. Now all the organic surfaces which cannot be measured through vernier caliper or micrometer, there we need to go for 3D scanning. Then there is non-destructive testing. So as I told you, during in situ process monitoring, we need to build some coupons for destructive testing. But once you have made the part, you can actually take the part through a series of non-destructive processes or very basic non-destructive process such as X-ray. And then you can actually check whether you have some porosity or cracks inside the part. So there are other methods of also of non-destructive testing which can be taken into consideration. But first you need to analyze your end application. What is your end application? And based on that, you decide what kind of destructive testing you need to go for, non-destructive testing you need to go for. And you also need to analyze your features, what kind of features you are having in the component. If it is organic features, you can do it through measurement using vernier caliper. If it is inorganic features or I would say a more biomimic feature, then you need to go for 3D scan. So let's talk in detail about design validation. What do we need to consider in design validation? So before printing, you have to check the design because you might have some errors, inconsistencies, or some compatibility issues with the chosen material. And in order to do this, you need to be clear with your 3D printing method. That is why we have learned all the 3D printing techniques so much in detail in the previous modules. So you need to know which 3D printing process you are going to use and which material you are going to use in that 3D printing process. And based on that, you have to validate your design. Now, there are some 4-5 kinds of validations that you need to perform. First is your geometric validation and STL file validation. So you need to check what is my minimum feature size, what is the wall thickness I'm trying to print, and if my STL file is having any error. There are certain errors that you get in an STL file, and if your STL file is having those errors, then the same errors will be replicated in your printing process, and your print might fail also sometimes. Or even if the print doesn't fail, when you take the part out, you will not be able to use that part for the end application for which you had designed and printed the part. Then there is checking of dimension and tolerances. Now, for example, if you want to print a particular part with 0.1 mm tolerance and you choose a 3D printing technology which gives you the tolerance of 0.2 mm, 0.3 mm, which is the case with most of the 3D printing technologies, then there is no use of doing it. Or if you want to achieve some tolerances which is 0.05, no 3D printing can produce that 0.05 tolerance. So you need to consider some post-process technique which you need to account for in the design phase itself. So checking the dimension and tolerances are very critical. For example, if you want to make a hole of 0.1 mm, which cannot be made in any 3D printing process.
So you need to go back and check if you can make a 0.3 mm hole or 0.4 mm hole, or you don't need to make the hole at all. Later on, you need to develop that hole in any post-processing operation. Then once you have done that, you need to validate the functionality and performance. Functionality validation is done by the FE analysis of the part in your conventional simulation software such as ANSYS Workbench. And then performance has to be validated there as well. Also, you can do simulation for the particular 3D printing process, that if I take this part to this 3D printing process, what are the problems that can be encountered? There are multiple softwares available now, such as Simufact Additive, Fusion 360, Materialize Magics, which enable the user to actually simulate the component for that particular manufacturing process. Then yeah, this is what we were talking about, simulate printing and assembly. Now for example, if you have an assembly feature in your part and you have, it's a movable, two movable parts are printed together, and in order to achieve that movability you need to have 0.1 mm gap. Then you need to check whether 0.1 mm gap will be produced in the printing process or not. So these are the basic design validation techniques that we need to do. I will just give you an example of geometric validation, which is like fixing the STL file before 3D printing. So if you see in this file, there are multiple shells, there are holes, there are floating angles. These are the some of the basic defects that we get in the STL file. Now, if these defects are still there in your STL file while you have taken up for printing, your printing will fail. So what you need to do is, what you see on your right hand side, this is a screenshot from Materialize Magics, where you get a fix wizard which detects all the problems in your file, and then you can manually or automatically using the software algorithm fix it. Now when we talk about dimensions and tolerances, uh, every 3D printing process has got a different kind of dimension and tolerance. For example, multi-jet fusion, which is MJF process, it has got a tolerance of plus minus 0.3%. So basically for 100 mm length, you are getting plus minus 0.2 mm tolerance. Then what is the size, maximum size that your 3D printer can accommodate? So in case of multi-jet fusion, it is 380 mm, 284 into 380. So this much big part you can make. Now in case if you're designing a bigger part, you have to split and plan the printing accordingly. So this is a part made in MGF. Then we talk about selective laser sintering. In selective laser sintering, again, we see that similar tolerances can be achieved around plus minus 0.3%, but it is slightly higher side when we talk about tolerance for SLS. We get for 100 mm, we get plus minus 0.3 tolerance, which is a bilateral tolerance. Then the maximum parts that can be made in SLS is around 340 into 340 into 605. This is one of the SLS part where you see that threads cannot be made properly, so they have used a copper insert which has been added in the part after printing. Then we have stereolithography, SLA, that we have studied as well. In SLA, you get the best possible tolerances amongst all the polymer 3D printing process, which is plus minus 0.2%. So it results into plus minus 0.2 mm for 100 mm. And the sizes that you can print in SLA are really big. There are really big SLA 3D printers available in the market. You can print up to 736 into 635 into 533 mm. Similar tolerances are there for FDM. It is very much similar to SLS. The parts that you can print are much bigger in FDM technology. It goes up to 914 into 610 into 914. So this is quite a large part. Then you have DMLS. In DMLS, which is basically a metal, you have slightly better tolerances than other processes. You can also get a good accuracy of plus minus 0.1 for 100 mm tolerance. And then parts can up to 400 into 400 into 400 can be printed here. Then in polyjet, you can get tolerance as good as 0.05 mm, which is 50 microns for 100 mm part, because polyjet is a very precise technology. So when I was saying you need to check for your 3D printing method and your design tolerances. Now for example, if you have to print a part in 0.05 and polymer,
then you will not go for SLA, you will go for polyjet. Now the parts that can be printed in polyjet currently are up to the size of 490 mm into 391 into 200 mm. Now let's talk about in-situ monitoring. Basically, in-situ monitoring is monitoring of all the process parameters using different kind of sensors. Now, one new thing that has come in the market is using cameras to analyze your parts when the printing process is going on. Now, there are certain things that you can detect very accurately. Then there are certain aspects that has medium detectability, and there are certain aspects that has low detectability. For example, you can easily detect a lack of fusion. You can easily detect if there is high amount of spatter generation in selective laser melting. Now this camera technique is largely used in laser powder bed fusion of metals, because those equipments are very expensive equipments, and even metal parts are expensive parts. So similarly, you can check for porosity, but it's the amount of porosity that you can detect is slightly on the lower side. Then you can check for the stress induced crack. Again, that comes, it's not necessary that you will be able to detect all the cracks. Then delamination. But now there are certain softwares or certain imaging methods with which you can also detect problems such as if there is anything wrong with the chemical composition, if there is anything wrong with the microstructure, or if there is any contamination in the part. So all these things can be detected. Their degree of detection may vary. So, but you can go on Google, and you can check in situ monitoring, and you can get a whole lot of data. This is a new research area, in situ monitoring. But the basic aspect of in situ monitoring is that you want to monitor all the process parameters which contribute to the quality of the part while printing. So thank you, and we will meet in the next module, where we will learn about the dimensional inspection of component and some techniques of destructive and non-destructive testing. Thank you. Welcome back to the last section of this module, where we are discussing about quality considerations in 3D printing. And in this section, we will be talking about destructive and non-destructive testing. So destructive testing is basically when you make a specimen along with your 3D printing, while you are 3D printing the part in the same build or in a different build, and then you test those specimen by destructing them. So if we talk about destructive testing, you can see that in this particular build, there are this particular is a hydraulic manifold which has been 3D printed for a aerospace application, which was done by Boeing. We have discussed this in the application sections of this course. And along with this, you will see multiple coupons that have been printed. Now these circular coupons that you see, they have been printed for a non-destructive testing, which is surface roughness measurement. So basically the end user wants to measure the surface roughness, how it is varying along with the varying angle of this circular pipe. Whereas all these other blocks that you see, they are for burst pressure testing, and there are certain blocks for hardness testing and impact testing. And there is a dumbbell type of component which is again for your tensile testing. So whatever testing you need to do on through destructive method, there are multiple sort of testings which include tensile test specimens. You can make tensile test specimens and do tensile testing on that. Then what you can do is stress rupture testing. Stress rupture is also done for components which are having application at high working temperature, 600 degrees, 700 degrees Celsius, or which go under stress a lot, and where creep is an important phenomena that you want to test. How much is the creep strength or stress rupture strength? Then there is burst pressure testing. So any component, for example, this hydraulic manifold that you see, it undergoes certain pressure when the fluid is flowing inside. Now, in order to make sure that your part is suitable for the burst pressure that you have designed, you need to do some validation while printing. So you print burst pressure testing coupons along with the part. Then we have fatigue testing. Then we have hardness testing. Hardness testing is basically Vickers hardness, Rockwell hardness, Brindle's hardness, and all of it can be done on a very simple coupon, a circular coupon or a cubic coupon, which you will put under the hardness testing machine. Now, the important point here is that for each kind of testing, you have ASTM standards defined, which you can easily access over the net. And you can also get the test specimen drawing required for that particular testing. So you need to design those specimens, and then you need to put those specimens along with your part in the build itself. So what you see on your screen is a build plate of metal 3D printing, LPBF, laser powder bed fusion, or DMLS. Uh, Now in this, multiple coupons have been built. Now let's have a look at some of the other builds also. Here also you will see that these are the parts. What you see on the left hand side, these are the parts that are being printed for actual use. But along with the part, the customer has, or sorry, the end user has printed multiple coupons in different directions. These are tensile test coupons, flat tensile test coupons, which are tested based on ASTM E8 standard. Now they have printed coupons in vertical direction. They have printed coupons in horizontal direction, lying flat on the bed. They have also printed coupons in different directions at different angles. You can see here. There are coupons at 45 degrees. There are coupons at 60 degrees with the base plate. Now, why do we do that? Because we know that 3D printing has got uh, an isotropic nature. So the properties that you achieve in X and Y are different. The properties that you achieve in Z height is different. So in order to account for all the different properties which are varying in different directions, you need to do coupon printing in multiple directions, and these coupons are then tested in a universal testing machine, which is very much suitable for tensile test specimens. So basically, you break the coupons. That is why it is called destructive. You destroy the coupons, and the point at it which gets destroyed, before that, until that point, you are measuring all the loads given to the part, and you get a stress strain curve. So this is in general applicable for any mechanical method, for forging, casting, machining. You can make such coupons in any manufacturing method which is considered under engineering manufacturing methods, and you can do the strength evaluation using a universal testing machine. Then one more thing that I would like to highlight is that in the previous build you saw there are flat tensile coupons, where in this they are making uh, cylinders, and then these cylinders will be uh, machined to dumbbell shape coupon, which is again another standard of tensile testing, and then these coupons will be tested in the universal testing machine. So here if you see, they have also numbered the coupons so that when you test a specific coupon or a specimen, you know that in which angle it was printed, and in which orientation it was printed, and at what location it was printed. So this gives you a full distribution of your base plate, like where I am getting what kind of mechanical strength. Is the strength same, or is it varying depending on the location? So these kind of testings are very much favored, because the cost involved here is very less when the testing is done. But yes, the costing of printing the coupons is quite higher. Then we talk about non-destructive testing. So destructive means destroying the specimen and testing the properties, basically the mechanical strength, whereas non-destructive testing is done to check if there is internal pore or any crack inside the part. So again, we take example of the same manifold which we saw in the first slide on the print bed. Now this is in the finished condition, assembled conditions, you can see. Now if I have to evaluate this part after printing, the destructive testing coupons are being made along with the part, and uh, they are a reflection of the part strength while printing, because they are being printed in the same process parameters using which is being used to print the part. But once the part has been printed and then you want to check which like if there is any crack or any defect in the part, then you can do an X-ray analysis or a CT scan analysis. So now here if you see, this part underwent CT scan, and the particular profiles have been inspected if there is any defect or not. So all the white areas that you see, that is metal, and the black is not metal. So if there is any black area appearing in between the white sections, that can be considered as a porosity or lack of fusion or overheating of the part, or if there is any crack inside the part, that can also be detected through these particular non-destructive techniques, which is commonly X-ray or CT scan. X-ray is a very affordable technique, but you get to know cracks and pores more than 0.05 or more than 0.1 mm inside the part, whereas in CT scan you can find out defects which are even smaller than 0.05. So here if you see, this is again an CT scan image of the same part but taken from a different angle. So that is also important, that the area which is of your focus, whether that is being covered in that particular angle or not. So this was done using a 300 kV micro focus X-ray source, which is manufactured by GE Inspection Technologies, and using that particular X-ray source, 300 kV micro focus X-ray source, GE Inspection Technologies performed CT scan on this manifold. Then let's talk about part inspection, which is measurement of the dimensions. That can be done using 3D scanning and CMM. Now, this is again a general phenomena. Any engineering part made through any manufacturing method can be checked or inspected using a 3D scanning and CMM. So, in order to understand how 3D scanning is helping us in inspection of the part, we will have a look at this video. So this is by Extia, where they are doing a con rod inspection. Con rod is a component used in your automotive industry, the connecting rod basically, which is connected to your piston. And this is the CMM machine which can produce components with an accuracy of 10 micron and a resolution of 100 microns. So in a very less amount of time, the data got scanned. Within seconds, within minutes, you can scan the data. Now, once you have the 3D scan data, what the software does is it allows you to measure each and every dimension, not only which is visible from outside. In fact, you can take cross sections of these dimensions and measure. Now here if you see, our concern should be the diameters of the connecting rod. So you can actually create a circle using the 3D scan data and measure the dia of the circle. Also, you can overlap the 3D scan model which has been generated by 3D scanning with the actual CAD model, which was the input for 3D printing or any other manufacturing process, in this case 3D printing, and it will give you the variation between that dimension and this dimension. So this is about 3D scanning, where it is being used for inspection. Now CMM is another process that is largely used in the engineering industry and manufacturing industry for inspection purpose. Now what does a CMM does is that by probing, it will take certain points. As you can see, it is taking certain points inside a hole, outside the hole, on the plane, along the edge of a plane. And using these points, you can create basic geometric features such as a cylinder, a plane, uh, a cone, a frustum, or a line. And using those lines, planes, or those, for example, if you have created a cylinder, you can measure the cylindricity, you can measure the dia, you can measure the center point of that cylinder. If you have created a plane, you can measure its parallelity with respect to the datum or other plane, and you can measure the multiple aspects of a line, such as how perpendicular line how that line is, what is the straightness of that line, and other features. So it basically again gives you an option of inputting your actual CAD model and then the data captured through CMM, and you can compare both to do the measurement. So with this, we come to an end of our quality considerations module. I hope you have a very basic understanding of now what are the quality considerations that we need to consider while 3D printing. And you can research more on like what applications require what kind of measurement and testing, what kind of quality considerations. But most of the considerations that we discuss in this module are common to all the applications. So thank you, and please explore all the other possibilities. If you have any doubts, you can anytime come back and uh, try to use this knowledge, implement this knowledge in your practical applications, and that will help you in learning. Thank you. Hello and welcome to the module Post-Processing for Additive Manufacturing for the course Role of 3D Printing in Industry 4.0. So post-processing is a very interesting and necessary activity for the parts which are 3D printed. So in this module, we will understand in deep about what is post-processing, what are the different techniques like and then we will talk about why do we need post-processing. Why is it exactly an important step in the 3D printing workflow? We will understand about those requirements, and then we will talk about the post processing for metal additive manufacturing specifically, because polymer 3D printing requires different set of post processing techniques, whereas metal 3D printing requires different sort of post processing techniques. So we will talk for metal and polymer in specific, that what are the post processing techniques involved for metal and polymer. So moving ahead, let's start with the first topic of this module, which is what is post-processing. So post-processing is basically any additional step that you need to do after 3D printing. Now, when we talk about the workflow of 3D printing or additive manufacturing, the workflow starts from the pre-processing of CAD data, which we have very well understood in the previous modules, how the CAD data has to be processed and what are the different considerations to be taken into picture. Now, after the pre-processing of CAD data, we actually go for the 3D printing. Now, once the part is 3D printed, then it goes through post-processing. So our module or this particular learning that we will have in the next 2-3 videos, that will be based on this post-processing aspect, which is the third aspect of the third step of the additive manufacturing workflow. And also uh, it is very important because when we are doing a post-processing or deciding upon the right post-processing operations, we need to take into consideration multiple factors. Now, those factors we will try to understand, and it, post-processing can basically refer to any process that we need to do after the part is printed, such as removing the support structures or removing some excess materials or improving the surface finish. So let's try to understand what are the different post-processing aspects that we need to cater to when the part is printed. So one of it can be support removal, basic support removal. We saw in the previous modules where we spoke about support structures which are required for certain processes such as selective stereolithography, SLA, and metal 3D printing, as well as for FDM supports are required. But these supports are something that you don't want in the part. They are not required based on the design and functionality of the part. So you need to remove them after the parts are printed because their job is done, and that is why they are called as the sacrificial structures used during printing. That would be the appropriate
definition of support structures. So you need to choose a post-processing method which will help you in removing those support structures. Then we talk about improving the surface finish using post-processing. Now, many 3D printing processes give a certain amount of support structures, a certain amount of surface roughness. Now, it may be that based on the end application, the surface roughness is not good enough and you need to improve upon it. Or when you are getting these line marks, you need to remove the line marks that have been developed through 3D printing. And to remove that, you need to go for a particular surface finishing technique. Then there is machining. Now, if you have provided some extra stock on a metal part, now machining is usually considered for metal 3D printed parts. Now, if you have provided some extra stock on the metal 3D printed part, which you need to remove after machining. This stock might be given for multiple purposes that we will understand in the next video. Okay, why do we need to give stock and why do we need to machining? But machining is basically removal of extra material which is not required as per the end application. Then we have heat treatment. Now, heat treatment is usually done to alter the mechanical properties or to alter the microstructure in metal 3D printing. Again, heat treatment is something related to metal 3D printed parts. Then we have joining. Now, sometimes uh, you would have built two parts, one single design in two different components, depending on multiple factors, maybe due to generation of support structures inside the part, or maybe due to the build volume is not allowing to print it in one go. So now you need to look at how to join these parts. So joining is particularly the word that we are using for polymer 3D printed parts. And when we talk about joining in metal, then definitely it has to be done through welding processes. There are multiple welding processes that can be done, can be used to join metal 3D printing part in the post-processing stage, such as TIG welding, MIG welding, robot-based laser welding. Multiple type of welding techniques can be used depending on the material and the part. And then one of the most mandatory post-processing step is powder removal for powder based techniques such as MJF, SLS and others. Now, when you have a hollow or a part which is having internal channels where the powder will be stuck in metal also, then you need to provide provision so that you can remove that powder. So powder removal has to be done after the parts are printed for powder based methods, including metal, laser powder bed fusion. Now, all these techniques that you see, they have to be planned well in advance during your pre-processing stage of the CAD data itself. This can include this planning can include your how you are going to remove the supports, how you are going to remove the powder, how you are going to improve the surface finish, and whatever is mentioned right now there, we just spoke of. So these are the post-processing techniques that we will be doing after a part is printed. Now let's think about the factors on which a post-processing technique is depending. So a post-processing technique basically depends on the printing technology that you are using, because depending on the printing technology, you will have a specific type of support structures which you need to remove. You will have a specific kind of surface finish, line marks, powder finish, matte grainy finish, depending on what kind of printing technology you are using. Then it also depends on the materials which are being used for 3D printing. Now, the material will tell the mechanical property and the material will also tell the kind of post-processing techniques that you can go for. For example, if you're doing thermoplastic 3D printing using FDM, you cannot do machining on that. Whereas if you are doing metal 3D printing, then you can do machining on that. Now, for certain metal 3D printed parts, depending on the material, welding might not be feasible, and for some, welding might be feasible. For some, a typical kind of welding should be used, and for some, another kind of welding should be used. So, material plays a very important role. Also, the heat treatment for metal 3D printing, the post processing heat treatment cycle is defined by the material that is being used. Then we talk about the powder removal techniques, part design and geometry, how we are going to remove the powder from inside. That depends like how small these cavities are. You might have to give a hole which will be plugged later through welding in order to allow the powder removal to be done. Then we talk about the end application. Now, based on the end application, you need to figure out what mechanical properties are required. Now, for example, a certain type of material in a certain type of printing technology is giving you some mechanical property or some tensile strength, to be precise. Let's talk of taking just an example. Now, if this tensile strength is not good enough for your end application, then you need to perform certain post-processing applications in order to match the tensile strength which is suitable for the end application. So these are the very crude description of the post-processing factors which will be taken into consideration before deciding upon any post-processing technique. In the next module, we will learn about why do we need post-processing. Basically, we will try to understand the limitations of the 3D printing techniques that uh, facilitate the post-processing requirements of any 3D printing workflow. Thank you and see you in the next module. Welcome to the second video of the module post-processing for additive manufacturing. And in this module, let's try to talk about why do we actually need post-processing. So in the previous section, we understood that post-processing is the third step in the process flow of additive manufacturing, but why is it so necessary? So the basic requirement of any post-processing technique, whether it be for any metal 3D printing method or any polymer 3D printing technique, it is arising from the limitations of additive manufacturing. So the very basic post processings uh, are the result of the limitations of 3D printing or an attempt to overcome the limitations of 3D printing, few of the limitations which we can overcome through post processing. The first one is high surface roughness. Now, irrespective of the technology, in most of the 3D printing technology, we expect a slightly higher roughness side, either because of the powder particles being used in the 3D printing method or because of the layer by layer phenomena. So there are layer marks or layer evidences. Then we have poor dimensional accuracy. So we have studied in the previous modules where we discussed the various 3D printing techniques. So what is the accuracy that we can expect in each one of them? So if just to overcome that particular limitation, you can do post processing, machining, and other things and improve your accuracy. Then limited materials. Now, materials is a very important factor because right now 3D printing is a new technology and there are limited set of baskets of materials which are available for any 3D printing technology. So every time you will not have a one-to-one match for the material that you intend to use in your in manufacturing of your part based on the end application. For example, if my end application is allowing SS304, but in 3D printing, we don't have SS304, so we need to use SS316L, which is an inequivalent of SS304 or SS310. So, in order to match the material properties exactly to what I need for my end application, requires post processing. Then layer marks, this is again something related to high surface roughness because of the layer wise evidence on the part on a 3D printed part, there is high amount of layer surface that is generated. And in order to get rid of that the high roughness or reduce the surface roughness number, we need to do some post processing. High residual stresses. Now, this high residual stresses is usually in most of the 3D printing process because all of them are thermal based phenomena. Whereas in metal 3D printing, high residual stress sometimes leads to warpage and crackage of the part. That's for a metal additive manufacturing process, we have a post-processing heat treatment method that has to be done for each and every 3D printed part in laser powder bed fusion so that the stresses are relieved much before they transform into strains or show any deformation behavior. Then machine constraints. Now machine constraints is very simple. For example, you have a build volume of 500 into 500, but you want to make a part of 1 meter. So you have to split the 500 part and then make it into 1 meter, and then as a post processing additional method, after the part is printed, they will be joined together. In polymer it can be joining, in metal it can be welding. Now, let's try to understand few of them in a bit detail, so that we completely get the idea that what, where and all, and in what cases processing is required. So what you see on your screen is a 3D printed aerofoil. Now this aerofoil is not having a very good surface finish. You can see there are line marks and the surface roughness is quite high. But when we talk about aerofoils as a subsystem or as a component to be used in aerodynamics, the flow has to be absolutely smooth. And in order to have a smooth finish, what we need here is we need a good post-processing technique that can smoothen these surfaces, and thus the performance of the end part is not affected. So this part will be taken through number of techniques such as vaporization or smoothing, and then it will be prepared as per the end application. Now, what you see on your right hand side, this particular surface roughness at the down facing areas of these angles. So this is to demonstrate that as the angle of any feature varies, its surface roughness also varies. And when the surface roughness is varying in such a way that it is very much different from the other areas of the part, then specific post processing attention needs to be given to those highly surface areas. So in metal 3D printing, your whole of the part will be coming out with a different surface finish. So surface finish becomes one of the most important post-processing technique used for metal 3D printed parts. Then we have dimensional accuracy. So most of the parts that are printed using 3D printing will their dimensional accuracy or tolerance would lie somewhere between 0.1 mm to 1 mm plus minus 1 mm, depending on what kind of technology we are talking about, what kind of size we are making about. Now if your post processing requirement is much less than that, if for example for a feature or for a dia your tolerance required is plus minus 50 microns, and through 3D printing you are getting plus minus zero point 0.1 or zero point 0.2 microns, then what to do in such situations? You provide additional stock in those areas and then machine those areas out using the right post processing machining method. So depending on the accuracy that you are getting from the post process from that 3D printing technique, as well as what is your target accuracy based on your end application functionality, that has to be taken care during the post processing technique. Then we talk about residual stresses. So as you can see, these are the specimens printed on laser powder bed fusion process. Now when these specimens are wire cut in order to separate the part from the base plate, they tend to show some deformation, as you can see in the image. This is because of the high residual stresses contained in the part, and if we don't heat treat these parts before wire cutting, then almost all the parts will show similar kind of deformation. So in order to avoid such deformation warpages, it is a mandatory post processing ritual that the part after printing in DMLS, LPBF or selective laser melting, basically powder based metal 3D printing, it goes to the furnace, it is stress relieved, then it is taken out, cooled down, and then after that the wire cutting is done, so that there are all the residual stresses are gone during the heat treatment of the part. So that was about the reasons that enable the addition of post-processing techniques in the 3D printing workflow. I hope this is very clear. Now in the next video, we will go through a number of post-processing methods, both for polymer and for metal. Thank you. Like, what is post-processing? And then we went through the basic limitations of a 3D printing process that make post-process mandatory for most of the 3D printing processes. And now we will talk about the specific post-processing operations required for metal additive manufacturing or metal 3D printing. So basically, as we saw that the biggest limitation in 3D printing are surface roughness, uh, your dimensional inaccuracies, and then residual stresses. For residual stress, we do stress relieving, and that stress relieving is basically depending on the material. So every material, for example, aluminium alloys will have a specific heat treatment cycle for relieving the stresses. Stainless steel will have a separate cycle, heat treatment cycle for relieving the stresses. And similarly, titanium, Inconel, each of the materials used in metal 3D printing will have its own cycle for stress relieving, which is largely influenced by the conventional heat treatment cycles used for similar alloys. Then for accuracies, we will go ahead for machining. Now, machining can be varied from turning, milling to grinding, honing. So, whatever conventional machining processes are applicable based on the tolerances that needs to be produced, the same are applicable for a 3D printed part. Once the metal 3D printed part is out of the machine, out of the 3D printing machine, then it can be treated just as a conventional component and the machining processes can be applied on it. Now, what is interesting or what is a new vertical for post processing for metal additive manufacturing is the surface finishing techniques. So, let's talk about the surface finishing techniques in a bit more detail. One of the very popular technique is polishing, which is basically nothing but uh, using some emery papers, filers, your diamond paste, and then you're finishing your or polishing your component. That gives you a very shiny finish. It depends on how much you are polishing, what techniques you are using to polish. Accordingly, you will get the surface finish. Usually, polishing is uh, done when you want to have a shiny finish on your surface. Then short blasting. Now, short blasting does not give you a shiny finish, but it improves the surface roughness. It reduces the RA value or RG value of any component produced through metal 3D printing. Short blasting ke liye there are various techniques. So in this video itself, we will go through one quick video of an OEM where we will try to understand the short blasting, how it is done, what are the different variables there. And then we have tumbling. Tumbling is a vibromechanical finishing method where you put the part amongst large size ceramic granules of around 8 10 mm dia, 30 mm, 20 mm height, and then they rub against each other and they rub against the component which has to be finished in a vibratory motion and hence provide the desired surface finish. Now, what you see on your screen is a highly polished component. uh, After 3D printing, you get the component which is having grainy finish, powdery finish, or a matte finish, we can say. And then, if you want to achieve a surface finish like this, what you see on your screen, then you need to go for post processing methods such as polishing. Now, some other post processing methods, surface finishing methods, which will yield you similar kind of results, but you need to choose depending on your application and depending on your uh, budget, economics, and everything, lead time. One more such process is micro machining process, which is being into the industry only after 3D printing came or because of 3D printing, I would say. Now, micro machining process uses uh, chemically catalyzed abrasive materials, micro abrasive materials, to remove material from the surface and to provide a shiny finish. Then we have abrasive flow machining. Now, abrasive flow machining is a way of improving the surface finish of internal channels and cavities by passing a highly viscous, slurry based abrasive media. So, there are abrasive media, diamonds particles, abrasive media, uh, which are mixed in a paste. This is something like more viscous than the toothpaste that we use. So abrasive flow machining, but this is only used for your internal area. That is the catch here. Chemical leaching is another chemical based method which helps in removing the surface roughness of a component by passing the chemical through internal channels. So these are mostly used for conformal cooling channels or channels in electric motor casings or other type of casings provided for the purpose of cooling. those channels can be cleaned using chemical leaching. Again, you have on your screen one example, which is a titanium knee implant manufactured, this is a cobalt chromium knee implant manufactured through laser powder bed fusion method. And if you see that the surface roughness in as printing condition is around 21.02 microns, whereas the surface finish after taking it through number of post processing operations is RA 3.02. So yes, post processing can make a huge difference in the properties, whether it be mechanical or surface related. Now let's look at a small video. This small video was made by EOS Additive Minds. They wanted to display the differences between short blasting and short peening. So now I will please ignore that part. Just look at this video to understand how short blasting and short peening is done, and what are the different kind of medias that are used here. So this is the how the chamber inside a short blasting media looks. Now in blasting, what we do is we take the object, we use a nozzle from which uh, media is coming out with compressed air. This media can be nutshell, ceramic, steel blade, silicon carbide, aluminum oxide. Now when we talk about this media, this particular media gives you uh, all the different kind of medias are used to provide different kind of surface finish. Now in the short blasting method, one person has to hold the part and we have to make sure that the distance is good enough so that neither it is over removing the components nor it is what do we say, uh, under removing the materials. So nutshells, ceramic, steel beads, silicon carbide nutshells are used to provide very glossy finish to the part. Sorry, not glossy, it is used to provide a white finish to the part. It helps in cleaning and brightening of the surface, whereas ceramics are used for surface compression and providing a metallic matte finish, shiny look to the component. We will have a look at a few of the samples after this. Steel beads. Now steel beads are again used for surface compression. So they not only improve the surface roughness, they also help in providing compressive stresses to the component, which is very much usable, desirable in order to improve the fatigue life of the components. Silicon carbide, again, it will give you a smoothing finish and a matte look. Now, blasting is something which is used for cleaning and smoothing, which we will be mostly we are using in post processing techniques. Whereas if we talk about short peening, it is basically done with a slightly more compressed air pressure, so that it actually hammers the surfaces down and induces compressive stresses on the surfaces. Now, the purpose of doing this is to, as we know that in 3D printing, we have to clean the surfaces, smooth and change the appearance. But what we need to do is first, we need to target specific areas and make the different kind of finishes, different kind of surfaces, which are having different kind of surface finishes. We need to make sure that all of them are nearly in the same range, and then we can do a overall process. Now here you can see that there are different kinds of finishes that has come up using different kind of media. So that is how much difference a media makes. So yeah, this is about short blasting. You have seen the operation. Now let's talk about the polymer post processing. Now polymer post processing is very simple. You get the part, you remove the you remove the surface burrs, you smoothen the component using emery paper, you apply putty to it, you again further smoothen it, use emery paper and make the surface very fine, and then you go for a round of primer and painting. So the same thing we will see using this video. There is a 3D printed part which is having different kind of roughness at the different sections because it's a layer by layer method, and the depending on what region we are talking about, the surface finish is varying by a lot. Now
if we have to post process this, the first step would be to making the surface finish as uniform as possible as we can, using manual finishing methods such as an emery paper or uh, yeah, some pneumatic tools which are used for polishing of surfaces. But we should take care that the tools are favorable for the plastic that we are dealing with. That also comes in concern. Then once all the sanding has been done, initial sanding, surface preparation, we apply putty to it. Once the putty dries, again we need to do sanding on it, and the sanding is done. Now after doing putty and second round of sanding to remove that excess putty, the surface will be very, very, very smooth already. Now it's time that we can go ahead for our primer applications, and then we can start printing the part. So now the part is being taken up for printing. This is the first round of primer, white primer that is applied. Then the black color, that is the desired color in this case. Now, once the black color has been given to the part, we might want to apply different colors to different sections of the component. So what we do there is that whatever area we want to be remaining in black color itself, we mask those particular areas and apply a different paint on the other areas of the part. So now this part is going through another second round of painting, where the masked areas will not have that painting, whereas the areas which are exposed will get a coat of the new paint that has been spread on it. And once the it is all dried up, we remove the mask tapes, and we get the final part that we have to use for the end application. So I'll just show you how the part looks like. Yeah. So this is how the part will look like. So that was about post processing, and by this you complete the last step of the additive manufacturing workflow, which is post processing. I hope this is useful for you and you will use it in your future applications. Thank you.